Niel. So when I submitted the abstract, I was just planning to talk about electromagnetic searches for supermassive black hole binaries and how we use LSST to find these things. But since then, there have been some exciting developments in the gravitational wave search for binaries. So I'll just cover that and talk a little bit about the synergies with LSST. So as you all know, from observations of nearby galaxies, we know that every massive galaxy has a supermassive black hole, and that black hole is a very important component of the host galaxy. We also know that galaxies merge very often in the history of the universe, and that process naturally leads to galaxies that have two supermassive black holes. And as the black holes the merger evolves, the black holes come to smaller and smaller separations. So once we have a galaxy merger, the two black holes sink at the center of the newly formed galaxy through dynamical friction. So this is large-scale interactions with the gas and the stellar bulge of the newly formed galaxy. And that process is efficient to bring the galaxies to separations of a few parsec. Then when we get to the parsec regime, the interactions with the immediate environment become more important. So if there are stars, the binary can expel the stars at large distances and by that process lose some energy. If there is gas, the gas also can act as a catalyst to the binary evolution and move these binaries to smaller and smaller separations. At the last stages of their evolution, the binaries will emit gravitational waves, and the gravitational wave will be the dominant process that brings the binary to the final coalescence. So of these three stages, the intermediate one is the most uncertain. There's a question mark here, and the reason is that we don't have any observations, any confirmed binary at subparsec separations. I would put an asterisk on this, given that we have some recent developments and some exciting news for gravitational waves, but still we don't have one source that we can say this is a subparsec supermassive black hole binary. So where are we observationally? Of course, we have a lot of observational evidence that galaxies merge. We see the initial stages of galaxy mergers and the interactions with the of the two galaxies. We see galaxies with two active supermassive black holes at kiloparsec separations. And we even can resolve the two black holes when they are at parsec separation. Now, when we go to subparsec separation, resolving them becomes impossible. So we need to infer the presence of the binary from the effect it has on its environment. The good news is that we typically expect to have gas in the center of a post-merger galaxy. And that gas can activate a quasar. We know that at least some quasars are associated with galaxy mergers. So one of the most promising methods to find these binaries at the last stages of their evolution is to find quasars with periodic variability. Now, I would argue that this idea of periodicity is fairly intuitive. We have an orbiting binary, that periodically perturbs its environment. But this has also been seen over and over in multiple hydrodynamical simulations. So when we put two black holes in a gaseous disk, so what happens is the two black holes will initially push the gas from the central region outwards, and it will create a cavity of low-dense material. But as the binary interacts with the edge of the cavity, we have these streams that enter the cavity and hit the black holes. So if we look at the accretion rate to the black holes, we see that it is periodically modulated. So this is one of the ways that you can produce periodic brightness modulations. The other is related to the gas that gets bound to the individual black holes. So this gas, if it emits, it's also moving with relativistic velocity. So we should have effects of special relativity. And for example, if we have an unequal mass binary, typically the smaller black hole has a brighter mini disk because it's the one that is moving closer to the edge of the circumbinary disk and pulls most of the material inwards. And it's also the one that is moving faster. So when the secondary is moving towards the observer, it will appear brighter. When it's moving away, it will appear dimmer. And that gives rise to this very nice sinusoidal periodicity. Now, in the last 7 or 8 years, we had a lot of developments in this field because for the first time, we had the time domain data that we needed to do systematic searches for quasar periodicity. And now we have about 250 candidate systems from pretty much we have analyzed all the time domain data that are out there. The emphasis here is, of course, on the word candidates. And the reason for that is finding periodicity in quasars is extremely challenging. One of the reasons is that the periods that we are looking for are a few years. So we can't see many cycles of that periodicity in our data. The other reason, of course, this is an AGN conference. You're all familiar with AGN variability. And you know that AGN variability is stochastic, and that stochastic variability can mimic periodicity. So what I'm showing here is one of these candidates that were claimed to be periodic. And on the pink on the back is a simulation of quasar variability of a typical quasar that has one supermassive black hole. And you can see that in the limit of few cycles, it's practically impossible to differentiate the two. So we do expect that this sample of 250 candidates is contaminated with a lot of false detections. But if there is a periodic source, maybe it's one of those. Now, confirming even one of those is a really important thing because, as I said, we've never observed a subparsec supermassive black hole binary. And there are two routes, I guess, we can take. One is observe much longer, see if the periodicity is persistent, accumulate many cycles, convince ourselves that the source is periodic. We are talking about periods of a few years. So if we want to observe 10 cycles, we need a few decades. So that takes a long, it takes a lot of time. The other possibility is to look for other signatures. So I will just briefly mention one of these signatures. I already mentioned that in some cases, we expect to have the effects of special relativity. So if we have the periodicity arises from a relativistic Doppler boost, there is a multi-wavelength prediction. So for example, if we look at optical and UV data, the amplitude of the variability will depend on the spectral slopes. So if we have spectra of the sources in two different bands, we can predict exactly how the light curves will look like. So they will change simultaneously, but with different amplitudes, which are predictable from the slopes of the spectrum. So I'll just show you the best example we have for this. So this is PG1302 is one of the first quasars that was identified as periodic. And the top panel shows the optical data. The blue curve is the fit to the optical light curve, knowing the slope of the optical spectrum. And then on the bottom, we have the prediction for the Doppler model from the UV spectrum. And then we ask Swift to observe this source, and you can see that the data line up well with the prediction. So we can say that this source is consistent. However, you can see that the data are sparse. They cover only a small part of the periodicity. And the other key thing is that quasars also have wavelength-dependent variability, and that is not a unique signature. So in that paper, in the 2018 paper, we looked at a control sample of non-periodic quasars, and we compared the optical and UV light curves, and we saw that even by chance, we can get these signatures at about 25% of the time. That improves as we get better quality data. but still you can see that the UV light curves are not great quality. I'll just very briefly say that there are a lot of other signatures, either photometric or spectroscopic, that we can look. Even the jets, there are predictions of how the jet should look if the base of the jet is moving in a binary. And the main takeaway from this is that there are candidates that show independent lines of evidence, but none of the signatures is unique. And it's very hard to distinguish them from the typical quasar variability. Now, of course, this is an LSST conference. We are all excited about LSST. And in my opinion, LSST will be a game changer for this type of search. First of all, because the quality of the data will be great. Well, maybe. But the other big aspect of LSST is that the sample of AGN that LSST will observe will be 2 or 3 orders of magnitude bigger than what we have now. So in that huge sample, we expect to find even more rare binaries that have shorter periods. So for example, this is a prediction by Cheng Xin, and they looked at the population of quasars that we expect to detect with LSST. And I would say this is a highly optimistic model, but there are predictions that we should see binaries with periods of 2 or 3 months, and they should be in the hundreds. So if we see something like that, if we see a binary that has a period of 3 months, we'll see 4 cycles in a year, 40 cycles over the course of the survey. So then we can be certain that this source is truly periodic and it's not just a fluctuation of the noise. So another prediction has to do with slightly different, let's say, configuration of the binary. I already talked about the relativistic Doppler boost. There are also the case that we could have self-lensing flares. So one of the black holes go behind the other, and because of general relativity, we have strong lensing, and we get these pronounced flares at the exact time when one black hole is behind the other. So there have been some predictions on how many of these systems you should predict. This is based on a cosmological simulation called Illustris. And you can see that we expect of order 100 Doppler boost candidates and more of those with self-lensing flares. Now, the reason we expect more self-lensing flares is because in that model, the flare is very pronounced and it's also symmetric. So we don't need to see many flares to convince ourselves that this is periodic. Just by the fact that these flares are symmetric and repeat, it's a strong indication that this system could be a binary. So there are, as far as I know, these 2 papers are the predictions of how many binaries we should see in LSST. Now, thinking about LSST, we, with Caitlin Witt, who is now a postdoc at Northwestern, we developed a pipeline to select periodicity on top of dumb random walk model. And then we decided to test it with simulations and test something like the current capabilities. So data that look like Catalina, and also make predictions about LSST. So what I'm showing here is the true positive rate, so real periodic signals that we should be detecting, versus the false positive rate, so noise that is falsely identified as a signal. And you can see, and the star is the detection threshold that we set with this method. So if we look at Catalina, which is this level here, I'm trying to point. So you see that the true positive rate is about 60%, the false positive rate is about 20%. So we have a huge contamination of false positives. But then we go to LSST, which has better sampling, and we can think if what we simulated is realistic. But then with LSST, we go to something with a much smaller false positive rate. Now, you can see that in both cases, we have low true positive rate or relatively low true positive rate. And the reason for that is the stochastic variability that I already mentioned. If we had white noise with LSST, we would find all the periodic sources, but we don't. Just to dig a little deeper on that paper, we also looked at the different parameters that we simulate, like the periodic signal and the time random walk parameters. And you can see that the detectability of these sources depends both on the signal and the noise. So on the top, in general, this is the red curves are the true positive rate, and the blue curves on the bottom are the false positive rate. And the solid lines are LSST, the dust lines are Catalina-like light curves. So you can see that it's easier to detect the short period binaries. I think that makes sense because we have more cycles, so we accumulate better significance over the course of the survey. It is also easier to find the ones that have higher amplitude, so find the strong signal. That also makes sense. In terms of the noise, when sigma, which is practically the amplitude of the noise, increases, our ability to find periodic signals is decreased. So pretty much the periodic signals are buried in the noise. Now with tau, it's a bit more strange because we see a dip at about of order 100 days. And I think what is happening here is the two time scales, the period and the damping time scale of the time random walk are very similar. And that hinders us from finding the real periodic signal. In terms of false positives, I think as the sigma increases, we get more false positives, but with tau, I would say it's relatively flat. So that's all I had for the time domain electromagnetic searches. So I'll spend the last few minutes talking about gravitational waves. So these binaries are very promising sources of low frequency gravitational waves. They cannot be detected from ground-based detectors like LIGO, but they can be detected with detectors like pulsar timing arrays, which I will explain in a moment, and LISA in the future. So LISA will be just a gigantic interferometer that will fly in space. So this is a very exciting time because last month, all major pulsar timing arrays have announced that we have found the first evidence for the low frequency gravitational wave background. So I'll just explain how pulsar timing array works and how we got to that detection. So pulsar timing arrays are a galactic scale detector that rely on millisecond pulsars. So pulsars are magnetized neutron stars and they have this collimated beam of radiation. They're also very stable rotators. So as they rotate, we get this lighthouse effect. So every time the beam of radiation swipes our line of sight, we get a pulse that we can record with radio telescopes on Earth. And because they rotate very stably, these pulses repeat very stably. So with pulsar timing arrays, we monitor many of these pulsars. And the idea is that if we have gravitational waves passing through our own galaxy, they will squeeze and stretch the space-time. So they will squeeze and stretch the distances between the pulsars and the Earth. And so instead of getting this precisely periodic profile, we will get some pulses arriving sooner and some pulses arriving later. And if we see this signal in many pulsars, and also this signal is correlated among different pulsars, then we can detect gravitational waves. So I'll take a second to describe this correlation pattern that we expect, because this is the telltale signature that we have found. So this is called the Hellinson-Down curve, and it shows the degree of correlation as a function of angular separation of the pulsars. So we have a pulsar pair, and the two pulsars are roughly from the same part of the sky. This was supposed to be a GIF, but it doesn't work because it's PDF. So the two pulsars will experience stretching and squeezing simultaneously. So if they are at 90 degrees, the two pulsars one will experience a stretching, the other one will experience a squeezing. And if they are at 108, again, they will experience the squeezing and stretching simultaneously. So we go from positive correlation to negative correlation and again positive correlation. So this was the red line is the theoretical expectation for the correlations among pulsars. And this is the data. So you can see the black now is the theoretical expectation. The blue is the data. So all PTAs have found something like that. So they have found the characteristic interpulsar correlations between 3.5 to 4 sigma. We expect that the significance will increase as we time more pulsars for a longer time. And this signal is consistent with supermassive black hole binaries. So the very exciting thing is that the signal is somewhat stronger than what we had expected in the past. So here are the predictions of over the last 25 years for the amplitude of the gravitational wave background at a frequency of 1 year and at a frequency of 1/10 years. And you can see that it is towards the high end of what people have predicted in the past. So that means that binaries merge more often than what we expected, or that their masses are higher than what we had expected. So what exactly that means for LSST and how many binaries we should find in LSST, I can't tell you right now, but maybe I can tell you in a few months because we have just started thinking about this. Okay, so for the last 5 minutes, I will switch from the background to finding individually resolved binaries. So this will be strong sources that will stand above the background. And the exciting thing about this is that we can combine their gravitational wave emission with the bright electromagnetic emission and do multi-messenger observations. This is important because each messenger probes different parts of the physics. So gravitational waves probe the orbit and the dynamics. Electromagnetic observations probe the conditions of the gas around the binary and how it interacts with the binary. So we have looked at how many binaries we can see with both messengers. So this is the parameter space in terms of total mass of the binary and period that we can detect with electromagnetic surveys. So this is the blue shaded region, and with gravitational waves. So the purple shaded region show different sensitivities of PTAs, starting from the nanograv 11-year data set. We already have 15 years of data, and then projected sensitivities in the future. So for now, we are limited, if we want to do multi-messenger observations, we are limited to the most massive black holes binaries out there. But as the sensitivity increases, the common parameter space also increases. So hopefully with LSST, and as PTA sensitivity increases, we will have a few of these multi-messenger sources in our data. So why do we want to do this multi-messenger science? The idea is that each signal has different dependencies. So for example, if we look at different parameters here, like the mass ratio or the total mass, and we constrain it only with the electromagnetic signal or only with gravitational wave signals, you can see that we can get very different constraints. So putting them together gives us the best parameter estimation. So we have started playing with that, and I have simulated many binaries and analyzed them separately with electromagnetic data, gravitational wave data, and then writing a joint likelihood and analyzing them as a single data stream. And here what I'm showing is the percent error for the injected parameters. And you can see the best is to be peaked around 0. So for some cases, for example, here, we get much better constraints when we look at the multi-messenger signal. So this is preliminary results and it's still a work in progress, but I think it's very exciting. So I wanted to share this with you. And I will just leave the summary here and take questions.
Questions? Go ahead.
Great talk, Maya. My worry is more about, hunting these QPO signals. And I think we need to sit together at some point and discuss what's the most optimal way to extract the, QPOs and to test their significance.
Absolutely.
Because as you have seen and you have showed that in your slides also, there was a QPO claim in a source, and then there was another paper which says that it's just red noise. And we certainly don't want to happen that with the LSST data. We want to make sure that our tools are ready to test the real, to distinguish between the real signals and the noise.
I think you're right. Well, first of all, let's say in all of these searches, somehow the dumb random walk noise was taken into account. Each paper implemented a different strategy to account for the red noise. The other thing I would say is that this is really challenging. And I don't think we can totally avoid it with LSST. We can be more careful. We will understand the noise better as we...
But if we can constrain our red noise properly, then we can also constrain the significance of the signal in a better way too.
Right.
So one of the issues which I feel is that when people are using these different methods, every method has its own way of dealing or detailing, and some of the methods actually don't take into account the red noise processes, and that's one region I think is responsible for predicting different significance or different periods from your data.
I totally agree that there has been like a history of people not accounting for the noise, and I think in different wavebands people are more careful or less careful. But I would say there's also something intrinsic to the noise being like that. So if I show you this, it can fit equally well with the sinusoidal model and with the dumb random walk model. So it is a limitation from the data and from the fact that we cannot see many cycles. If we want to be extremely conservative, we will require from the beginning to have many cycles of periodicity. But then since we are searching for something rare, I wouldn't think that this is the best strategy because you will probably not find anything in the end. And because as you collect more and more data, you can, prove or disprove or build your confidence or the significance of these sources. I would say finding some candidates, good quality candidates, and then verifying them with additional data would be my strategy. I wouldn't be like the most conservative from the beginning. Like if I don't see 10 cycles, I don't claim a candidate, because the chances are we are going to miss the rare candidates, the rare binaries that are out there.
Yeah, I think that sounds good too.
Okay, go ahead. Yes.
So in these cycles that you saw, where you see like periodicity or oscillations, the time scale is years. But could you think of any scenario in which the time scale would be like months, like I don't know, 3-4 months?
Yeah, even in the binary scenario, we do expect that binaries will get to periods of a few months. The thing is, I think these are more rare because the binaries spend more time at the bigger separations.
But if you expect this like month time scale, the separation would be like shorter, or
it will be shorter, so it comes closer to the merger. And because this is an accelerated part of the evolution, we expect that we have fewer systems in that. And that's why I'm saying LSST then, because it has this huge sample, maybe it will detect these short period binaries, because you need millions to maybe find a few.
Okay, sorry, I think we better move on. But look, any more questions, please talk to the conference break. Thank you again.
Thank you.
Yeah, just a comment from the Zoom audience. If speaker can use this pointer, it's hovering to the screen, they'll much appreciate it because they can follow what you're talking
Oh,
about.
so not the sticker.
But they cannot actually see you
Got it.
speak from
Okay.
far away.
All right. Got
If
it.
you can, yeah.
Yeah.
Okay. Clock's not on the screen up there.
Oh, yeah. It's my bad.
Okay, so we'll now hear from Yasaman Homayouni. Oh, you want to go back one, just tell us about, yeah, again, a black hole mass census with Rubin LSST.
Right. Hi, everybody. So today I want to talk about mostly reverberation mapping and how we can use LSST to build a black hole mass census and how important that's going to be. So one of the main things we know about supermassive black hole is this tight correlation between, am I pointing? I don't know.
Yeah, this is.
All right, okay. This tight correlation between the black hole mass and the mass of the bulge. And despite decades of research, we still lack a coherent picture of what are the main drivers of this tight correlation. What is the role of large-scale environment on fueling the black hole, and what is the impact of the black hole outflows on the growth of the galaxy? And one of the main things here is that if you look at this correlation, there's a very large error bar on the black hole mass. And even though the black hole and the galaxy have these different scales, these properties seem to be correlated. So one thing that is important here is that we do a better job of measuring our black hole mass. So we are technically we can do dynamical measurements for a few of the nearby black holes, but for the majority of them we can't do much. There are a few exceptions here. There's the case of the first quasar where we can use practically use observations to get resolve the brightline gas around the supermassive black hole. This rapidly rotating gas around the supermassive black hole. There are a few other cases. There is the NGC 3783, which is the gravity team were able to resolve this broadline region. But this is the only two so far. And there's of course the famous case of the two event horizon cases where the event horizon team practically used Earth as a giant interferometer to resolve the shadow of the black hole. And we can do this for the center of our galaxy, which is Sagittarius A star, and also M87. So if you can do this for just these few cases, how can we get a better estimate of black hole mass for the other remaining quasars? So we often use a technique known as reverberation mapping, also known as echo mapping technique, where you practically use light echoes to resolve the spatial parameters in the black hole. So the quasar environment is prone to rapid short-term changes. The ionizing flux from the center is going to get reprocessed by the different components and gets reprocessed after some time delay. So you can see the direct emission from the black hole in a region, and you can also see the reprocessed light. So by measuring this time delay, you can measure, get a sense of the physical distances in the black hole. So as one of the main components of a quasar, the broadline region responds to this changing ionizing flux. And what you can see is that you will be able to measure this distance using reverberation mapping. So practically you are you're substituting temporal resolution rather than spatial resolution. So if you can measure this time delay, and you can combine that with a velocity width measurement, you can get an estimate of the black hole mass using the real product. And there's this F factor here that includes all the information about geometry and dynamics of the system. And this is often done for a prominent emission line. Throughout this talk, you hear me mention H beta, H alpha. What I mean is I am trying to measure the H beta emitting region in the broadline region, or H alpha emitting region in the broadline region. So I often refer to them as H beta RM in my talk. So in principle, you can do this for any quasar, but in practice, this has been done for maybe about 60 AGNs up until a few years ago. And this is mostly limited to low redshift, redshift of less than 0.3. And it doesn't depend on the luminosity of the target, so you can do this for any quasar you want. One of the main byproducts of reverberation mapping is this tight correlation between the radius of the broadline region. So what you see here on the y-axis is the H beta emitted in H beta size from reverberation mapping, and the x-axis is the continuing luminosity at 5100. So if you look at the local targets, these are mostly from local observation of reverberation mapping. You see that there's this tight correlation. And this is very attractive in reverberation mapping because you can use single luminosity measurement to get an estimate of the broadline region size. So you can practically get an estimate of the y-axis and then combine that with a width measurement and get a black hole mass. Particularly attractive when you are dealing with a large sample of targets, when you don't want to spend a lot of time measuring single by single target. So this is one of the really important results from reverberation mapping. But one needs to know that this is only done for low luminosity AGNs and low redshift targets and for only H beta. So it seems that what we need to do is we need to target more quasars in higher redshift universe. And in fact, if you look at on top of this plot, so this is the exact same plot. Sorry, this is the exact same plot. I'm just showing more measurements from more diverse data sets. So what you see in blue and red are higher redshift observations of reverberation mapping overplotted on the same thing. So if you look, there seems to be an offset between reverberation-based observation when you overplot on the same scaling relation. So in a sense, if you use the scaling relation to get the estimate of your mass, you're gonna keep overestimating your mass because the true observations are all below that line. So it seems that what we need to do is to target more quasars, a diverse sample of quasars going into higher redshift, and also target many different emission lines. And in fact, if you look at the SDSS population of quasars, you see that all the previous observations are all limited in a narrow space in eigenvector 1 plane. So there seems to be this need to target a larger data set in a more diverse sample. So this known digital sky survey reverberation mapping was designed for this case. The campaign started in 2014 and is planning to continue all the way in 2026 as part of SDSS-V. Started with 850 quasars, expanding the redshift up until 4.5. We have observations from SDSS in spectroscopy, and we have simultaneous observations from CFHT, BOC, ZTF, pan-stars. So what the goal is to target a less biased sample in the most possible way we can. So the selection criteria here is that we only select targets that are below magnitude of 21.7. So this is the picture the parameter space that looked before SDSS-RM started. we have a few targets in H beta. In the low redshift regime, we have just 2 targets in MG2, and then more targets, about a handful of targets on carbon-4. And what SDSS-RM has been able to do is to fill this gap between low redshift and high redshift. So we started with about 45 H beta up until redshift of 1, and then adding about 60 in MG2 in redshift, mid-redshift range, and then adding higher redshift carbon-4 observations, filling this gap nicely throughout the course of 4 years. So these are results from 4 years of SDSS-RM observations, which combined added 150 reverberation-based masses to our existing sample. A little bit on our analysis. So this is where we spend most of our time, where we look at 4 years. So this example shows a 4-year light curve. Top is the continuum light curve, bottom is the line light curve. And we often deal with gaps in our observations, which we need to be very careful about. So that's why we apply weight, which is typically a convolution between the autocorrelation of the continuum light curve as well as what is the number of overlaps between our observations. So we need to be very careful about, we have the best chance of detection when we have overlap between our observations. So that's why we apply this weight to our lag prior probability distribution. This is a very good target that doesn't show aliases, but we don't have that kind of clean lag posteriors. So you see that we have a lag of about 60 days. So this tells us that the MG2 emission region, in this case, is about 60 days from the source of the ionizing continuum. One thing that we need to be very careful about is that the SDSS-RM is an industrial scale survey. So you need to be really careful about the gaps that we have in our observations, and that's why we apply the weights. What are there? You have to apply statistical priors on our lag detection. And we really are looking for genuine reverberation rather than just noise. So we apply this statistical cuts on our lag detection, where we want to look for lag measurements that are significant from 0, usually 3 sigma significant from 0, and lags that are concentrated in one single peak in our lag posterior, do not want to have aliases in our observations. And we usually set these threshold of statistical cuts based on average having 10% false positive rate, as we expect from our survey. So when we do this kind of cuts, what you see at the bottom here is the distribution of the lags, all of our lag measurements in the 4-year data set. So on the 4-year data set, we have a typical baseline of about 1,000 days. So what you see here is the distribution of lags over this baseline. And you see that we have this excess of lags in the positive regime, even without applying the statistical cuts. When we do apply the cuts, is this red histogram here, which we pick, sort of cherry pick the most reliable measurements that we know. But even without doing that kind of cut, we still get a positive excess in the lag measurements in red, which tells us that most of our measurements are from genuine reverberation rather than just noise in our observations. A big overview of this is a result from a recent paper that was submitted. This is a result from 7-year data set, where we have been looking at the 7-year lag curve combining with a sort of 10-year photometry from Penn stars that we've detected. Almost 300 masses from reverberation mapping, going from H alpha, H beta, MG2, and carbon-4. What's going on? Okay, all right. So I mentioned the H beta emitting H beta radius luminosity relation. One positive. Is it good? So one thing that I mentioned before was the radius luminosity relation in H beta regime and how we do not have the same kind of results in the other lines.
Let me try to stop sharing. Can you just go use your speaker and I just turn your slide if you call. Give me a sign.
Can you go back?
Yeah, sure.
So I mentioned this radius luminosity relation and how we have this only for H beta, but not for the other lines. And it's specifically for MG2 because we only had 2 measurements before, so maybe 3 measurements in MG2. So SDSS-RM has been able to fill this gap in the continuum luminosity and MG2 line, and we are able to find a radius luminosity regime in MG2. What we find is that on overall, we are broadly consistent with what we expect from basic photoionization observations, which are shown in blue. So you're gonna
if you give me a sign, I'll just
okay, all right. So if you go to the next slide. So far we talked about how we can do emission line reverberation mapping. Usually, this means we are measuring physical sizes using light echoes, and we need multiple epochs to measure these time delays, and this takes months to years. SDSS-RM has already tripled the previous sample of black hole masses that are measured from reverberation mapping, and this is a huge expansion in terms of parameter space, both in redshift, luminosity, and accretion rate. If you go to the next slide. So I now want to talk about something slightly different, still within the context of reverberation mapping, but this time targeting the accretion disk. So one other thing we could do if using reverberation mapping is instead of looking at the broad line region and the accretion disk, we want to only look at the accretion disk itself. So that means looking at the hotter emission from the accretion disk, and then also outer cooler regions of the accretion disk. So based on that, we can do this kind of measurement of what is the disk size on the disk. And people often use this if you have multiple photometric bands. You can use this to study the accretion disk stratification, how to, based on the different bands, your temperature changes on the accretion disk. And so we applied this method on the SDSS-RM data set. If you go to next. So we applied this on the first year of SDSS-RM data, which we had the most higher cadence observations and no gaps in our observations. This is the broader sample of this quasars with accretion disk measurements. Some of them are filled, which means that we have already measured the black hole masses through reverberation mapping, and some of them are open symbols, which means we use single epoch or this radius luminosity relation to get black hole masses for them. So this is the parameter space of about 100 targets that are measured using continuum reverberation mapping. And you can compare that, compare that with the previous observations. You can see how all of those previous observations are targeted to a local universe, also in a narrow range of parameter space. So if you go to the next, so most of the observations that have been focused on the local universe, they are finding disks that are about a factor of 3 or 4 times larger than is expected. A very famous case is NGC 5548, where they used 6 months of HST observations to target the UV part of the disk, as well as coordinated multiband observations from the different sites on the ground, as well as SWIFT And they found that the disks are a few orders bigger than what is expected. But most of these observations also find that the wavelength dependence of the disk is consistently about 5 to the 4/3. So if you go to the next slide, please. So what we did is we got all of our disk measurements from reverberation mapping and compared what would the Shepard-Sanya disk expectation would be if we compared to our measurements. So y-axis is the disk size measurements, x-axis is the black hole mass, and you can see most of these gray points, which are the local observations, all are in a range of parameter space. So what we find is that on average, our disks are broadly consistent, but we have a larger diversity. We have, for a given black hole mass, we have very different disk sizes. So that's one thing that we wanted to look into. So we selected a few targets, the diamonds here, that we wanted to target with HST and see perhaps if their UV disk sizes are different. Other than that, we also wanted to combine all of our observations and get a statistical sense of what is the parameter on the disk. So we performed nonlinear regression on the black hole mass dependency and accretion rate dependency, and also disk size normalization. And we found that our disks are consistent with Shepard-Sanya expectation on average. We find black hole mass that is consistent with a mass of 1/3, and using luminosity as a proxy for accretion rate, we also find luminosity mostly about broadly consistent with luminosity to 1/3. But one interesting factor here is that we found a factor of 2 day that is offset, which is could be, we were relating this to any physics that we do not understand. This could be black hole spin. This could be relative efficiency. We still need to understand that part, which is sort of has to do with the diversity of the disk sizes that we measure. So going back to the subsample that we wanted to target with HSD. So this is about, we had 7 targets over the course of 2 HSD cycles, where we wanted to look at the UV disk size. Along with that, we had observations from Las Cumbres in different sites, and we found that our disks, we did the measurements and we found that it's consistent with the disk stratification model, but we find that the UV disk sizes are not that different from optical extrapolation. If you go to the next one. So this is an example of our UV and along with the optical light curves. So one interesting thing we found, which was not observed before, is that usually when these disk sizes that are measured in low redshift and they find disks that are larger than expected, one thing that people contribute, the thing that it's contributing is the contamination of the broadline region. Another factor is that sometimes we see this kind of difference, offset from the expectation, which people relate to the diffuse Balmer jump. So when we did our UV observations, we found that there are some observations that are lying on the exact diffuse Balmer or iron jumps, and this was observed in the lower redshift, but we actually found it in the higher redshift as well. But as I said, we found disks that are broadly consistent. The UV disk is broadly consistent with what we expect. And the most important thing is that we found this sort of difference. Okay. One interesting factor that people want to look into is, well, if you have your broadline region disks that are contaminated by the broadline region, and maybe there's some kind of correlation. And people have investigated and found that there seems to be a tight correlation. These are measurements from local universe. And what we did was try to add the SDSS-RM measurements and see if we can find the same thing. What we find is that we do not see the same kind of correlation. So the recipe of, if we have an accretion disk measurement, we can go to the broadline mass. black hole mass, because of this correlation, is not going to be so true if you go into higher redshift. At least that's what we find in the preliminary stages. In the last few minutes, I'm just going to give a quick summary. So what we learned from all this is that SDSS-RM has been able to provide a lot of black hole mass measurement as well as accretion disk measurements. SDSS-V is going to continue the SDSS-RM part all the way to 2026, and we expect about 4 to 5 times more masses from SDSS-V. And we have 5 high cadence fields, and we expect about 800 more reverberation-based masses. But the SDSS-V can go up to a redshift of about 3. Because of time dilation effects, you cannot go beyond that redshift. It's not going to be, so if you expect your target to be variable on a 3 to 6 month scale, because of time dilation effects, you would need a 12 to 24 months of observation to be able to actually detect that kind of variability. So you cannot use that kind of measurements beyond redshift of 3. So what we can do instead is, if you go to the next slide, please. What would be interesting is when we have LSST observations, come up with some kind of black hole mass estimator that would probe higher redshift. Go to the next. So SDSS-V is probing a redshift of about 0.3 to 1 to about 3, and then we have accretion disk measurements in the up to redshift of 1. So if we can use this overlap of SDSS-V as well as SDSS-RM disk measurements and be able to calibrate our black hole masses, we can build a black hole mass estimator with LSST that would be able to expand all the way to redshift of 5. This is important because, first of all, LSST or accretion disk reverberation mapping only depends on photometry. You do not need spectroscopy. Also, the accretion disk size measurement is only weakly dependent on redshift. So redshift is not going to be contributing as much as it would for the emission line reverberation mapping. So I kind of went over this, but the goal here is that we have accretion disk size measurements from SDSS-RM, and we have a subset of black hole masses from SDSS-RM. So we can combine these two and build a black hole mass estimator for when we have LSST observation. One way to move forward with this is try to understand if the harder UV emission has to do with larger disk size or not. So if the harder UV is going to be contributing to disks that are hotter or disks that are colder, we have an HSD observation that is going to investigate this. But we also have a subset of about 80 quasars that have overlap from galaxies, XMM, pan stars that we are investigating to do the ACD fitting for this. This is just going to emphasize that LSST is going to be transformational when we have a black hole mass estimator. We are able to build black hole mass sensors going all the way to redshift of 5 or 6, and it's going to be important because we have deep drilling fields that are going to produce about 1,000 continuum lags in every deep drilling field, and would fill this gap beyond redshift of 3. That's where I'm gonna...
Any questions? Go ahead, yes.
Yeah, the MG2 light curve that you showed, it has like also like very large error bar. So like how does it affect your time relay measurement and the black hole mass?
So that was a good lag here that you showed. And you saw the lag posterior is really single lag posterior that we had. So when we use the Javelin model to use a damp random walk to fit the lag curve, what we get is that even for that kind of large error bar, we have a single well-detected peak in our lag posterior. So the one that I showed you wasn't too bad. There are cases specifically for MG2, because MG2 is not as much of a variable line as like this carbon 4 H beta. There are cases that you have ADSs all over the place, so the only, so we can try different models to test if like there's like Pyro, Javelin, and see if they would provide a better fit. Or if the target is not, for example, doing much in a certain year, but it's variable in different year, but that's usually what we do.
Any other questions? Go ahead, yes.
Yes, and one of your slides, I think you showed that the disk size was related to the luminosity and the mass. So is that related to the accretion rate then? I mean, because it looked like it went maybe to the same power for both. I just curious.
Yeah, so what I can say is that in this kind of fit, we really wanted to focus on the observables. So what are our observables to be able to simplify the fit as much as we could. So we didn't want to go from luminosity to accretion rate and change that and then do the fit, because a lot goes into that kind of transformation. So that's why we had luminosity in there as this component, and translate that. Yeah, I would say going into what it means in terms of accretion rate, you have to make a bunch of assumptions, converting to bolometric luminosity, and then also assuming an accretion rate. So we'd have to make that assumptions, which we didn't want to do at this stage, or at least we weren't ready to do it at this stage.
Go ahead, yes.
Yeah, so actually about this, I was wondering, does the gravitational redshift from the black hole itself, can it add to the dispersion that you're seeing from the disparate average mapping?
So no, these are not at the stage or that would at least affect these kind of measurements. These are between, I don't know if I have size. There's maybe I do here. So looking at the G band, these are not so close enough to they might contribute, but they're not so close enough that would affect the G and I band as much. That being said, they might be important for the UV part, or even going like into higher energy, but not at the G and I.
So, but that's for SDSS-V, right? So I think for LSST, if you go to much higher redshift, would that actually be something to?
You mean from the black hole itself, not the
right.
cosmological
So I'm thinking about like inclination effects. So you get kind of the corona around the.
Yeah,
right.
yeah. I think for LSST this is going to be important because we're going to probe a different regime with LSST. So, but I think even going before that, we need to understand a lot diversity that is happening in the optical. But yeah, I think for LSST is going to be.
Thanks.
Okay, I think we better move on to keep on time. So let's thank the speaker again.
If it works,
I think it's now it's working. It was a bit of a, I mean, before I just.
yeah.
Okay, so we'll now hear from Minghao Yue, who will tell us about studies of close quasar pairs in the LSST era. Go ahead.
Hi everyone, I'm Minghao Yue and I'm a postdoc at MIT Kavli Institute. So today I'm very happy to get this chance to talk here, to share something about close quasar pairs, which I think are very interesting objects and will gain a lot of attention in the next few years. So I will talk about why we think these objects are very interesting and what we have learned from previous studies and how LSST will greatly improve our knowledge about close quasar pairs. So just as a brief introduction, close quasar pairs are some very rare products of galaxy mergers. Well, the point is, we all know that galaxy mergers can trigger luminous quasars. In some rare cases, both supermassive black holes in the progenitor galaxies can get ignited and shine as AGN in the galaxy merger. And in this case, we will see a pair of luminous quasars. So here I'm showing two famous examples of close quasar pairs where we can see the tidal tails of the merging host galaxies. Well, probably I should I should emphasize one thing is that not all galaxy mergers are capable of really generating a quasar pair. Indeed, what we have learned from hydrodynamical simulations is that most galaxy mergers can only generate a single quasar, which actually emerges in the so-called final coalesce stage of the galaxy merger. So that's why we usually see like single quasars that are hosted by single galaxies. So in other words, it's really a special population with some specific properties of galaxy mergers that can produce quasar pairs. And exactly what kind of galaxy merger can do this actually depends on your models of galaxy merger evolution and AGN triggering supermassive black hole growth, right? So that is why we can, in principle, use the statistics and properties of close quasar pairs to constrain the models of all these astrophysical processes. And in addition to the studies of supermassive black holes and galaxy mergers, actually quasar pairs are very useful probes, very useful tools in many other studies in extragalactic astronomy. First of all, quasars have been used to study the structures and properties of foreground intergalactic medium and circumgalactic medium using the absorption features in their spectrum. And in the case of close quasar pairs, we have two sight lines instead of one. So that means we can see the structures along the two sight lines and probe the small scale structure of, here's an example of studying the structure of intergalactic medium. And also we know that quasars tend to reside in massive halos. So that means if we have two quasars, that we are probably facing some overdensities. And the third example I want to talk about here is we can use quasar pairs to study the structures and kinematics of galaxy merger, the circumgalactic medium of galaxy mergers. Here, I'm talking about the quasar pair itself, because we have a pair of luminous quasars, the CGM is enlightened and will shine in resonance lemma alpha, from which we can detect, the CGM directly. And lastly, is very relevant to Maria's talk earlier this morning. These quasar pairs are actually, progenitors of the more compact, more small separation binary supermassive black holes, which will be the source of low frequency gravitational wave and can be detected by a pulsar timing array. And these are just the progenitors of those very exciting binary black holes. Okay, given all the studies that we can do, the exciting things, there are some weird alignment because it's converted from a keynote. But anyway, let's keep on. So this figure kind of shows roughly what's the current status of close quasar pair searches. So you can see that what we're talking about is some kiloparsec scale, which is one several arc seconds angular separation. And roughly the current status is we have found, or people have found, roughly 30 or now could be a bit more close quasar pairs, kiloparsec scale quasar pairs beyond redshift 1. And this sample is still pretty limited beyond redshift 3. Well, I would say this is actually a very nice sample, which contains many very interesting objects. But we also need to acknowledge that, 30 objects is pretty too few for an accurate statistical study. Although you can do some primary statistical analysis, but in order to get a smaller error bar, we do want a larger sample. And in addition to the small sample, there's actually another bit of problem, that is the luminosity mismatch between the observed sample and cosmological simulations. So there have been several cosmological simulations trying to predict this population of close quasar pairs. But the problem here is those simulations don't have enough volume to really produce like a large sample of luminous quasars. So usually what they can do is get a sample of less luminous AGNs, which usually have luminosities I mean, the like lower limit to be 10 to the 43 ergs per second. In comparison, the observed sample of quasar pairs have luminosities of 10 to the 45 ergs per second. So there's a luminosity mismatch, which means it's kind of hard really to use current sample to compare with cosmological simulation and to say something like we learned from this comparison that galaxy mergers and black holes should evolve this way. That is why we really want LSST, not only because LSST gives us a much larger sample, but also we go deeper. We can really probe those faint quasars or AGNs, let's say, that cosmological simulations can produce and do some meaningful comparisons. So in the rest of my talk, I'm gonna provide more information in this topic from basically two aspects. I will talk about like what's the statistics of close quasar pairs we learned from simulations and what does that imply on the survey outputs of LSST and other surveys. And in the second part, I will talk about like, there's this number of close quasar pairs, but how can we find them? Like, I will talk about all the efforts, what we have investigated based on current data sets, the survey strategy, and how we can apply what we have learned to LSST. Okay, let's start from the statistics of close quasar pairs. So as I said, there have been a number of cosmological simulations trying to predict at least the statistics of fainter AGNs. And well, these simulations are based on kind of different assumptions in how galaxy mergers evolve and how they produce AGN. So you can expect a little bit different results from these simulations. But we do find some general consensus in terms of like some of the most important statistics we care about. For example, here I'm showing the pair fraction of AGNs, which is defined as the number of close pairs within some distance divided by the total number of AGNs. So those simulations do find that this pair fraction is somewhere in between like 10 to the -3 to the 10 to the -2. And this fraction depends on luminosity of the AGNs and actually decreases with luminosity, which means if we talk about those faint AGNs, we are talking about a pair fraction of about 1%. And if we are talking about traditional luminous quasars, then the pair fraction is like 0.1% or even lower if we go into the brighter end. And we also see that the pair fraction have a subtle redshift evolution. It slowly increased towards high redshifts. And something that this figure doesn't show is that these simulations do suggest kind of a flat dn over dr, or like a flat distribution in pair separation. If we plug all this information to like some simple calculation, we can do roughly an estimate of like how many quasar pairs we can find in different surveys. Well, this is, I don't know what happened to my slides, but anyway, it's just a simple integration of the quasar luminosity function and multiplied by the pair fraction. So I just listed all the assumptions I made in the calculation here for your reference, but the concept is very straightforward. So I first checked what we should find in current sky surveys, where I'm assuming kind of a typical depth of I-band magnitude 21 limit magnitude. And I'm assuming like we are surveying over half of the sky. And what we find is based on these assumptions, we should find, roughly 1,000 quasar pairs. Well, just a reminder, we have already discovered like just general quasars, single quasars. We have like a sample of 1 million. So as I mentioned earlier, we expect a pair fraction of 10 to the -3. So this number kind of makes sense. But this also tells us like, since we know less than 100 of close quasar pairs, there are still plenty of room for us to explore. Like, I won't say it's like the survey strategy is wrong, but it's really, we just started to try to find these objects. And of course, there is still plenty of room for us to improve the survey strategy. But anyway, now I want to have a look at what LSST will tell us. So obviously LSST is much deeper. So we expect a much larger sample, and this my simple calculation suggests the number of pairs should be like several times 10 to the 4. And if you assume a steeper Feynman slope of your quasar luminosity function, this number could easily go beyond 10 to the 5. Well, that's just some uncertainties at the faint end of the quasar luminosity function. But this is anyway like several tens or around 100 times larger than what we expect for current surveys, and will definitely give us a much better statistics. And what's more important, as I mentioned earlier, this sample will really go deep enough to match the luminosity range that can produce by simulations and really enable some meaningful comparison between the observed statistics and what's suggested by cosmological simulations. All right, I think this is pretty exciting to me. It's pretty promising. And in the second part, I will move to the observational side. Like, we know there are so many quasar pairs waiting for us, but how should we find them? Well, I would say probably the most straightforward way to find these objects is to just start from the known quasar catalog and to see what quasars which sample of quasars have a close companion next to it. So this kind of features suggesting close companions can be either like you see a companion in the catalog, right? But it could also be, well, in sometimes the quasar pair is heavily blended in the images, and the survey catalog thinks there's only one object, but there are still some signs. For example, if you fit this blended object as a single PSF, you will see a very significant image fitting residual. So that's kind of two useful methods. We can find a possible companion next to a non-quasar or whatever objects. Here are two quasar pairs that from one of my recent paper, and this two corresponds to the close companion case and the large fitting residual case. But anyway, you can see it works. And then we can take follow-up imaging and spectroscopy to confirm that both of the components here are quasars and they are at the same redshift. In this way, we can identify the sample of close quasar pairs. I would say this method is kind of very traditional, and it's been applied ever since the age of SDSS. But it turns out this method is very efficient. I realized that either finding companions in the catalog or identifying image fitting residuals can actually probe an angular separation down to somewhere comparable or even a bit smaller than the size of the PSF. So, for example, this is legacy survey image with the PSF of like 1 arcsecond, and this method probes down to like 0.9 or even 0.8 something arcsecond separation. That's pretty surprising to me, but I can provide more information later. But the point is, this method is probably more useful than many people have thought about. But the limit is also pretty obvious. When we go to like even smaller angular separation, like much smaller than the PSF size, then we don't expect really we can see the signs from the images. So is there a way we can find those very small separation close quasar pairs? The answer is yes. There is a method recently developed by Professor Yueshen's group in UIUC, which is called Verstronomy, which uses the variability of quasars to find those very small separation quasar pairs. Is this actually a video? Would you mind? So I find this, yeah, just click it. So I find this very nice video from YouTube. Maybe I should. Yeah, it doesn't, it's fine. It doesn't work. No, but I'll just keep, I'll just talk. So the point is, quasars are variable, as you know. So here's a mock image of a quasar pair. So imagine that the two quasars have different light curves, and this system is blended in your survey image, and you measure the flux center of this system, and you will see the flux center of the system varies with time. So that is the idea of like this variability analysis. Still not working. Okay, it's fine.
Sorry, I cannot figure it out now.
Okay, never mind. So we can look at this figure anyway. This is from a simulation done by Huang et al. So if we assume some variability of the two quasars and measure the center of the system, we can see the center of the system vary with time. So in other words, if we have a sample of quasars and we measure like multi-epoch astrometry of these quasars, we'll have some signs that there is a close companion next to it. And actually, this method had led to successful discoveries of several very small separation quasar pairs. Again, that's studies led by Professor Yueshen's group. Well, speaking of astrometry, we know that currently probably the best data set is the Gaia survey. So this method have only been kind of applied to bright quasars in Gaia, and that's kind of the current limitation to this method. It has only been applied to like those bright quasar population, right? So just to wrap up a little, not there yet. So yeah, there are two slides talking about, I should mention that close quasar pairs are some natural products of lens quasar surveys. Well, the reason is straightforward. These are all doubly imaged lens quasars, and you check the image, they just look nearly identical to close quasar pairs. Actually, it can be very difficult for us to really tell the difference between the two populations just purely based on these images. So in order to really distinguish quasar pairs from doubly imaged lens quasars, we need either like deep imaging and high resolution imaging to detect the lensing galaxy, or like high signal noise spectroscopy to see the differences between the spectra of the two quasars. So I mean, that's kind of some expensive observations, but the good thing is survey for one kind of useful objects will naturally return the other kind of very useful objects. So we know that there will be intensive efforts to find lens quasars in LSST, and I do expect that this kind of service will also return a nice sample of close quasar pairs. Okay, so just to wrap up a little bit, I have talked about how we can find close quasar pairs based on purely their images, which is kind of the traditional method. We can find those objects, those quasar pairs that are at least marginally resolved in survey images, and this method has the potential to go to deeper and higher redshift. And I also talk about, okay, there's a typo I will just move to. I mean shallower here, but for variability analysis, based on like the variability in their position, and this method helps us to find those quasar pairs with very small separation and are not resolved in the survey images. But since we need like multi-epoch, very accurate astrometry, this method is kind of limited to, brighter population, or like it goes to shallower and thus a little bit lower redshift. And then I think about what we can do with LSST. LSST, as you know, has a pretty decent PSF size and it's very deep, and it's a multi-epoch survey machine, right? So that means we can kind of comfortably apply what we have learned from current survey methods, both imaging or like the variability in their astrometry. We can kind of comfortably apply both methods in LSST data set, which means we can cover, both the larger separation resolved and the smaller separation unresolved end of the quasar population. And eventually, I expect that with proper survey methods that we are still trying to work on, we'll build a sample of, statistical high completeness quasar pairs with bolometric luminosity somewhere beyond 10 to the 43 arcs per second, and the separation larger than 3 kiloparsec. So that will be a nice sample to compare with simulations and tell us like how these objects evolve. I think I still have a couple minutes. 2 minutes. Okay. I will quickly advertise my work a little bit, and actually that is, I think, a very exciting open question in the field of close quasar pairs. That is some surprising discoveries of high redshift quasar pairs. Since I'm running out of time, I'll go quick, and I'm highlighting this redshift 5.7 quasar pair, which has been observed by HSD and ALMA, and we can see the tidal tables of the merging host galaxies. The reason why it's surprising is kind of this quasar pair itself indicates a pair fraction that is 20 times ish larger than what I mentioned earlier in my talk, right? So it's kind of a discrepancy between what we expect and just indicated by this single quasar pair. So what does that mean? Does that mean like we miss tons of information about like high redshift galaxy mergers or high redshift quasar pairs? Where do this object come from? What's their environment? I don't know. I don't have answers to these questions yet. And I hope LSST will answer these questions by providing a larger sample of high redshift quasar pairs. I'll put my summary here, and I'm happy to take questions. Thank you for listening.
Questions? Go ahead.
So about the lens quasars, shouldn't you be able to easily separate them by their variability? Because they would be covariant, right? Or they would just
That's true. We expect lens quasars to have some kind of correlated variability in different images. But I think the point is you can say it's very likely to be a lens quasar if you see like two very similar light curves. But we cannot say 100% sure, especially if the variability is not so strong, right? There are the micro lensing event that will generate differences in the lensed images of lens quasars, and we cannot really rule out like the coincidence, like this period they just kind of look similar. But of course, if they look very different, then we can probably say, okay, this is a quasar pair. Yeah.
Go ahead. Yes.
Yeah. So any idea what fraction of quasar pairs you might be missing in an optical survey because one of the quasars is obscured, and particularly given their merging systems?
Yeah, that's a great question. So I don't have like an exact number in mind, but I think obscuration is definitely something that people should be very careful of. But I would prefer to take this question as, obviously obscure fraction is a very good indicator of, as I mentioned, galaxy merger evolution. So I would say like the number of these unobscure quasar pairs can be a very good indicator of like what's the obscure fraction when compared to the simulations. Well, I don't think there is a clear evidence that obscurations in these systems are very different from Euro quasars. So if I'm to guess, I would guess like somewhere a higher redshift is somewhere like 70%, lower redshift maybe 30%. But I don't know the exact answer, I would say.
Go ahead. Yes.
I've seen papers where they talk about dual AGN, right?
Yes.
So local equivalent of that, but at closer separation. Are the statistics similar?
Well, I think it should. I'm not sure if it's the way to say similar, but yeah, I think for lower redshift observations, people are now kind of seeing what we think they should be in cosmological simulations. Let me go back to that one. So I haven't really talked about like very low redshift because we do see like that's why I don't think I'm trying to find a good way to express this. So like first of all, at lower redshift, you see at least at redshift 0 to 1, there is a quick increase in pair fraction, for example. And this, at least at the lower, very low redshift, I think cosmological simulations are kind of giving us some relatively consistent results with observations. So in this sense, maybe we can say, okay, it makes sense. It's kind of consistent with what we expect at higher redshifts. But in terms of like the real numbers, like what's the pair fraction, then the pair fraction at local is kind of different at redshift 1. So to summarize, we are finding what we kind of expect from simulations, but we do expect that this pair fraction is very different at low redshift compared to like the local redshift compared to some high redshift. I hope that makes sense to you.
Okay, any final question? Okay, well, let's thank the speaker again. Now have coffee. Okay, so we are now going to hear from Tatavik Merkachan on the development of a Rubin LSST mock catalog using Cosmos.
Hello, everyone. I am a student in Universidad Diego Portales, Santiago, Chile. I'm going to present one of the works that I started to work recently. So it's going to be a presentation and a small discussion on what we're going to do. I'm working with Roberto Esteve, Matthew Temple, and Yara Mazzucchelli. Also, some collaborators outside of UTP. I will present them later. So I will start with presenting my goal. Also, we'll talk about the motivation and about some challenges, problems that we see right now. Of course, when we will start work more on details, I think we will have more challenges, but you're free to also give your ideas, your questions, because this is going to be more like a discussion presentation. So I will also discuss some solutions that we see, and then we will discuss my to-do list, like in details, what I'm going to do each step. And hopefully, because when I was training, actually, I was making this presentation shorter. So I decided to add some slides about my work that I am doing with Foremost Changes project. So what is the goal? The goal is to make an opportunity for AGN science collaboration to do photometric redshift estimation with LSST mock data. So as a first main step, we're going to make a training set data of LSST objects, let's say, and then we will try to estimate their photometric redshift. But we also want you to collaborate and to use your algorithm, test your algorithm on our mock catalog as well. What is the motivation? First of all, of course, the motivation comes from the ability of Rubin providing wide, deep data. The second main motivation that is performing spectroscopic follow-up is expensive. And because we're going to have hopefully a lot of targets, it's better to have more effective and optimal way of estimating photometric redshift. And of course, if it's going to be an archived data, it's always better to have something as a program that is running and giving you the output of the redshift, rather than just spectroscopic observation. What are the challenges? One main challenge is, of course, this identification of AGN, because AGN comes with its flavors. There's a lot of different types of it, like obscured, low luminosity, high luminosity, and we need really good templates to describe different types. So be sure that we're not missing any type. The second challenge is variability. We discussed about this a lot yesterday, especially. So because AGN is variable, this will make an uncertainty in our data. So we need also to include that afterwards. Another problem is that sometimes it's really hard to distinguish optical emission from AGN because it can be dominated from the host galaxy. So this is another challenge that we see. And another problem that actually also was described in the paper of one of our collaborators, Salvato 2009, is that when we compare the photometric redshift accuracy of normal galaxies and AGNs, we see that the accuracy for normal galaxies is better than for AGNs. because of the acidity that we see, the characteristic of emission lines. It's getting worse when you are dealing with AGN. And we should also take that into account. And another thing is the operation differences that is LSST providing, depth drilling fields, and also tenure stack, single exposure. We need to make different mock catalogs for each of them. So be sure that we're not missing anything. As the solution, as I already mentioned, is collecting good templates for AGN, Galaxy, stars. Also, we need a really deep, good sample of AGN that will be our fundament for making the training set. Next, we will use acidity feeding, but we also really want to add some empirical methods with it. So we can run them simultaneously and also compare their efficiencies. Add a model of variability, and as I also mentioned, we're going to make two different mock catalogs, including uncertainties and depth limits. Actually, this is partially true because we are going to make three of them. I will show you why we decided that. So with templates, we decided to use Salvado's templates because she's providing about 30 AGN templates of type 1, type 2 objects. And in her paper, in her studies, she also showed a really accurate estimation of redshifts, of photometric redshifts. And she was able also to detect some high redshift objects higher than 4.5. So another template of galaxies and stars that we will use is Silbert and Boleta's templates. For the deep sample, we are going to use Cosmos survey because it has a lot of passbands, and also the broad, medium, and narrow photometric bands are allowing to make a precise estimation of photometric redshift. And we will also use in some terms the Cosmos 2020, Cosmos 15. As the acidic feeding model, we will use LEFAR, and we really want to use Rail for making the catalog. I haven't really studied it in details. I have it already installed in my computer, but as far as I see, it can also help you to degrade the catalog. So we'll need to have more faint objects at higher redshift. So I really hope that Rail can be helpful. Going to the to-do list. So first initial step, this is for all studies, doesn't depend on what you do. You need to collect all important information, meaning for my project, I need to have papers that were doing the same or really close work before. I will need to have templates and filters. So this is what the papers that we're relying on. But here I would like to have your input as well. So if you know any good studies, or if you're doing something relevant and you think that could be helpful, we would really appreciate your opinion. LSST, we're going to use filters. First of all, at the very beginning, we're using Subaru HST filters to reproduce some of the results. And then because Cosmos has a lot of passbands, we will use all possible passbands to make the mock catalog as close to real AGN as possible. And the mock catalog will be based on LSST filters as well. Reproducing results, we are going to use Marchesi sample of Cosmos Marchesi sample. And in his paper and also the paper of Salvato, there are some results already done with that survey and with particular templates. So we want to reproduce them to be sure that we're on the same page and the program is running correctly for us. And after that, being sure that everything is correct, we can start simulating LSST, getting the fluxes and creating mock catalog for single exposure, 10-year stack, and DDF. Why we're going to have these three subsets? Because if we look at the distribution of the HSC I-band and HSC R-band, we see that going to the fainter magnitudes, we're having less objects. So this is one of our challenges, to make mock catalog with faint sources as well. So that is why we really need to separate each of them. Another step is, because we really want to run the SCD feeding program with some empirical method, we want to research on similar studies and empirical algorithms. And actually the talks yesterday of Ivano, Paula, and Gordon were super helpful. But if you have any suggestions, again, we are open. And afterwards, yes, we will start to test the algorithms. So we will need to do SCD feeding for different objects, different subtypes of AGN, and to use empirical method. After this all, we will include the variability. So just to be sure that we are on the same page, I want to emphasize one thing, that these whole steps are actually three different products. The first product is going to be the catalog. So we, as the first main goal, we really want to provide a catalog, a mock catalog of AGN. And as the second product, we will make we will test algorithm and see which algorithm is better, comparable with other than studies before. And the third project and the third product will be the output of our whole analysis with variability included. And we will analyze photometric redshift estimation accuracy, compare methods. Also, why not? We really hope to use the first year Rubin data, if will be possible that time, and determine maybe additional external data. What is the current status right now? I am working on reproducing results. I collected all necessary information for the very beginning, but again, if you have any suggestions, we're more than welcome. You're more than welcome. And right now I'm trying to reproduce a galaxy mass distribution, which is described in Marquesi's sample, in Marquesi's paper, just to be sure that we're getting close results as he did before, the same results that he had. So we'll be sure we can start simulating LSST. Now, I think because I have plenty of time, I can discuss about my work that I was doing, and I am still doing that with almost. This is the team of this project. So if you have any questions, please, you can contact us remotely, or you can see us during breaks. So the other project that I am working as well is selection of high redshift quasars for FORMAS. So we use SCD model feeding to find high redshift quasars higher than 5.5. And this is going to be a catalog of quasar candidates that will be hopefully observed by FORMAS. What are the methods that I used? Because we're dealing with a huge data, it's about 450 million objects. We need to select 16,000 quasars. So first of all, just to not run all SCD on 450 million objects, we decided to do some cleaning from contaminants, which is the first initial step. And then we converted magnitudes to the fluxes to start running SCD. And with the SED calculations, based on SED calculations, we started to do prioritization. But we also, during this whole work, we decided also to add some color cut, just to see how many objects we can cut with that selection. So these are the selection conditions that was implemented before running the SED. One is the extended class C from Delve, which shows that if it's equal to 3, then we are dealing with not AGN, not quasar, so we can exclude them. And it's an extended source. If the ratio of proper motion is more than 2, then it means the object is moving, so we don't need it. We will cut it as well. If we have a G magnitude from Delve, we also cut that one, and we do the color difference of Weiss filters, selecting only the ones that are not in this range. What template we used for the SED? So we used 2 groups of quasar templates, one provided from Selsing and another provided from Temple 2021, which is list of templates based on emission line mode, EBV modes, and redshift. And we used ground dwarf template, which is based on surface temperature and gravitational potential. This is one of the tests that we did as a result. We run SED fitting on the same object, but from different catalogs. One is a catalog from Banados of high redshift quasars, and another is the Stripe 82. And we wanted to see if we will have the same results with the same object, but with different catalogs. And as you can see here, the fit looks the same. And because it's quasar, the object is quasar, it's more or less a good result, showing that the best fit is with the quasar template. As I mentioned, during the work, we decided also to add some color selection. And here you can see I minus Z with R minus I plots show this was done to understand what is the criterion, what is the range of R minus Z and I minus Z and R minus I threshold in a particular exact redshift range. And with this visualization and with this study, we found out our best selection criterion to select quasars. And as a result, from the very beginning, we have 450 million objects. When we started to do the cut before SED running, we end up with 25 million objects. And because we needed to also, for I minus Z and R minus I, we needed to have the exact range of redshift, we ended up with 12 million from 25 and 70 million, I'm sorry, from 25 and 808,000. This is the range of exact redshifts that the cut was used for. And after cutting them, we had about 12.5 million objects, which is the half of the amount of objects that we had when we were running SED. Afterwards, we can use the main results of SED, meaning the statistical parameters. And the statistical parameters that we were using is Bayesian information criterion and F-test value. Using this criterion, this condition, and at the end, we decided to add one condition, which is still we are figuring this out if we need this one or not. But we really want, because we have 10 data points, we really want to have objects with enough data points so that they will be, we will be sure that their SCD fitting, their results will be accurate. And this is the prioritization that was done. So we used, for the prioritization, we used chi-square minimum with the ratio of chi-square minimum divided to Brown-Dwarf chi-square minimum. And we decided to have this particular range of them. And this is the magnitude prioritization, because it's also really important to have a good magnitude range so it will be observable. Yeah, and at the end, we'll also try to see if the objects will match with cosmos stars and galaxies. And as you can see in R-I band, we have less objects, although some of them are overlapping, but I think that will be always an issue. When you're observing, you can always see some brown dwarfs. So I think this is all that I prepared for you. I am more than happy to hear your questions.
We have some questions. Go ahead, Mark.
Yeah, so I like the SED fitting approach. I think, yeah, we heard a lot about being able to label AGN, but one thing that's very useful, of course, particularly for the lower luminosity things, as Vicky was saying yesterday, you can fit the host and the AGN components in an SED fitting. That would be nice. I was wondering if you thought about that. And also, I was sort of inspired by Nevin's talk with the API for the photometric redshifts. Could you do an API for the SEDs as well? That'd be an interest. SED fitting as well. Something to think about.
I don't know. This can be maybe a really good way. I'm not sure about the first part of your suggestion. Yes, actually, the sample of Marquesi that we're going to use, one of the reasons behind that is that it has type 1 and type 2 AGNs. It has a wide range of low redshift AGNs. And what is good that it also includes mid and low range of luminosities from 10 to 42, 43 erg per second. So this can be a partial maybe an answer to your question if we're including any labels. The sample also provides you labels, and the templates are white. Also, Mara used to provide hybrid templates of her own template list, which was the best fit. So she also has her recommendations. We can try to test them as well.
Gordon, go ahead.
So, I mean, tend to do photo either as template fitting or basically machine learning. I think it's obvious that we're going to have to do both. I mean, the main thing that comes to mind is the differential chromatic refraction, which has to be machine learning, can't be template fitting.
Why not? Couldn't you add it as posterior?
Right. So I mean, that would be the logic. So the question to you is essentially, are you doing anything to try to plan for that, or is there something that we in the science collaboration can do, or maybe in the project could do to start giving people that are interested in PhotoZ information on DCR? I mean, nobody is doing it right now because no one has come out and said, this is the information that you're going to get. Like, so what can I give you? Because I mean, the obvious thing to do would be have it be a prior, right, to it, like template thing.
Yeah, so because this is, it's a future work, but the first priority is making a catalog. I would say maybe we can, it's good to have in mind what else empirical approach we can have, or perhaps you can do some part of it. But for now, let's discuss it. But keep in mind that the first step obviously is to make the catalog and have it, and then we can talk about how to.
I mean, I guess it's an existing method, right? So it's not really a future step, right? In the sense.
Yeah,
that-
sure.
But I think in the context, right, of what Tetevik is doing, so at the third part of the project, right, is actually simulating variability, and then sort of adding a DCR should be
At that point.
right? And then however you design your method to work with that sort of mock catalog, the DCR information would be available. Right, I think that's what makes most sense in terms of this project.
Any other questions? Yes, go ahead.
Yeah, these are very nice results. So I'm interested in I mean, there's some pre-selection cuts in, I think both you're selecting only point sources and you're requiring no detection of the proper motion. Since LSST is going to, finger ends, and I don't know how much do you worry about, it's not like the current status thing, but how much do you worry about like the host galaxy contamination, and sometimes cutting on the proper motion will rule out some very interesting objects. If you heard about that, there are some Gaia-related studies talking about like strange behavior quasars in terms of, promotional parallax, which has non-detections on these quantities. I just wonder if you have any thoughts and comments on this, like those selection.
This is a really important question. So my part of this project is what is the difference is, first of all, we are giving one part of high redshift quasars, and there will be another also selection, not based on SCD. So 25 million hours will be used for foremost, which the half will be for SCD modeling and the half empirical way. So for now, I'd say about the proper motion cut and G delta cut, we came to that because of this really simple results. When we try to see from the sample of high redshift quasars, how many of them are having G delta went up with sources which has 99, which means that they weren't detected. And the same was with the proper motion. So it is coming from the background of some already known quasars list. But with LSST, of course, one of the things that we might be concerned, maybe to have a really good sample first to see if it is including all the host galaxy dominated AGN, and then during the testing, maybe to have anything that could fit with it. But I mean, the galaxy template should be fitted like that type of object.
Yeah, I think that's a good strategy. Thank you.
Thank you.
Okay. So I think we better move along to stay on track. So thank the speaker again. Okay, so now we're going to hear from Ake Vitanen. I didn't murder your name. Okay, and we'll hear about realistic empirical LSST photometric AGN galaxy catalog. Go ahead.
Okay, thank you. So my name is Ake. I started recently working at INAF Roma as a postdoc, and I'm going to present you a status report on the catalog that we're trying to generate for the purpose of to be used by you, basically. And this is the list of collaborators that we have, both in Roma and both in Napoli. And okay, so in order to motivate my talk, I'm going to steal these sentences directly from the AGN LSST Science Collaboration Roadmap. So if you look at the major tasks that are written there, and you look at places 1 and 2, basically both of these tasks deal with simulating realistic data. And this is, of course, timely now that we don't have the data. And what we're trying to do is we're trying to address these tasks that have been listed. And what we have currently available within the collaboration is the Cosmo DC2 is kind of like the flagship simulation, the state of art. and it covers 440 square degrees below redshift 3 and brighter than R band 28. And for galaxies, it has everything that you ever wished for. And the LSST, the simulated sky survey, is a 300 square degree version of this simulation. And what we have available in the data preview is the truth catalogs. So the original catalog was fed into the image simulations. And then there are the LSST like exposures, so the Galax single visit exposures and the full 10-year co-added images, and also the detection, so the extracted information from the images. But as it stands, we don't have AGN in the data preview. And what the enough in-kind contribution, so what part of the enough in-kind contribution is trying to do is trying to answer this question. So what we are trying to do is we are trying to simulate a truth catalog containing galaxies, AGNs, and stars. And this we try to feed into an image simulation pipeline, which is already existing within the LSST. And then also this should be extracted to provide a photometric AGN catalog with variability, magnitudes, errors, so on and so forth. And what we're trying to do will be complementary to the what is available in the data preview 0. So we are not going to try to increase the fidelity in terms of galaxies. We're just trying to add in the AGN. Okay. And how do we do it? We have an empirical approach. So kind of like a definition for an empirical approach would be to simulate the galaxy and AGN population according to known observables such as number counts, luminosity or mass functions. And this will be done in a statistical sense. And compared to more expensive simulations as semi-analytical models or hydrodynamical simulations, we have a couple of advantages. So first of all, we are reproducing the observables by design. We are highly extensible. So if you have another observed relation that you want to input in the simulation, it's relatively straightforward to do so. And last of all, it's computationally inexpensive. So if you want to change something in the simulation, it's not let's say not a matter of running too much expensive simulations. And this is a highly technical cartoon of the approach that we have. So we start by simulating the quiescent and star-forming galaxy population by using a stellar mass function, and then we are populating the galaxies with AGN according to X-ray and optical recipes. And as a post-processing into the catalog, we are then adding stars. The current catalog that we have simulated is 10 square degrees large. We are going up to redshift 5.5 and R band brighter than 30, stellar masses about 10 to 8, and it is about 5.7 million galaxies that we have. And this is the full pipeline. It is quite a mouthful. I will try to guide you through it. So for the galaxies, we start with the input stellar mass function, and then we are adding stars into the catalog, and we're adding AGN into the catalog, and hopefully at the end of the day, we will end up with the output photometric catalog. And most of the work that we have done is in the AGN part of this image, and basically the right-hand side of the image. We have implemented the image simulation, we have implemented the source extractor routine, but we are in the process of migrating towards the LSST pipelines, what is already available. So we start with the galaxies. So we are using EGG, which is an empirical galaxy generator. It takes as an input a stellar mass function for the quiescent and star-forming galaxies, and then it uses recipes to populate these galaxies with realistic stellar populations, dust, star-forming range, morphologies, you name it. And the output of this process is going to be an SCD for every galaxy, distribution in redshift, the positions are a deck, and also the egg recipes, they have been calibrated to reproduce the observed galaxy number counts. And also there is an algorithm for the two-point correlation function of the galaxies, and that is also calibrated in terms of redshift and stellar mass. Then we populate the galaxies with X-ray AGN with accretion rates. So we are using a bivariate distribution that is derived from external cosmos data. So for this sample of X-ray AGN, we have the host galaxy stellar masses, and also we have the accretion rates. And I will talk about the specific accretion rate, which is a proxy for the Eddington rate, which is defined as the ratio between the X-ray luminosity and the host galaxy stellar mass. And what the bivariate distribution is, it is a joint number density of the AGN host galaxy stellar mass and the accretion rate. So basically, it gives you the probability of a given galaxy with a stellar mass hosting an accretion event as described by the specific accretion rate. And just to demonstrate it a little bit, here is the two-dimensional distribution. On the bottom left, you have a higher number density of AGN at lower stellar masses, lower accretion rates, and on the top right, it's a lower number density overall. And if you integrate the distribution in terms of specific accretion rates, you are going to end up with the AGN host galaxy stellar mass function. Instead, if you integrate it with respect to the stellar masses, you can you get the accretion rate distribution for a given stellar mass. And this gives you the probability of a stellar mass hosting an accretion event with a certain accretion event. And you can also integrate it in terms of certain X-ray luminosity, and you can also retrieve the X-ray luminosity function just from the bivariate distribution alone. So this is showing as an example the redshift evolution of the bivariate distribution and the AGN host galaxy stellar mass function. And on the left, I'm showing the galaxy stellar mass function. On the middle panel, I'm showing the AGN host galaxy stellar mass function as derived from bivariate distribution. And then on the right, I'm showing the AGN duty cycle. So if you compare these two together, you take the ratio of the two, you can estimate the AGN duty cycle, both as a function of stellar mass and redshift. Okay, so we do this exercise populating galaxies with X-ray AGN, and then we compare against the observables. So on the left, I'm showing you the log n log s of both the XM Cosmos and the more deep Chandra deep field south, 7 megasecond. And on the red, this is the output of the process of using the bivariate distribution. And we are doing quite a good job in reproducing the observed log n log s of X-ray AGN, and also towards lower fluxes as well. On the if you then look at the redshift distribution of the sources, so here is the X-ray luminosity function from 0 to all the way to up to 6, and this is the data is from Miyagi 2015. And here as well, we are reproducing the trends in the X-ray luminosity function quite well. And if you look at the very bottom of the plot, you can see that in the bivariate distribution, there is a large redshift evolution, which is basically that the last redshift bin is large, and in the bivariate distribution, there is a redshift evolution from the low redshift bin to the high. We move on to populating the X-ray AGN with optical AGN. So for this, we are using SVD templates, and the idea is to add on top of the galaxies an optical AGN SVD template. And we are using basically the same approach as in Temple 2021. So we are simulating the AGN SCD from the Lyman limit all the way to 3 microns. And this consists of 3 components. So there is the accretion disk responsible for the optical and the UV. There is a torus responsible for hot just black body component, and then we are on emission lines on top of that. And the SCD template fitting is based on SDSS, UKIS, and WISE data. So quasar colors on a wide range of redshift and also absolute magnitudes. And the idea is that from this sample, we are selecting a pure AGN sample, which doesn't suffer from host galaxy contamination. And then we are refitting the model in order to derive posterior distribution for the AGN parameters. And on the bottom, I'm showing the type 1 posterior SCD as a result of this exercise. And as a final note, so we are moving the SCDs up and down. So the normalization of the SCD is then derived from the X-ray using a correlation for the X-ray luminosity 2500 angstrom luminosity. To each AGN, we are then adding a type. So each AGN can be a type 1 or type 2 based on a X-ray luminosity dependent fraction as derived from the X-ray cosmos data. So on the top left, this is the fraction. On the top right corner, you have the unobscured AGN, and top bottom left corner, that's the obscured AGN. And there is this evolution with respect to X-ray luminosity. And we are using these offset fractions to assign each AGN in the simulation a type. And then we draw an EP minus V based on an empirical distribution derived from maximum cosmos AGN. And if somebody has any suggestions on if there is a better way to do it, we are happy to hear it. But after drawing the EB minus V, we achieved the redundant SCDs of the AGN. So here is a couple of examples showing the effect of the EB minus V on the SCD templates. And here is then the composite SCD. So on the red, you can see the Galaxy SCD, and then on top we have the AGN SCD, and which is shown on blue. And this is just one single random AGN from the simulation selected. And at the moment, we are simulating all of the LSST bands and also the Euclid niche bands. Adding any other bands into the simulation is a straightforward process as long as we are dealing in the correct wavelengths. And then if we look at the some validation of this exercise optical AGN, so here I'm putting the quasar B band number counts, the points I'm taking from the LSST science book, and then the lines corresponds to either the galaxy number counts or the AGN number counts. And you can see that at fainter magnitudes, as we heard yesterday, the number counts are completely dominated by the galaxy number counts. But comparing our AGN B band number counts to observed ones, we are in the correct ballpark in terms of the observed data. And then if you go towards brighter magnitudes, the AGN population starts to dominate. And at the moment, since we are simulating 10 square degrees, we are missing the most brightest objects. Here is the redshift distribution of the sources, so the G-band quasar luminosity function. And here we are capturing the redshift evolution adequately well. We have some redshift beams that suffer from, let's say, a little bit of an under prediction in terms of the number counts. And then if you go towards the highest redshift beams, you can also see the effect of the limited volume that we have. On top of all of this, we are adding variability. So we have a recipe for adding light curves to each of the AGN. For this, we have this empirical relation based on 5100 luminosity, and it is calibrated for a wide range of bolometric luminosities. And the algorithm is the damped random walk. Here are some examples on the right of a several random AGN picked up from the simulation with their light curves plotted. And each of the light curves are normalized in order to give you the mean magnitude over the 10-year range. We have some future improvements in mind already for the variability. So at the moment, we are simulating each band to vary the same way. And at the moment, we are simulating type 1 and type 2 AGN to vary the same way. And both of these can be improved as long as we have the observational data. Okay, the stars. So I wrote there that we are going to generate the stars, but actually somebody did it already for us. So we are using the publicly available LSST SIM. LSST SIM catalog, which is a complete sample of Milky Way imaginary clouds, stars, and binaries, down to the LSST limiting magnitudes. And we are just into the combined catalog, we are just including directly whatever they have in the database. Sorry, how much time I have?
You have about 4 minutes.
Okay. Yes. So now we move into we take a deep breath. We have complete
7 minutes. I'm sorry. 'Cause I-
7.
Yes.
Okay. So now we take a deep breath. We have completed the, let's say, the truth catalog, and this can be then fed into the image simulation pipeline, and the images images can be then fed to the photometric extraction pipeline. We rolled our own in terms of the image simulation and the source extraction, but the idea is to move on to the LSST pipelines in order to capture all the file data that they have already included there. So this is the demo regime of the talk. Okay, so for simulating images, we're using SkyMaker, which is simulating galaxies with double Census profiles for the disk and the bulge. AGN and stars are point-like, and we are being rather modest. We are simulating one LSST detector with these characteristics, and the simulated images at the moment include a single visit and then a 10-year coad exposures. And this is the number of visits I'm using for reference, and this is the field of view that we are simulating compared to the full catalog that we have. And this is a single 30-second exposure in all of the LSST bands. And alone, I don't think it is too interesting to watch, but it is if you compare it against the coated images, you can appreciate the depth increased and the number of sources and the decrease in the noise. It's not updating at too fast of a speed. But okay, this is the 10-year coated image. If I zoom in a little bit, you can see the shapes. So this is in the catalog that we are inputting. It's a combination of galaxies, AGN, and stars. So galaxies are usually not point-like, but the AGN and stars are. Here is an image of all the input catalog sources plotted, and you can see, for example, on the top right, a lot of faint sources that are not detected, but that are not basically showing up in the image at all. The stars are point-like. The AGN that we have in the simulations are either point-like or extended, depending on whether or not the host galaxy dominates. Here is an image of the variability. So this is a very fake cadence of visiting the same AGN once a year. So you can see the light curve that we input in the brightness of this particular AGN. And then I just have a few more images about the source extraction. So we just run source extractor on the simulated images, and then with the input catalog 29,000 sources, we are matching the source extractor sources within all the. Whoops, sorry. Okay, we are matching to the input catalog. We are removing all the spurious matches of 1 arcsecond, and this is the number of sources that we end up detected in any of the bands or all of the bands. And I'm not going to comment on this too much, just to say that we are almost capturing the limiting magnitude for the LSST 10-year, and this is the extracted, the true magnitude plotted against the extracted magnitude. And you can see that the scatter at the moment is not too large. The same thing we did with colors. And then this is plotting the half-life radius against the magnitude, and you can see that the QSO-like AGN, so the point-like AGN and the stars occupy this region of the plot. The idea is that the mock catalog is very near completion, and the improvements that I discussed with you about are to be implemented as future work and also based on your suggestions. And the first version of the catalog, the images and the photometric catalog, we plan to release at the end of September. And in the long run, we would like to have a database solution which makes it all, let's say, efficiently accessible and LSST-like. And if you want to use anything that I have shown here today, just get in touch, please. Open issues, future work, the laundry list that we have in mind. So we are thinking about working on the AGN clustering. So at the moment, we are using the same two-point correlation function we got from egg. This can be improved upon based on the observed quasar X-ray AGN clustering. For the hosts, at the moment, we are not separating between quasars and the star forming. We have the same bivariate distribution for all of the hosts. and that can be recalibrated, that can be input into the simulation. For the variability, as I mentioned, band-to-band variability, type 1, type 2 AGN differences, and then for the image and photometry, we plan to just use whatever is already available within the LSST. Any additional Galaxy AGN features to be added, if there are suggestions, we are happy to hear about them. And then in general, if there are any requests for the enough in-kind contribution from the AGN science collaboration, also get in touch, and the deadline is beginning of October. And my last slide, I thank you for your attention and take any questions.
Any questions?
So is the goal to like release these light curves as a part of the DP0 to be accessible for everybody?
So it depends on, so the light curves can be completely deterministic. So it depends on what we want to store and what we want to simulate, like on an on-demand basis. Because if we want to store everything, if we do half a sky, all the AGN, everything, all the light curves, I don't think that's very useful. But if we give you the algorithm that you just input these properties into the code and give you the light curve, it's entirely possible.
Yeah, well, one thing that we are interested in is have some sort of simulated light curves to run our reverberation mapping pipeline and see, like get a sense of what we're going to get. So that's, I'm mainly interested in the light curves.
Yes. So we know everything what is happening with the light curves. At the moment, we're not storing them. We just when you point the telescope, we ask what is the current phase of the light curve, and that's it.
Other questions? Go ahead.
Something that really interests me is like really heavily obscured AGN, complex AGN that can be hiding, you know, in and potentially spectral signatures can affect things that we do later. Do you have any plans of increasing the obscuration and seeing how that might affect things, or how that would play in with the variability that you test later?
Okay, so we have two types of obscuration, because we have the classification we have is for both X-ray and optical. And then when at the moment with the bivariate distribution we're using, it doesn't include comptontic AGN at all. So the distribution stops at NH 10 to the 24. And I don't know whether or not it will have an effect. And also with respect to variability, I only can guess what kind of recipes we can implement differently for type 1, type 2 AGN. But definitely this is something that we can input in the simulation. You can produce a forecast based on that and test the effect. But it's not something that we currently have in the simulation.
Yeah, so this is really interesting work. So I was wondering though, it seems like even everything you've done, trying to separate between type 1 and type 2 is not very meaningful, right? Because in the end, that's a very observational category based on optical spectra. So it might be better to think about it in terms of just amount of obscuration towards the accretion list based on the host, right? So you can also include stuff from the host and the torus. But I don't know if you've thought more about how would you optimize that part instead of just creating the separation before you start the simulation.
So the way the simulation is currently built, so you have the type 1, type 2 classification decides the amount of reddening you have on the SED. And this is of course band dependent and also redshift dependent, but whether or not it's gonna affect the magnitudes, which are kind of like the final product that we have. And at the moment, I would say that it is relevant, because if you go to certain bands or if you go to certain redshifts, it matters how much obscuration you have. And then for the number counts, for the quasar luminosity function, it also matters, because the bright end is dictated by the number of type 1 AGN you have. So that the bright end of the quasar luminosity function can also be calibrated, or that the EB minus V distribution that we have can a little bit be calibrated by the right end of the quasar monster function.
There's an online question related with
Oh,
the
go ahead,
previous
go ahead, yes.
question. I'm just reading it. Could you please repeat how the broad emission lines are added, and are these also from templates and then taken into account when appointing type 1 and type 2 AGN?
Yes, so the order of operation is that first we assign every AGN type 1 or type 2 in the optical. And then we have two different templates for, so type 1 AGN has the broad lines and type 2 AGN do not have the broad lines. And the broad lines, as far as I know, they are also set by the refitting that we do for the bright AGN sample. So does that answer the question?
I hope so.
Okay.
Final question, go ahead.
Yeah. Going back to the type 2s, what we often see in the spectra is that there's more like a scattered or leaking UV component that comes through in addition to the narrow lines. I wonder if you can model that somehow, because that would be a very interesting way possibly to identify type 2s.
Yeah, as I mentioned, anything that is observable can be put in there. So if there's a relation that gives you this in a statistical sense, it's straightforward to put it in. One thing that is maybe relevant for LSST is how well are we going to pick up type 2 AGN in general. So how well are you going to select those objects, either based on variability or the photometry. So if we are not able to select them at all, then whether or not we have in the simulations doesn't matter too much.
Okay, I think we better move on. Let's thank the speaker again.
Will you introduce?
I'll do it. Okay, so we will now hear from Satish Shiba. Yeah. And we'll hear about selection of LSST AGN candidates through photometric redshift estimation. Go ahead.
Okay, thanks, Neil. So I'll introduce myself. I'm Sharat Satish Shiba. I'm a PhD student at Institute of the Astrophysics of Andres Bello in Chile. And I'm working with Timo Ancoita from the same institute and Roberto Asaf from Diego Portales. And today I'll be speaking about the project which I have done for selecting LSST AGN candidates through photometric redshift estimation. And I would also like to thank Kata for funding the project and my travel. And giving a quick introduction. So as we know, LSST will be producing millions of AGNs. In a very large sample, we estimate from 20 to 80 million at least. And the 6 filters of LSST will also give us information covering a very wide wavelength range from near ultraviolet to near infrared. And with its high cadence, we are also expecting to get a time variable behavior, so we can really study variability as well. So on the right, we have the quasar surveys which have been done until now. I mean, the quasars detected, for example. And this is something which we expect to detect with LSST, so that we can go much deeper than Sloan or other surveys. So, I mean, we will be getting more information, which is really helpful for studying AGNs more statistically. But the problem is selecting our candidates just by using photometric data sets. It's an active problem. So many of us are working on selection. And we would love to have a spectroscopic follow-up for, studying these things more, but it is time consuming, of course, expensive. So our motivation for doing this project is to select LSST AGN candidates by estimating the photometric redshift. So we can use these candidates for different purposes, either foremost follow-up or also high cadence using smaller telescopes. So coming to the data, we were in need of very large data for training our algorithm. And so we used the LSST AGN Science Collaboration Data Challenge from Gordon, which is basically the SDSS type 82 and XMM data. And it has about more than 400,000 sources arranged in different flags, such as quasars, high redshift quasars, AGNs, galaxies, and stars. So one important point here is that there is an additional Y filter, which is simulated from the other SDSS filters. So we use that. And to compare and to improve our selection, we have used multi-wavelength data from UKIDS and WISE. And over the right, you can see the web page of the data challenge. It is public and it is accessible to the community. So coming to the methods, we use low resolution spectral energy spectral templates from Asaf et al. And here you can see a sample fitting for a stereotype quasar. The advantage of using this template is that the minimum bands necessary for the algorithm to run is 4. But we, of course, are at more data points to improve our selection. So in general, we chose the model by determining the chi-square. So we chose the one with the best chi-square. So a bit about the fitting parameters. So each source is fitted using either stellar and galaxy and a galaxy plus AGN templates. So the galaxy templates are considered as it is being created by assuming a linear combination of different stellar populations, like old continuous or starburst stellar populations. And the AGN template is basically the same galaxy templates with an additional AGN component of varying reddening and absorption by the intergalactic medium. And coming to the stellar templates, we use 4 types of stellar templates that like main sequence, subgiant stars, giant stars, brown stars with different amplitudes. And over the right, you can see the templates from the paper. And so after the fitting, the advantage of the algorithm or how the algorithm works is that it assigns a probability for the best fit for the source. As I mentioned, that we are doing this by estimating the redshift. However, the redshift that were estimated by our fitting is not very well constrained, but the probability for the best model is something that we use to make the selection. Perhaps a better estimation of the photometric redshift can also happen. So now we have the sample of 400,000 sources. We need to divide them into stars, galaxies, and AGN. So initially we use chi-square to remove the stars from our sample. So from the fitting, all the sources that has a chi-square lesser for the stars are stars, and we remove the other stuff as AGN or galaxies. So now that the stars are removed, we need to separate out the AGN from the galaxies. We used Bayesian information criterion for that because, as I mentioned, the AGN templates are basically galaxy templates with an additional parameters. So to avoid overfitting, we used a Bayesian technique. So it punishes the algorithm to avoid overfitting. Furthermore, and as an additional step, we did a selection using F-test, which is another statistical method of selecting where it assigns the probability for the best model. Also, we did this on 2 separate samples. It's not a separate sample, it's basically a control sample taken from the main sample where it has detections in all the multi-bands. This is to compare how much the selection improves by adding multiple bands. So initially, we have done our fitting with just LSST bands. So this is at least 5 bands. And over here, you can see the distribution of the chi-square. So we consider that all the sources, these are stars and these are AGN or galaxies. So now that the stars are removed, we had to go back to the Bayesian distribution to select our AGN from the galaxies. So from this distribution, we selected the AGN such that the AGN population basically flips the galaxy total population. So in this particular plot, we use a Bayesian information of the big index of 8 to say that all the sources that have a big index greater than 8 are AGN, and the sources which have a big index lesser than 8 are galaxies. So just by using, and over there, it's the same source with just LSST bands, and you can see the chi-square and the big index of that particular source. And by applying it to 400,000 sources, we got these results. So just with LSST bands, we could get a positiveness of 61%. So in this table, the data challenge classifies the sources into 5 flags, but our algorithm selects it as only AGN, galaxy, or stars. I mean, the real positive ones, I mean, these columns say that what percentage of the sources that we select as AGN are the real AGN. And the completeness accounts for what percentage of these real AGNs are in the total AGN sample. So in practically, we have just used the quasars, but you can also see that there are high redshift quasars and AGN, which we should use for estimating the positiveness and the completeness. But the number of quasars are significantly larger than the other classes. So we just use the quasars for estimating our positiveness, I mean the purity and the completeness. Now that we added multiple bands, let's see how it improved with WISE. So here we added LSST and WISE, and we did the similar thing for selecting out stars and also AGN. And over there, you can see the same AGN with LSST and WISE bands, and the blue data point over there is an upper limit of WISE. And you can see the chi-square and the big value of this particular source by adding LSST and WISE. And coming to the results, we see improvements. The WISE has really helped in selecting out the AGNs. And also it has improved the selection of galaxies and also stars. So we decided that it is really good to add WISE. Then we see how it improved with UKITs. So we added a mid-infrared data into that and followed the same method of estimating the selection. So over there, it's the same source with all the bands. We have LSST, UKITs, and WISE bands. And we use the Bayesian criterion for selecting AGN and the normal chi-square selection for stars. More improvements. But here, in order to compare how much each band is improving, we had to make a control sample, because from the total sample, there are sources which is, the number of sources that is being detected in just by LSST and by UKIT is not the same. So we cannot compare the percentage of the purity and the completeness. And so we made a control sample by choosing the sources that has detections in at least 12 bands. So 12 bands as in, we expect to have 13 bands by all the 6 LSST bands, 3 from UKIT and the 4 from WISE. So we did the same thing with the control sample. And by adding WISE, you can see that the purity of our selection of AGN increased from 49% to 80% with a completeness increase of about 20%. And also the similar percentage for, not the similar percentage, similar improvements for the selection of galaxies. It improved from 68% to 82%. And the stars, we improved the completeness with similar purity. So we added Ys here, and then we added check with just UKIDs. So we removed the Ys and we added the LSST and UKIDs to see how much it improves. And the AGN selection has not improved, but the galaxy selection has improved more than the Ys. So, and of course, the stellar selection has also improved. So we understood that, okay, the UKIDs is helping much for selecting out the galaxies and the stars, but not really helping for selecting the AGNs. But when comparing to the whole sample, removing out the galaxies and the stars, of course, help in classifying the AGN. And the best selection will be all the combination of the three. So if I compare all the three here, just by adding LSST plus UKIDs, LSST plus Ys, and all the three, we have the best selection of 83% purity with 88% completeness by adding all the three filters, sorry, all the three bands. And adding UKIDs is good for selecting AGN, but Ys is always better. Coming to the stars and the galaxies, UKIDs showed better results than adding Ys. And so, as I mentioned, we have also did the F-test as an additional step to select AGNs out of the galaxies. So, where it assigns the probability for the best fit, and you can see the probability distribution of from the F-test for this 100,000 sources from the control sample that we made. And we found that we got better selection by using F-test than using BIG. So if I go back to AGNs, you can see that we were able to select AGNs with 83% purity and 88% completeness, but with F-test, we got 85% purity with 91% completeness. Similar to the case of galaxies as well. It's not a very significant change, but F-test can be used as a better selection over BIG in this case. So the algorithm works by estimating the photometric redshifts. But as I mentioned, the estimated photometric redshift is not very well constrained, but it's improving. You can see the improvement of the photometric redshift by adding multiple bands. So from LSST to all the three filters, you can see that we are slowly improving the redshift estimation. And if you compare the Ys and the UKIDs, you don't really see a big drastic change. But when you add both of them, you can see that the estimation of redshifts for galaxies has improved because we don't have many galaxies more than at a redshift greater than 2. Also, the selection, also the estimation of redshift for AGN has also improved. But the stellar redshift estimation in the data sample, in the data challenge, all the stars have a redshift 0, but we got some redshift here and there. So it's okay. So as a summary, we have the sample and we used chi-square to remove out the stars from the AGN and galaxies. Then we used the BIG or the F-test to remove the galaxies and the AGN. So the advantage here is that we can really select AGNs by increasing the BIG index, for example. So when we select an AGN, when we get a select a source with higher BIG index, they are AGN for sure. So we can, this algorithm allows us to tweak between the purity and the completeness of our sample. And the additional step which can be done for this project is to add a time dimension into this by taking multi-epoch data and trying to fit it using same algorithm and to see how it improves. And thank you for it.
Since Niel is out for a second, I'm gonna take your question from the audience. Any question? Yeah, please.
When you add the WISE data, are you requiring all 4 bands detection? Or just some?
Not really. So the WISE data we took directly from the data set of WISE. So for the sources which don't have all the 4 bands, they had upper limits. So we used upper limits as well. And that really helped, I guess.
Any other question? Yeah.
So I just want to say I'm glad that people are still making use of the data challenge, data set. But I mean, just a comment, like maybe a challenge to everybody in the room, right? I mean, I would say if we can't do 95% completeness, 95% efficiency, 95% photometric redshift accuracy to the SDSS depth, we failed, right? But if that's all we're getting on the data challenge data, then that's not a really good indication of what we're going to get on the real data, because those data are biased in some way, right? And so I think what that says is, we need to do a better job of working together, trying to figure out how to use all of the data, because 95% is really, really hard, right? But I mean, basically, if you can't do that well, then you need a spectrum.
Yeah.
Right. And we're gonna have 100 million quasars. We've got to be able to do science without taking spectra, right? I mean, so thanks, and I think there's more for us to talk about in a discussion after lunch, based on all the talks this morning so far. So.
Gordon, I'm going to push back on you.
Yeah.
Because I think you're comparing apples and oranges. Right, because basically you're using all of the AGN or all of the quasars known in SDSS stripe 82, but those were not selected optically. Right, so you have to go back to the days where you selected optical quasars and then found 95% of them or whatever.
Oh no, my point is that you're right. Like, we need to be using all of the data, right? The infrared, the X-ray,
But I mean, to say that
everything.
why aren't we finding 95% of them? It's because there's X-ray selection that went in later in Sloan. There's a mid-infrared selection that went in later in Sloan, right? I mean, so there's known confirmed quasars that were not selected with optical data. And so it's not surprising that we can't find them.
Yeah, no, I agree, right? But I mean, that's my point. I'm not saying why are we not selecting them. I understand why we're not selecting them. I'm saying that should be our goal, right?
Right, but I think it may not be a feasible goal, right?
If we have multiple data types, if we have colors, variability, multi-wavelength data, astrometry, proper motion, I think we have to achieve that goal.
At the depth that is there, but I'm not sure we have that over a large field.
Yeah, we don't.
Yeah. And so just taking the optical and the variability in the DCR, like, I'm not sure we can, make a selection of AGN that's as comprehensive even as what you have for the data challenge. Right. That's kind of the point, is to see how well you can do, but it's not clear you can get them all.
Yeah, no, I agree. I'm not criticizing this work. I'm saying let's take that as a
challenge.
Yeah, something to try to achieve, right?
Yeah.
Yeah, Mark.
Euclid data will be out, I guess, in the next few years. So that's going to be very deep in the near infrared. That might be interesting.
That could be helping for selecting out the galaxies. But what we found that we don't have too many UKITS data points for our sources. So most of the sources don't have UKITs. So
Euclid, are they?
Yeah, I mean, by getting Euclid, we let's see how much it improves by adding Euclid data.
It should be a lot deeper than
I hope
Euclid's,
that if
yeah.
we get for more sample,
Yeah.
it can really improve our galaxy selection.
So someday we might also have NeoCam, the infrared.
Yeah.
Yeah.
More question? Can I have a quick question? Can you comment on, especially for the near infrared UKIDs, which is available, but how useful in terms of the make it quantitative assessment to find out a high Z AGN with and without the NRAO?
Well, I mean,
photometry. I mean, my question is LSST alone, how much will it be useful without, let's say we don't have the UKIDS data, other deeps, near infrared survey.
Okay.
Is it still useful, or do you think it's really necessary we have that data to find out the high Z AGN?
I mean, as of now, I cannot comment completely on the redshift of the AGN, but I mean, if we are able to detect the high G AGN, but if we go back to our table, maybe here. So real one. So if you don't have a just LSST bands, we don't really have a very good purity on the high redshift AGNs. As you can see that our purity is really low.
Okay.
With just LSST. But by adding WISE, it can help a bit. But the problem is that the photometric redshift that we estimate are not very well constrained here.
Okay.
But in general, the selection, if you're saying about the selection of AGN, even if there is not a deep survey available for the near infrared, it's possible to select AGN with WISE. WISE is helping much more than the near infrared.
No, just wanted to, so one thing is that this specific process, how it's been done, it's not really tailored to high redshift because we're just running out of bands to actually do a proper modeling. So I think you really have to go to kind of like the processes that Tevik was talking about to try to identify those high redshift. Whereas we really didn't worry at all here because there's so few that yeah, we just decided to not add.
Thank you. If there is no other question, then let's thank our speaker again. Yeah, then now we have a special talk before we all out for a next lunch. I'm going to introduce a speaker who is the Catherine Brockis sitting in the back of the auditorium. She is the manager of the North American Alma Science Center, which supports this workshop. So she's going to tell us about the activities of the NASC in general and gives you some overview. So I'm going to share the screen with your slide. Yeah, this one. This is one, yeah, the one that I got from this one. Yeah. Fine.
Great. So first of all, I hope you're enjoying the workshop so far, and thank you to Ilsang and the organizers for giving me this slot before lunch to talk with you, and I will try to keep you too long. So as also mentioned, I'm Catherine Vlahakis, I'm the North American ARC manager. And so what I wanted to just spend a few minutes telling you about is who we are as a NASC, what we do, what services we offer. Some of you in the room already know that already, so apologies for that. So in the NASC, in essence, we work to provide the North American scientific community with access to the ALMA telescope. And we're operated by NRAO here in Charlottesville, but also in collaboration with Canada's National Research Council, Hertzberg Astronomy and Astrophysics Research Centre, and also the National Science Council of Taiwan. And so what we support the use of ALMA by astronomers in both North America and Taiwan, and also the support for research and development of future ALMA upgrades. Here in the NESC, we have the North American ARC, which I manage, and we focus on providing core support to ALMA users, and each partner region has an ARC, so one also in Europe and another one in East Asia. And if you want to find out more about what we do, I put 2 links at the bottom here. I'm not going to read through all of the words on all of these slides, but I can share them afterwards, and they will have a bunch of links with hopefully useful information. So in terms of core services that we provide, it's things like preparation of the ALMA scheduling blocks with content scientist support, development of tools and algorithms, data reduction guides, the data reduction itself and the delivery of the quality assured data products through the ALMA pipeline or either manually. We also deliver calibrated measurement sets through a service called the Labor Saving Added Value Automation Service, or LAVA for short. And then for interferometric observations, we have an ALMA data mining toolkit called ADMIT, products that give users a quick look of the data, including things like well-known chemical species and moment maps. So in North America, both of those will come along with the delivery of your other QA2 quality assured products. We also have ALMA help desk support that we manage here in North America, and knowledge base articles, both of which can give answers to hopefully all and every question you have about ALMA. I just wanted to emphasize that no question is too small. If there's anything you want to ask about ALMA, whether it's your project or any other questions, preparing proposals, whatever it is, reach out to us on the help desk. We're here to help with whatever you need. And other things we do, ALMA documentation for each cycle. We maintain and operate a copy of the ALMA archive and a computing cluster for data processing. We also contribute to extending and expanding ALMA's capabilities in conjunction with the ALMA Observatory. And we also have the North American ALMA Development Program, which aims at keeping ALMA at the forefront of scientific discovery. And you may have heard of the wideband sensitivity upgrade, which is the next big development that's coming. And that will include a new wideband correlator and an upgraded band 6 receiver on the part of North America. And there's other elements to that as well. So other services, calibrated data on demand. So NRAO operates a science-ready data product service, SRDP. And so calibrated measurement sets from previous cycles can be obtained via the service. So if you're an archive user and you want to get access to that, or if it's from an earlier cycle than cycle 5, you can just contact the help desk and we can provide you with the calibrated measurement set. And there's also, as part of SRDP, there's a service called AUDI, the ALMA user-defined imaging service, that allows the ability to request re-imaging of data products. So if you don't want to do the imaging yourself, you can use the AUDI service. And I've added the link there to SRDP if you want to find out more. And also just a reminder about raw data access. Sometimes it's not obvious that we provide that. If you have PI data and you want access to the raw data, you can request that through the ALMA Science portal as soon as your data has passed the QA0 stage of quality assurance. That does start the proprietary clock, but the service is available if you need it. Face-to-face visitor programs. So we love to have you all coming to visit here in person or virtually. A typical in-person face-to-face visit lasts about a week. It can be longer, it can be shorter, and we can do it virtually on Zoom if that works better. And we also offer NAS chats, which are 1 or 2 hours. If you have a question that is too long to discuss on the help desk and you want to jump on Zoom with a member of the staff, we can facilitate that as well. If you are coming in person, we can accommodate up to 3 researchers per team visit. You can visit here in Charlottesville, or you can visit Victoria in British Columbia. And we can support you for ALMA data reduction, whether you're a PI or an archival researcher, proposal preparation, if you just want to work on your papers, or if you have a science collaborator here for a shorter visit or a longer visit like a sabbatical, all of those can be accessible. And while you're here, you get to work with our data analyst team and our scientific staff. And of course, access to an office, high-speed computing, and so on. For North American PIs, as well as archival research, we also offer some funding available. So for 1 or 2 people per visit, if you don't have your own travel support, we can support that as well. And so if you want to come visit us, you can just apply through the ALMA help desk. Computing support, I already mentioned, but even if you don't want to come visit us, but you need help with your ALMA data in terms of computing support, you can get access to the NESC's high-speed computing system, and you can request that also on the ALMA help desk. Particularly wanted to point out support for large programs. If you are planning on submitting a large program or you're already a PI, I do encourage you to utilize the face-to-face visitor program and reach out to us in advance of your proposal preparation, so we can better support you. If you want to come for a data reduction visit for a larger team, we can support a large program for up to 8 people, as opposed to 3 or so people for a regular program. Again, the computing support, data storage, solutions for sharing data, let us know what you need and we'll try and figure it out for you. There's also some financial and logistical support for large programs if you want to organize a workshop on data processing, analysis, preparing the papers. Contact me and we can try and get that set up for you. That was what I wanted to say about large programs. I mentioned support for conferences and workshops outside of large programs. If you're interested in organizing a workshop like this one, there is a call for proposals that's actually opened yesterday. The deadline for that is going to be September 6th, and that will be for meetings that will take place in the next fiscal year, so starting from October through next September, for US-based meetings. You can request between $10,000 and $25,000 to support the meeting. We ask that the meeting support encourages the participation of students, postdocs, early career researchers. And if you have any questions about that, you can contact us here at this email address. If you just want to organize a smaller meeting that isn't requesting much funding, you can reach out to us at any time, and we'll try to support you with that pending available funds. And one of the last couple of things I wanted to mention is the ALMA Ambassador Program and community training events. So many of you have probably heard of the ALMA Ambassador Program. This is early career researchers that come here to NRAO and get trained up in proposal preparation techniques and data processing techniques, and then go out into the community and host their own workshops to pass that knowledge on to the community. If you're interested in becoming an ALMA ambassador, there's an annual deadline, and you can get up to $10,000 of research or travel grant, and then we support you logistically in setting up your workshops and running them at your host institution. And student observing support, there are several things offered by the NASC. So there's a student observing support program. The most recent one was for ALMA archival research. That deadline just closed. If you're interested on that, that can provide a good amount of funding for a student to work on archival projects. And then summer student program, REBA pre-doctoral program, and a new postbac program. So I encourage you to go look at these web pages if you're interested in, if you are a student or you have a student and you're interested in support. And last but not least, I wanted to mention that NRAO does have page charge support for US-based investigators. And so if you would like to request support with your publication that uses an NRAO facility, you can check out the information on the NRAO webpage. So I'll just end there with a couple of pictures of what we do. I hope that gives you a flavor, and I don't want to keep you from lunch, but I'm happy to answer questions. And I know I rushed through that, but I'll share the slide with you afterwards. Happy to talk to you over lunch. Yeah, I hope we'll see some of you visiting in future. Thank you very much.
Yeah, feel free to ask questions. Yeah.
So PIs in Chile can also choose the North American arc for the data. Are any, none, or all of these services available to PIs in Chile that choose the North American arc?
The short answer is yes. For example, we've had ALMA ambassadors from Chile that hosted the workshops in Chile. So the last few rounds, we've had ALMA ambassadors from Chile that hosted the workshops there.
So things like the page charges, would people be able to apply for that as well, or?
For the page charges, that's an NRAO rule, so that has to be at a US-based institution. Okay. If somebody is really stuck, you can always contact us and we can see what we can do. But in terms of the formal NRAO support, that's for researchers at US-based institutions.
Thank you.
But what about the joint Chilean-US paper?
Right. So
it's per researcher.
Right.
So the US-based folks on the paper can apply for their share of funding. If there are one or two people, if it's a majority North American based paper, there are one or two people that are not and really struggling with funding, just reach out to us and we'll see what we can do, not through a formal funding process.
Thank you.
Other question? No question from online? Yeah, just when LSST start operating, if you find interesting sources, please consider ALMA. It will be an excellent follow-up facility for your science. I guess we are done, right? Then we go out for lunch.
Yeah, I think lunch was already set up outside, so make your way outside slowly when you're ready.
Yeah, thank you.
Thank you very much.
We thought we would start off talking a little bit about the project posting tool that Roberto and Christopher Carroll have put together for us. I'm going to go through my project and as an example, which I just posted. I think it actually links really well some of the talks from this morning, and will basically suggest to people that, hey, this is a good way for this group and this group to talk to each other and work on common goals. So if you're on the Slack, I have pinned the live document that Roberto posted yesterday. This is how you make yourself an account on the Open Project site. You don't have to do that right now. But if either right now or as I'm talking, you realize that is something that is useful to do, go ahead and do that. And Chris is going to monitor and basically approve things as we go. But I know people don't necessarily want another account unless they really want another account. So let me try to convince you that you actually do want another account. So let's go ahead and pull up the. Okay, so that's the document that you're going to go through, but then let's pull up the Open Project. Okay, so SDSS, for example, and the Dark Energy Science Collaboration all have project posting facilities and publications committees and stuff like that, right? And so we would like to set up the same. The problem is we don't have any money, and what Desk does actually costs a fair bit of money. And so we have come up with a way to post projects, and really basically after this meeting, I think we're going to stand up the publications committee which is needed to help basically coordinate projects and approve them for posting and things like that. So this is the open project and so you can see we have populated a number of projects to sort of get things started. 2 of those are already marked as finished. This is a project that's basically announcing the paper by the Serbian AGN group. So it's a paper that is now posted. And then Georgia Savic, also from the Serbian group, has written a paper summarizing the data challenge. He was the one that won first prize for his submissions. And so there's a paper there. So you could look at those as examples of things. There's not really anything there, but it's just sort of like, backward history of some of these things. What I want to do is take you through this project that I posted. So let's go ahead and first one. Yeah, first. No, sorry. Just go back. This simulated one. This one. Yeah. Okay. So for a long time, I've been saying that we don't really need to wait for data to write a couple of papers. And I think one of those papers is the luminosity function paper. There's no reason we can't write a luminosity function paper basically right now. And so the idea would essentially be that if the universe looks like we think it looks like, based on this model, some bolometric luminosity function, and if the LSST data looked like we think it's going to look like, then here are the error bars on the luminosity function at, given magnitude and redshift. It was a lot like what Akka was showing, earlier, right? And so I posted this back in May when we were starting to talk about projects to get started. And so I wanted to sort of, scroll down and walk you through what the idea was. Basically what I want to emphasize is that I am not staking claim to this. I am just saying, I think this is something that we all need to do together. Here's my ideas for what needs to happen. I don't actually intend to do any of it other than maybe, get person A and B and C to talk to each other. But, I think it's a worthwhile thing to do, right? So this is basically what I just said. And then, so I broke it down into, 4 things that need to be done, right? So first, simulate I-band magnitudes, including the host galaxy. So do this in 2 ways. One, based on draws from a luminosity function. So, this is Phil Hopkins students' update of the bolometric luminosity function. So Roberto has that coded up, right? I don't remember which luminosity function you're using or anybody else is using, but something of that sort, right? So draws from the luminosity function, 10 million, 30 million quasars or something like that, type 1 objects, basically all the ones that we expect to find just with LSST data. Like that. And then, grid and redshift and magnitude. So you need something drawn from the luminosity function to generate a simulated luminosity function, obviously, or error bars in luminosity function. But you need grids in redshift and magnitude to eventually do the selection function for quasars when we try to extract quasars from other things. And so, like I said, right, so who could do that? Well, Chris could be running Roberto's code. There's any number of people in this room online that aren't, here that could do that. One thing that I would emphasize is that I don't think that anybody needs to think like, oh, this person's already doing this, I shouldn't do it. There's no reason that multiple people shouldn't do this. It worked really well in SDSS. No people or 2 people are going to do the same thing in the same way. It's good to compare results. it may be that we should be generating a black hole mass function or a Eddington ratio distribution function instead of a luminosity function or in addition to, and so on. So there's different ways to approach that. So that's one thing that needs to be done. Second thing is that is just giving us, I-band magnitudes for everything. We want to then simulate UGR, UGR, not I've already produced that, ZY, but then, JHK, Spitzer channel 1, channel 2, so on. And again, so, Matthew has a nice AGN SED template, right? So we can do that. Shankar is doing that as well. JT Schindler, Tanima, and Anna. This overlaps with plans for using Cosmos data for PhotoZ at UDP, right? So again, any number of people could do that, and as we saw this morning, basically, essentially already are doing that. And then, with that, we can simulate time domain data in each of those band passes. That's not hard to do. It's hard to maybe like store all this stuff. But, what we really, I think, would like to do is basically take your simulated objects, randomly assign them RA and DEC, and then actually lay them down on the baseline 3 simulation for LSST, and that's where you get your cadence from. Okay, so this is a real LSST cadence, not like we're going to do 200 observations in this band over 2 years. Like, no, on August 31st, 2025, this object was observed in the Z band, right? Kind of thing. Okay, and again, lots of people can do that. And then basically, like I said at the beginning, take that, generate a luminosity function, publish a paper as a AGN science collaboration, where the idea would be, full members would be able to say, hey, I contributed to this, I want to be co-authors. Core members, would automatically basically be able to put their name on anything that is a AGN science collaboration publication and so on. Okay, so so the idea is that you would post projects like this. The publication committee would review them, and well, you're going to submit correct me if I'm wrong, you're going to submit something to a Google form that basically says, here's my project, right? Right. Publication committee is going to then review that and make sure that it actually is a collaborative project that you're posting, and you're not just staking claim for something that is not actually going to be possible to do for 5 years. And then post that, and then you're going to be able to sort of go into this and request membership and so on, right? And so this is just an example that's sort of meant to be like an overarching kind of project. And I would encourage people in the room that feel like, oh, I've already done A or B or C in this. Like, we'll sign up as a member, and then we'll start using this as a way to coordinate efforts. All right, so I'll shut up, and then.
Also, if you click on work packages, you'll see, this is just some text of the project description, but work packages is where the tracking actually happens, and you'll see how things can be broken down in phases with different tasks. Once you reach certain milestones, there's others, and you can kind of lay things out in this way. So like Gordon was saying, if three people want to do the same thing but with different techniques, like you could have the 3 different tasks that are broken down the same thing. 3 different people are simulated in the data set, whatever, and then you can have these things individual, and then it's all grouped under one phase or one project.
Yeah, and that way you know who's doing what, where that data is, who to talk to if you want to try to get access to. You would know, like, oh, they've only simulated 10,000 objects and we want to do 10 million objects. Well, they didn't have the compute power to do that, so hey, I'm going to reach out to them and say, come use my computing cluster, or whatever. So
I believe there's also the ability within each to like kind of jot down some notes. So maybe if you're 3 people are doing the same thing, different, you can go in and check and see, oh, someone got stuck here. I actually think hey, I'm stuck is like one of the status that you can, or like on hold or something like that. So that, that's a different way that it can be used. We haven't put that part into, practice yet, just open it up.
Yeah, so you can create a forum as well associated to your project, where you can post things like questions, or have the rest of the people participating in your project sort of have this asynchronic discussions. Although of course Slack is also a very good place to.
Yeah, and I think things like that are things we will have to work out.
Yeah.
Right. I mean, there'll be some growing pains there. Like, oh, are we communicating within the open project for this? Or are we communicating in Slack or what have you? Right.
I mean, there's also one way that you can deal with that immediately is like, if you're on this project leader creates a private channel and adds all the members to it, and then you can actually have full-on discussions, in the channel for the project / paper or whatever it's called, one option.
And one more thing. If you go back, so if you click on work packages, there's a little, that works too. You can see there's the wiki there. So you can actually go ahead and create a wiki for your project as well, if you want to be posting things. Ideally, hopefully you will just be posting links, because it's not that the space is very constrained in the server, but currently it's constrained for uploading to the cloud for backups. So currently we're just using a free Google account, so there's a 15 gigabyte limit. But if you just post links to, for example, Google Documents or things you put in a Google Drive, and this is a really good repository for all of that.
Question.
Have you think on which way will be used to advise new projects to the collaboration? I mean, will we receive an email with new projects?
Yeah, so I was just gonna comment on that or ask that, right? So there's this news thing, right? So I guess the question, so there's 3 different types of communication that you would want to have happen, right? And I don't know the answer to this, right? So one is just let everybody in the AGN science collaboration know that there's something new, a proposed project or an actual project. Yeah.
And that comes, there's a document of when you get your account. These are the settings to set up. Sorry, that sounded terrible. This is how you set up your account so that you get a notification every time there's a new project.
Okay, so that allows anybody that has an open project account to know when there's a new project.
Which is why you need one. You should sign up.
But we should also make sure, and maybe what'll happen, I guess what would happen is you're going to submit to the publication committee, and once the committee has approved that project for posting here, they would also get posted on the main mailing list, and so that everybody knows, because we can't just have the 5 people that are on open project know about all the new projects, right?
Yeah, I think this is something that is working very well in SDSS, because every time that there is a new project, we get an email, and so you'll read it and you say, okay, I'm interested, so I'm going to join something like that.
So yeah, so that is a limitation of the platform, that you can't send an email to all the members, except through this news item. Okay. So if you put the news item, then everybody with this account gets an email. Yeah, I mean. But then we should also have a Slack publications channel where just to alert everybody a new project has been created in case new members haven't yet signed up or. Okay,
yeah. So we need some way to let everybody that is basically an approved associate member know about projects, and then there's ways presumably to communicate everybody that has an open project account, and then ways to communicate with just the people that have signed up for that. So all 3 of those need to be able to happen.
There's one more thing we could consider for the future as well. So right now it's set up that you go and request your account, but admins can also create accounts without you requesting them. So we set it this way because there's so many people already that we didn't really want to create an account for everybody. But you could imagine once sort of we go, everybody has an account, then a new member gets immediately an account created here as well.
Yeah, Matthew.
I was just wondering if you want to wait and notify all of the science collaboration, would it be possible to create an account, an open project associated with the science collaboration mailing list as the email account?
Sorry, could you?
Could you create an open project account
Okay.
With the email address OSST-AGN@list or whatever it is.
Yeah.
Or is that a particular security flaw that seems to be exposed?
No, I think it's just a spam. There's a spam potential.
It may quarantine all such emails.
Yeah.
And that just makes work for Neil, but maybe maybe we can set some setting that says don't quarantine your email from whatever. Yeah.
Open our publications committee might have that many emails to send. So.
Yeah.
How would you, the publication committee, consider if someone propose a project, not just for the AGN science collaboration, but reach out the other LSST community like the Galaxy forums and the group and want to work with them and posted a project with their name associated with it? Would it be treated as the normal, the same AGN project, or would you consider this as something different?
That's a good question, right? I think that's something that we would have to discuss, and that's the reason why we need to stand up the publications committee, right? Okay, so the immediate thing that comes to mind is, okay, if you're a core member and you get immediate, publication rights to an AGN science collaboration publication, but it's actually a joint AGN science collaboration Galaxies publication, then the Galaxies group might not agree that to adhere to our publication policy. Right, so we would have to. But yeah, I presume and hope that will happen. I mean, if we're not cross collaborating with Galaxies and TBS and Strong Wednesday, then that's a problem.
But there's some of the argument there has always been those people can always just join the AGN science collaboration anyway.
Right. And I think some of that has happened, but I mean, in principle, the people that do AGNs in the Galaxy science collaboration don't, as a rule, communicate with us or vice versa.
Yeah, I've tried.
Right. So,
yeah. In terms of just open and the instance of open projects, there are different roles, and so you could potentially, if someone from TDS wanted to work with a project here, we could potentially give them the role of non-member, and then they could only see the project that they're on, stuff like that. Like,
I don't know if that's feasible. Well, we have to investigate, because I think the issues we put it read protected. So we set it up that you need an account to see the projects, right? So they're not just displayed to the whole world.
So I meant that if you are not going to join the AGN science collaboration, but you want to work on a project, you're collaborating with someone.
Okay, so kind of like
you make an account, but then you get the role of non-member, and you don't see all the other projects, just the one that you would collaborate on.
Right.
Could be.
Yeah, I think that's feasible, but.
Other questions? Do you want to go through the document that sets up an account for people?
Sure, if you want, we can go quickly over through it. I think I've seen a lot of people have been signing up, so that's a good sign.
Yeah. Yeah.
Right. So this is still an incomplete guide. It's still missing a few things.
Right. So do you want to?
Yeah. So that might be easier. So basically, if you go to the website, right, this is what you'll find. So just go there to create a new account. And so eventually that notifies currently Chris and me that you want an account, and we activate the account for you. There's some basic requirements on your password that need to be met before you can create an account, but that's still the thing. And then this is the landing page. You see, so if you go, so this now, I don't think that's super important. So this basically explains how to set up such that you receive emails whenever there's news items created, which is how projects should be announced. Yeah, we keep going down. Right, so basically you set it, and you also want to click when memberships sorry, unclick when memberships are added, because otherwise you'll get a notification every time there's a new member. You probably don't want to know that exactly. Right, you want to make your email visible. So this is optional, but I think this is useful for project leaders to communicate with the rest of the people in their projects. And so then there's this submit a new project request. And then what happens, right, is what I was saying, the publications committee reviews it. And then there's a template project that we just copy and give the person that made the submission the project admin role. So they can go into that project and start editing everything, but it's not public. It is that they just prepare everything to get it ready, and then make it public, make a news item, and inform their collaboration that this new project exists. And on there, so if you go down a little bit, you can also add the members to your project. So then if you create sort of forums, boards, or anything, people actually know that will receive emails that a new forum post was created, for example.
There is a pre-existing list, or should we explicitly find out the members?
You should explicitly find out, right, who, because when you submit the project, you probably already have people you're collaborating with.
Yeah.
And then there also in the description, you can say like, oh, this is open for collaboration, right? So anybody who's interested in this, let us know and we're happy to collaborate. Or no, this is not really open, so open to collaboration, but you know, we still want to know what people think about this. So that's kind of up to every group specifically. And then this just goes how you announce it and create the news item to announce your project. And then at some point, I will add something about the work packages and how to create work packages, but it's actually very intuitive. If you just start playing with the system, it's very simple to create work packages. You can then display them as a Gantt chart if you want. I think that's basically, those are basically all the steps for this. I don't know if there's any questions or does it seem reasonable? Go ahead, Chris.
Did we publish this in the Slack channel or?
Yeah, so if you go to Gordon published the link, put it as
so this, right?
Right, exactly. So it's pinned to the channel of the meeting. But I don't know if there's any sort of thing that you see that is clearly missing. That I don't know if we can do it, but at least we can check if it's doable.
I mean, just an example, initially people might create a lot of projects, but actually some people lose their momentum or for some other reason, I can imagine there's going to be some abandoned project. So do we need to have some sort of a plan to clean those, the project out? So I basically don't mind to leave the project as original, submitted, or?
Well, if you go back
to the platform,
does have like a
go
not
to
on track or the platform itself.
Okay.
And then go to.
Right. So you can
3 bars at the top left. Do.
No, actually, it's not here. So if you go here, go to there. Yeah, those little boxes.
Oh yeah, no, right there.
This one. No, that's okay. That's what. So here you can actually put up. I think there's a category, or otherwise we can create it as just abandoned project.
Yeah.
So just people know that you're not working on it anymore. You're not really planning on. Also, the publications committee could have some time that says, okay, there's really haven't been any updates in a couple of years, right? We could just go ahead and mark it as
well, and then presumably they're also the gatekeeper for you can't post like a project Right? That's just sticking clear.
Can you refresh the screen?
Can you refresh?
Did you abandon?
There you go. Your project has been discontinued.
Can we have maybe another tag saying if the project requires access to data rights? So people with no data rights can collaborate on alerts, for instance, or things.
I think we should be able to put something here. So if you click on any of the projects, right, so it's one of the questions in here is, or maybe it's not here. But one of the standard things that we want people to fill out here is whether you have project rights.
It does say that somewhere. I don't remember where. But.
And then when you display all of the users for the project, then there's actually a category that is ticked or not that says project rights. So you know whether you're accepting people that actually meet the conditions or not of your project. But I think just for sheer necessity, that's going to have to be the responsibility of the PI of the project, rather than of the collaboration, to make sure that all of the people they're collaborating with actually meet the conditions. Maybe they should make it easy at least to identify if you cannot.
Yeah, just to say, I can easily imagine a project where a small part of it requires data rights, but the project as a whole would value contributions from people without data rights, right? And so I'm not sure you want to close off your entire project just because, you know, one little paragraph of it needs data.
Right, I think that's what kind of Franz was mentioning yesterday, that there's ways to navigate this so that you can keep other people involved in the project. You just need to make sure that you never share data products directly with them.
And maybe a work package would have data rights, and that would lead to a different paper or something.
Yeah, and you can also, if you have an overarching project, you could also just link them, and they get linked as sub projects of a general project, in case that will be useful for anybody.
Just one more side question. I mean, if the platforms turns out to be very useful, and that could place a lot of people actually involved in, how about creating not the project, but proposal writing stuff? Will that be also useful? I mean, if some people, in the LSST operating has some good idea, develop a proposal or something like that, and put some ideas and asking for collaboration, some external expertise to add to the proposal to submit it to Telescope, be a useful format to somebody actually use it.
I think that's a good idea. So if you go back to my, let's go to the project list. So if we go here, right? So one of the things you could imagine creating is like, so the way I see this, there's two things missing. So one, you could add extra categories. Let's say, oh, this is a proposal. This is an idea, right? It's not a project. But then also it would be great that if the publications committee decided a way to assign IDs, right? So this is project 001, right? And then you can actually filter things. And if you just want to see kind of like open proposals, you filter out and you just see the open proposal. And you see the finished projects if you want to know whatever is published. You can also track the use of funds. We didn't enable that by default because we have no funds. It's a collaboration, but if anybody's interested in that, you can also activate it in your project as well.
And it's by member. I saw that I was worth $0.
Yes. Yeah, and every project takes $0 to complete.
Right.
That's the.
Okay, so an underlying thing with all of this that keeps coming back is the publications committee. So that maybe brings up a couple of things, right? So as the charter is, if I remember it correctly, I guess I was the one that wrote it, but I just stole it from TBS, so I don't have it memorized. To be on the publications committee, you would need to be a full member. Right now, we've got what, a dozen full members or something like that, and they are more than populating the committees that they need to be on. So, so one of the things that we do need to do is sort of, encourage some people to apply for full membership. For example, if you've hosted a meeting or developed a new project platform, maybe the leadership will reach out to you and say, hey, why don't you submit an application, leaders of in-kind contributions, or something of that sort, right?
I very much agree with that. But let me just add, though, of course, don't think that the people who are the leader, the full members are omniscient. If you have done a very important contribution to the science collaboration that we might not know about, you don't have to wait for us to somehow come and tap you on the shoulder. You can apply to become a full member at any time following the normal application process.
Yeah. I think there's there's two things here, right? Don't wait for us. But one of the reasons why we had this new structure is because the AGN science collaboration became the AGN interest group, right? And then we did want to do some gatekeeping and basically say, no, you're not going to be a full member unless you're actually, doing things. So we want to like encourage people to apply for full membership, but also meaning like encourage us to tell us what you've done that we don't know about, or if we haven't tapped you and said, hey, we think you should really be applying for full membership, right? And so part of the issue with the publications committee is, we haven't stood it up yet, in part because I don't know, I think we sort of feel like, I don't know who's in charge of this, right?
We have a couple of volunteers.
We have a couple of volunteers, right? But I keep forgetting, who they are, and we probably need 5, and we maybe have 2 kinds of things. So I think we may do some, hey, you should apply for full membership, and one of the ways we're going to punish you is to encourage you to be on the publications committee.
You are punished as soon as you become a full member.
Right.
You have to help do the dirty jobs.
So that is sort of the next cog in this to get things going, is sort of 5 people to be on the publications committee. And what we would like that to mean is not the same 12 people that are full members now, but like basically the idea would be no full member would be on more than one subcommittee, right? So anybody who's on the memberships committee that wants to be on the publications committee, we're first kicking them off the memberships committee and then making sure we've got someone new to.
I think one thing that at least is my impression, but you can correct me if not. So the idea, right, is full members actually people doing real work, but there's a lot of people actually doing a lot of real work that are not full members. So don't necessarily think that by becoming a full member, your workload is actually going to go up. It's more like you actually be recognized for the work you're actually doing, developing science within the collaboration.
Yeah, so I mean, even stuff like, this morning's presentations are a great example.
Exactly.
Okay, if that's enough work to get you a full member, you just need to let everybody know about it and post it somewhere that, everybody has access to.
Exactly, you're not signing up to work more.
And then, then the memberships committee is giving you credit for 100 hours of work, right, that you've done in the past year or something, right? So,
One thing is about the student and postdoc lead project. Usually it's my preference, but if we give them a high priority to lead the project or somehow protected, their leadership by not, I'm not so sure whether it's really necessary formally or not, but if everybody jump into the same project and somebody has a strong voice and carry the project while the students and postdocs are a bit of a silence and they don't speak loudly, will we have to consider that as a situation somehow?
So SDSS did and does have this is a student project kind of thing. So I think it would be a mistake not to also do that.
So maybe this is something we can create a category here as well. So it shows immediately a tick mark when it's a student project.
Yeah, or you could imagine like one of the work packages within a project is labeled as a student project. And in that case, it would be like, please don't be a jerk and, do this thing that some student is maybe going to take longer to do than you want to wait, but it's a student project, right? So.
I agree with that. You certainly don't want to be a jerk, but we still cannot allow cordoning off of projects.
No, but I think there's enough history of this working out, right? So if we just mirror what has been working for other projects, then I think we'll be fine. We don't need to reinvent the wheel. Other things people wanna? Yeah.
Yes, I was just wondering, is this platform going to be also a place to have a discussion in? For example, for the catalog that we're creating, it would be very useful to have a structured way of gathering input, what could be included or what requests people have. So
would this be the place to have this kind of discussion in, or?
Right, so I haven't played that much with the forums feature, but every project can have its own forum, which is, I think, what you're thinking about.
What I'm thinking about, for example, GitHub and pull requests. So something similar, but I don't know everybody not using GitHub necessarily. So just something where you can provide feedback or suggest something or something like that.
Okay. I think that's something that we need to work out. You know, maybe differ by project to project, right? So, for example, we did a couple of years ago set up a Slack channel called AGN-SC-SIMS that was meant for cross communication with all the different groups that were generating simulated data. And I was, hoping that somebody would, be the coordinator of that, and that hasn't really happened. So, so there's a Slack channel that is meant to be dedicated to communication like that amongst groups. We could set up a different Slack channel, and you could set up a forum here. I think, we'd be open to whatever just makes sense, right? No one's imposing rules for the sake of imposing rules, right?
Yeah, I mean, the only limitations, right, is that this is the free version. So there are some things that once you try to do something too elaborate, it tells you that you have to buy. And unfortunately, the paid version is way too expensive for us to afford.
Yeah, do you know what the limits are? Like, 30 people sign up for a project and participate in the forum, and there's 500 messages in the forum. Will that?
No, I think that's actually, there's no limits once you are able to activate a module. There's no limits on the module. But you're not able to activate all modules.
Fine.
So one of the modules that we can't activate, for example, is change the thing that says open project or AGN science collaboration. That actually requires you to pay the full version. Right? It's kind of not important. I think it might also be interesting if people have not signed up to be full members and there's a specific reason you haven't to. It would be good to hear your feedback. It doesn't have to be public, or right, but also if there's something specific that you find it's too cumbersome, or right, the forum is too intimidating.
We haven't approved a full member in over a year,
right?
But we also haven't encouraged anybody to be a full member in over a year, right? So. Yeah.
So my main concern was the stability that postdocs have. So if you apply, but you don't know if you're going to have a contract in 1 year, I don't know how you deal with that. Like, do you need someone to apply for this to be like permanent, or at least have some long contract ahead?
I would say no, right? Because you're not tied between data rights and the science collaboration, right? So it doesn't really matter what your next job is, or if you're actually moving into industry but still want to do some astronomy work, you can still keep being a member of the science collaboration.
We were regulating that for a period of time when it wasn't clear if the project was going to tell us what we could and couldn't do. And they have,
which is still not that could change, but
right. As of now, they're not telling us that we can't have members that don't have data rights. So I think the membership committee's attitude is the only thing that we really care about is to make sure it's very, very clear to people that don't have data rights that we can't convey data rights, and we absolutely don't want you doing a bunch of work that you don't then get credit for, and maybe somebody else does, or something of that sort. And so as long as everybody is going in with that understanding, then I think there's no limitations for full members, whether you have data rights or not. I don't know, we've got 15 more minutes. We can take a longer break. We can talk more about the cadence stuff, or the roadmap, or projects, whatever might be of interest. we have another discussion this afternoon too. We'll have to talk over coffee and see what makes the most sense to do then.
Maybe you can talk a little bit about the roadmap, like in the last.
You want to do that now? Should we do that at the last one this afternoon? Well, why don't we can start now and then see what
Yeah,
happens.
maybe like an introduction.
Yeah. I don't know if you can bring up the roadmap quickly. Not that.
this one,
No,
right?
not that
We have,
one.
we have a link.
If you just Google AGN LSST science
Yeah.
collaboration, that's how I get to it every time.
Yeah.
This one.
Yeah, okay, so let me say a few things about this, right? First, related to membership. So the instructions for applying for membership ask you to refer to this document. In practice, we have stopped doing all checking for associate membership. So associate membership is just the AGN Science Collaboration Interest Group. Basically, very little will keep us from rubber stamping that application. If you're applying for full membership, you should take seriously the instructions in there that says, we would like you to refer to the roadmap. We would like you to refer to the project documents and explain what you're going to do, how you're going to integrate, things like that. And that's just part of that is so that we know what you're actually doing, right? And can maybe say, oh, you should talk to this person over here and talk to this person over here and so on. And the other part of it is just making sure that that you're sort of doing the things that would get you full membership in the eyes of the membership committee. So this is like, so the roadmap is way out of date. It is certainly not everything. We've always encouraged people, like if you don't see what you're doing on the roadmap, but you think it's important for the AGN science collaboration, you should just like write up, that section and do it, right? The vision that we had, or at least that I had, was that what you would do is when you're writing your funding proposal, you would basically say, hey, the AGN Science Collaboration's roadmap identifies this exact thing I'm proposing to do as item, 1.3.2. And so therefore, like, here's a link to this document, proving that that's something that's really important for future science. So I think it hasn't worked out that way.
Well, I mean, you certainly can still do that.
Yeah.
And I don't know, maybe some of our international colleagues have done that. I don't know. I did it once.
I have certainly done it for funding proposals.
Okay.
Just link the section on AGN redshift estimates.
So maybe it has had some impact.
Yeah, I mean, I've done it, but I mean, it hasn't worked out quite as well. Like I wanted to be able to say, 2.21 in some later version of the document in green, like, Roberto's working on this, Mara's working on this, so-and-so is working on this. That doesn't mean they've cornered the market on it, but just so that okay, here are some people that are working on it, and it kind of hasn't worked out that way. So, so it's still like a living document. It's kind of can go two ways, right? And we can decide that, like, should we just abandon it and leave it as, or just leave it as it is, or does it need to be updated, right? And if it needs to be updated, how should it be updated, right? But right now, it the idea is that you would refer to it in your membership application, right? Chris, you had a
no.
And I think part of it, so we might want to rethink a little bit of it, just because we now with the project tracker, there's might be a slightly different way of how you refer to things that are happening, right? Because you no longer need to mark, right, this is being done right now, but these people, but actually people from the collaboration can just go and look at the project tracker.
Well, maybe the project tracker then should include some linking to this, like section number or something.
Yeah, that's I mean, it's linked on the landing page, but
right.
But yeah, each project could on the description.
That might be good to have a little thing.
Right.
Like
So
that.
this I mean, kind of like a NASA proposal where you say this project addresses NASA goal
Yeah,
2A3.7, right? You could say this project addresses, 2.2, 3.31, and 4.1 or something like that, right?
Would it make sense then after the projects are done to have them go back and update the roadmap?
Yeah, I mean, I don't know, will anything ever be done? I mean, done, right? But yeah.
Yeah, you could link, for example, if there's publications, you could add them as a subnote of publications related to this item.
Have you just considered posting the document itself to the Astro PH?
Yes, no one's really wanted to do the work.
Well, posting it, that's easy. That could be done. I don't know. I don't object to that, but I mean, it isn't polished up the way you might normally polish up a professional publication.
Yeah.
So I'm a little hesitant perhaps for that.
I think some of the other science collaborations have done that, but they also have it a little.
As a white paper, but several, people often publish the white papers on PH.
Yeah.
I mean, to there is a more, to make more visual. I mean, than just, it's currently in our inside the collaboration, website.
Yeah. What worries me is the lack of polishing because it's
Yeah.
really unpolished. If you go to some of the details, it requires a significant amount of work.
I think as is, it would be rejected.
Yeah,
right. I mean,
actually, the archive
does not reject a lot, but I think they would reject this.
I see.
Well, according to Wash Stein, that the head of the archive actually is at Penn State, and apparently something that cannot be published something that is not somehow on track to be published in principle in a reference journal will be rejected.
Yeah.
And for a long time, for example, there are these I could go. There's a lot of stories there.
Notes, yeah.
Anyway, yeah.
So I think, last time we updated this was a year ago.
A year ago, right? Yeah. Ohad Shemer made a big push for last year's annual meeting to update it. And for those of you who want to know more about the roadmap document, Ohad Shemer gave a 30-minute talk, and it's on YouTube along with those 20 hours of YouTube video. So if you want to know more details about the roadmap and how it's evolved and so on, you have a YouTube video that explains it all. Yep.
And it is on Overleaf, although I don't think we want every single person even in this room to have access to the Overleaf, because that would just be chaos. But if you really were like, hey, I would like to add a section, we could give you access.
Yeah, I mean, another thing, if someone, as part of becoming a full member, wanted to volunteer to help push this document along, because I think Ohad feels heavily burdened by it, that could be a valuable thing.
No, I was going to say it might be worth knowing how this document gets updated when it gets updated, right? So it's up to the leads of each of the subgroup of the science subgroups to coordinate with the rest of the subgroup the sort of tasks and the text. So if you see that there's something really, really needed, you can now immediately just send your ideas to the project or the subgroup lead that it reflects to. And eventually that will make it, or should make it eventually into a version of the published roadmap.
Yeah, should maybe better than well.
Yeah, you have to get Ohad's permission. I know.
Yeah, Matthew.
I'm aware this might be a controversial opinion, but part of me feels that actually, if people have ideas and want to be, updating the roadmap, it would be better off saying, well, the roadmap was what we wanted to do 5 years ago, and if we want to do something now, we should post a project on the other project and actually move towards a more project-based model of operations.
That's fine. I mean, again, if the roadmap serves the purpose of giving people something specific to point to in grant applications, that's great. The project system, you probably can't get in there, and it doesn't have some sort of stamp of authority saying the AGN Science Collaboration has decided these are the priorities.
Sure, but at the same time, I feel like over the past 4 or 5, however many years, you spent a lot of time and effort producing this document, updating this document every year.
Right.
And I don't think there's anything major missing from it that we suddenly going to turn around and say, actually, we need to, this is critical for our science. I feel like we could all face this.
And I think once the data start flowing, there'll be less of a need to point to this document for grant purposes anyway. So yeah, you can kind of move on.
I mean, it's possible as is, this is the last version.
Yeah.
Right. I mean, I think part of what we're asking here, right, is does this need to be updated? Does it need work? Should we just leave it there for people to point to as need be until data start arriving, or, you know, or what, right? I think the default is that there will probably be no activity on it, and that we would probably move to the project system to do this. But then, yeah, like Niel said, that you're writing a grant proposal, you refer to this and not the project system. But anybody feels strongly like, oh, you know, hey, my ERC grant got turned down because, you know, this wasn't specific enough, and then, yeah, we should do something about that. Okay, I say we break.
Did that address everything? And maybe you were interested in this. Is that good? We're happy?
No,
Okay.
I already know the roadmap. So.
Was that?
I already know the roadmap, but
Okay.
I mean, I think it's a good like starting point. So now that we can start thinking. Maybe something that comes to my mind that could be a good idea is because you know more what is needed. Maybe there are some projects that needs to be developed. Maybe that's a good idea to point. Like, okay, these are the projects that are needed, that will be needed like in the near future, and maybe we can start like new projects focusing on these topics.
Okay. Yeah. I mean, maybe we can talk about some of that for the last one this afternoon. Like what, you know, are the junior people in the room waiting for other people to sort of tell them what to do in terms of, or what is interesting to do, or things like that, that we need to post this projects, or, yeah. Okay, we can talk more in.
Yeah, I was going to say, note that the majority of projects or ideas linked there, nobody's actually developing. So if you have any interest in developing them.
Yeah, like I said, mine was posted as a placeholder. I intend to do none of the work. That's not quite true, but okay.
So we're ready to begin this afternoon session with Yoon Jung and structures of AGN accretion disks from X-ray to UV optical emission regions.
Thank you. Great pleasure to be here. So this is actually the first talk in the theory sessions. So I heard a lot about data, about the observations. So I'm trying to actually tell you something we think we can study the structure of the accretion disk around the AGNs, and particular, let me see. Yeah, in this talk, I'm trying to, because the observers and the theorists actually use quite different languages. So in this talk, I'm trying to connect what we see from the simulations or the inner regions of the black hole accretion disks, and what is the implications on the variability properties of AGNs, particularly in the LSST era. And one of the things, first thing I want to show you is kind of what is the structure of the inner accretion disk emit all the X-rays, UV opticals from the simulation and compare with the standard alpha disk models. I mean, the 90% of all the observers basically use the alpha disk model to compare with the observations. It's actually, it's not their fault, it's the fault of the theorists, because the alpha disk model is still the only model that can be easily used in your analysis. But I think we have made a lot of progress in the recent years to learn what can be trusted and what need to be improved based on the simulations. And another thing that I think from the observational point of view, you may think alpha disk is a basic study, so you are surprised to see all the kind of vulnerabilities when you actually look at the data of AGNs. But I can show you that actually, if you do the real time-dependent calculation of the disk, the AGNs have a lot of interesting vulnerabilities depends on the physical condition in the disk. And I'll show you two examples on kind of vulnerabilities that is very basically robust and will vary as a function of black hole mass and m dot, which we can actually test from the data. And then I will have some implications on what we can do to connect both simulations and all the exciting data from the observations. So to begin with, I think as a theorist, we always have a very simple picture in mind in order to connect the physical conditions in the disk and the observational properties. So the basic picture, right, for accretion around the supermassive black hole is very easy. You just convert your potential energy and emit that in photons. If you are closer to the black hole, you will emit with a higher temperature, so you are in the short wavelengths. That's why X-ray is always coming to the inner regions closer to the black hole. And if you move to longer wavelengths, your optical is always further out. So these are the very generic properties of the accreting system. This is nothing to do with, for example, the alpha disk in particular. And I think it's very important actually to get some basic numbers on some of the relevant time scales. And the time scale, the first time scale is always, this way. Okay, the first time scale is always the so-called dynamic time scale. And that is also very simple. It's essentially, if you assume your disk is in Capellian rotation, you know your black hole mass, say 28 solar mass black hole as an example. And then you go to a distance, say like 20 gravitational radii. Go back. You want to go like 20 gravitational radii, and then you get a dynamic time. It just is the time you finish one period. It's about like half days if you go to like 20 RG, and then you go to like 6 days, go to like 100, typically like the UV regions you expect, and go to further out, get to 30 days. But for another very relevant time scale is the so-called thermal time scales, because the accretion disk is optical thick, and the time for the photons to go from midplane to the surface will depends on the optical depth, and then will actually depends on the accretion disk structures. And typically like 10 days in the inner regions, and then like 100 days if you go to like 100 RG, and go to more than like a few years if you go further out. And that is again very generic properties of the disk. And if you look at all the vulnerabilities, right, when you look at the real light curves, that's not surprising. You see vulnerabilities on these time scales, because for any optical thick disk, the generic vulnerability time scale, it is on the order of the thermal time scales. So this is a very simple estimate, but the more relevant or more specific to the so-called alpha disk model, there are two properties, which one is the so-called inflow time scales or the viscous time scales. This is actually very specific tied to the alpha viscous disk. That you rely on the viscosity to exchange angular momentum. So the material flow from the large distance to the inner regions is very slow. Like that process or that time scale is like 10 to 4 days, like hundreds of years or something. And that's why I get surprised when you see the fast variability in AGNs, which can happen right in years or 10 years, that much shorter compared with the viscous time scale that you will estimate based on the thin disk model. Another property that is not discussed a lot in the observers is the scale height. If you think about all the reverberation, for example, you have the inner region reverberate, like irradiate the outer part, and typical picture we have is that you have an alpha disk model, and then the scale height where the photon emitted a function of distance in the thin disk limit or alpha disk model, you always want to compare to in the radiation pressure dominant regimes. The scale height is actually independent of the radius. It's just a function of the accretion rate in N10 units, and then the number. So the disk is flat in that sense in the alpha disk geometry. So I just want to point this out, and then I will show you what the real structure will be. And that will also have implications on the reverberation that the people are thinking about. So although that the simple models, so at the title side of the, so it's basically like 40 years, 50 years after the Hernandez-Garcia disk is developed. If you want to make some progress, it's very hard to come up with a simple some analytical model can do better than that. So the thing we do is just do simulations. So the simulation, in my point of view, it actually likes the experiment. Like what you do is that you build a code that solve the set of fundamental equations, which we think capture most of the important physics that are relevant for the disk. And for AGN in particular, there are a few things that we think will be relevant. And one thing is the MHD. And the reason for that is because we believe the magnetorotational instability is responsible for all the turbulence and the angular momentum transport. So you want to have the MHD being able to do the disk structure so consistently without rely on any alpha assumptions. That's why you can check the alpha disk model. Another important thing is the radiation transport. You actually, in the regime where radiation is actually important for the dynamic structure of the disk, when the accretion rate, for example, is a significant fraction of the anti-limit, but also radiation is just the only way to cool the disk, so that also set the thermal structures and the radial profile, for example, the temperature. And then another thing I will mention that one unique thing for AGN is that you are in a condition that the opacity is very rich, that the electron scattering is actually not the only dominant opacity in the disk. You could have a very different opacity as a function of density and temperature can make a lot of interesting properties of the disk. And then another thing I want to mention that those simulations are doing for 3D, and in particular, we actually expect the disk become very thin. For example, if you actually calculate the ratio between the scale height in the alpha disk model and the radius, the typical ratio of HOR is like a few percent or even smaller, down to the region like 50 or 100 gravitational radii, where we think the UV optical emission are coming from. So we use a technique like a mesh refinement. You have the low resolution, have the whole sphere and using several level of refinement to resolve all the thin disk near the midplane. And what you can learn, basically, you build like an experiment or laboratory, and you run the 3D simulations with a certain initial conditions. Well, definitely not the model, the real nature of what the agent is doing, but we can just do that control experiment. And then we can learn, we can basically observe what we see from the simulations, like you observe from the real data of AGNs. But the advantage of the simulation is that we know all the details, every quantities in the 3D mesh of the system. So we can look on what is actually responsible for the different part of the property of the disk and how that change a function of like black hole mass or m dot that we can vary. So that is the advantage compared with the observers. You get the data right, but no way you can actually see exactly what the nature is doing to the real systems. And then by this way, we can actually try to understand what is the real structure of this and compare with the data. So that is the basic setup. I didn't show any equations. If you're interested in all the equations, I can tell you. I feel that will be very boring during the talk with many observers in the audience. So this is the opacity that I mentioned. So again, remember, like in the Hernandez-Garcia thin disk model, the dominant opacity is basically electron scattering, which will be a constant. Actually, I will say that if you actually read the title of the Hernandez-Garcia paper, the model is actually developed for X-ray binaries. So they say that in particular in that paper, the model is for X-ray binaries, which is actually very appropriate if we're seeing the dominant opacity, the electron scattering. It just, we want to know the AGNs. So we just follow the model and try to apply that to AGNs. But it turns out it's actually not not straightforward to move that direction. And the reason is that if you actually consider the typical temperature and the density that are relevant for accretion disk in AGNs, again, you do not actually need to trust any of the thin disk assumption to make the estimate. If you simply say that the emission from the disk is thermalized, so the thermal emission with the typical luminosity, for example, antenna luminosity, is always the luminosity value that you get from accreting system. And the emission area is basically 4 pi r square, where r is basically characteristic of the gravitational radius, right? For black hole, gravitational radius is just a scale to the mass. If you take the angular luminosity, divide by 4 pi r square, and you will find that for AGNs, if you go to like 10 to 7, 10 to 8, your temperature will be around 10 to 6, 10 to 5. Of course, depends on the detailed structures. The exact value could be different, but we know this is the right temperature regimes you expect for any of the thermal emission coming from the region around the supermassive black holes. And the characteristic density, if you take the range from like 10 to -8 to like 10 to -12, for this curve, the vertical axis is the so-called Rossum mean opacity, which basically determines the coupling between photon and the gas in the momentum equations. And each line is the function of the Rossum mean opacity as a function of temperature. Oh, should do this. Each line is the opacity as a function of temperature for fixed density as indicated on the numbers. And for all those different lines, not very responsive. For all those lines from the top to bottom, the density differ by factor of 10, go from 10 to -8 all the way to 10 to -12. So if you go to very high temperature, everything is ionized. So you get the electron scattering limit. But if you're actually around the temperature like a few times 10⁵ K, which is very relevant for the region where the UV and emission is produced, you get the enhanced Rossum mean opacity due to the ions, which can be a factor of few larger compared with the electron scattering. If you go to even lower temperature, then depends on the actual density, you could a much larger enhancement due to the helium ionization, or could be small if the density is too low. So this is the kind of opacity that we have in the simulation. So we want to do with all those additional physics, what is the disco will look like. So the first side of simulation I show you is the for the simulation box we put to the very inner region of the disk. So this is another caveat of the simulation that you may think for the simulation you just put everything in the computer and then you see what the disk look like. That's not what the simulation will work, because if you take the distance from gravitational radii to 100 gravitational radii, the kind of dynamic time and the thermal time scale from the inner to outer region can vary by a few other magnitudes. No way that the simulation can resolve all the range simultaneously with the full radiation, with the full MTD in full 3D. So that's impossible. So what we do is that we take our simulation domain first to focus on the very inner region, try to see what the X-ray emission region look like with different accretion rate, and then we move the box to the outer part, try to understand the structure in the UV optical emission regions. And then we can make some progress to see what the disk look like. The first set of simulation is for the simulation that focus on the one inner region, basically is like a 30 gravitational radii. For like a 10 to 8 solar mass black hole, the top panel show you the density in the left column and the radiation energy density in the right column. When the accretion rate that achieved in the inner region is about 7% of the antenna accretion rate, and the bottom panel show the case when the accretion rate is about 20% of the antenna accretion rate. So it's clear that when the accretion rate is larger, the density is increased. So the disk is become relatively thicker. But you can also notice that if you the dotted black line is the location of the electron scattering photosphere. For those inner regions, the disk is actually a little bit thicker. The distance between the electron scattering photosphere from the midplane is actually larger compared with the predictions. If you simply take the same accretion rate and you calculate the value by the alpha disk model. And more important, for those inner regions, because we're actually doing the radiation, you can actually look at the gas temperature, right? For the thing near the midplane, we are inside the photosphere, the gas and the radiation are summarized. So you get a characteristic temperature around a few times to 5K, as you expect, once you have summarized emission. But once you're above the photosphere, because of the empty turbulence, you heat up the gas, but because it's optical thin regions, the gas cannot cool efficiently, and then the gas temperature increase rapidly. And more important, the simulation can show you how the corona actually change the function of m dot. Basically, when the accretion rate is larger, the disk is thicker, and then there's actually less dissipation happened in the optical thin regions. Then the amount of X-rays you get in those high m dot case is relatively smaller compared with the case when the accretion rate is lower. This is actually pretty consistent. For example, the alpha OX relation function of luminosity. When the luminosity is larger, the ratio between the X-ray emission and the optical emission gets smaller. Another interesting thing that you can just collect the photons produced by the simulations and look at the variability properties. For the low accretion rate case, which is shown at the top panel, and the high accretion rate is shown in the bottom panel, you really do not need to do any Fourier analysis. You can immediately tell that the lower accretion rate case, you get more variabilities, particularly variabilities in the short time scales. In the accretion rate, the lower, all the short time scale variabilities get smoothed out. And that fundamentally because for the lower accretion rate case, the optical depth through the disk is much smaller. So you can actually see photons almost through the midplane. So you get a variability kind of in the dynamic time scales of the flow of the turbulence. But once the disk become optical thick, when the accretion rate increase, all the dynamic scale variability gets smoothed out because of the optical depth effect. And then what you see is only the variability around the thermal time scales. So those are the simulations for the inner regions. If you now move to the outer part of the disk, then another thing that you see immediately is that in some conditions, you actually see that the more is playing. You actually see the disk can oscillate. And this is actually regimes when the ion opacity show up. So this is the simulation we focus on between like 50 Rg to like 100 Rg when the disk temperature gets a little bit smaller. And then in the midplane regions, when the temperature is around like 2 times 10 to 5K, the ion opacity show up. When you have an enhanced ion opacity, it's just like the envelope of the stars. Then the diffusion of photons is not quick enough to transport all the energy generated by the accretion, and then convection develops. Once the convection develops, the disk will become thicker, and then you transport the energy out by convection, and then the disk cool down. Once the disk cool down, and then the opacity shows up again, and then you can repeat this process. So this is basically like the fundamental mode in the stars when driven by the opacity effect, except that this is in the disk. This is not in any particular radius. The opacity is very sensitive to temperature, and that can cause the disk to oscillate, but not in like a harmonic single period of oscillations, but more like a broad spectrums. I will skip that. Another one interesting that because of the opacity depends on the temperature. So if you even for the same black hole mass, if you try to change the why the slides in the screen not the same as the.
Can you go back?
Maybe you want to share again.
Yeah,
Quit and share again. Okay.
Yeah.
Okay. Yeah. So the interesting that because of the opacity are the strong dependent on temperature. So in the simulation, then at the experiment, you can just reduce the accretion rate, and then the temperature will change. And this is another disk structure you achieved when the accretion rate is 0.8, 80% of the antenna accretion rate. And then one thing you notice that from the movie, so you always get a very thin layer when the density is much higher. So the color indicates the density. And then you get a surface layer, which is much lower density, but accrete much faster. So the thin layer near the midplane is actually very similar to kind of a disk you expect from a Shakuni disk. But the thin layer on top of that is actually supported by magnetic field. And that actually can have very rapid variability and accrete much faster. And then another important thing that in the standard disk model, the scale height only tied to the magnetic field, so tied to the gas. But in this case, when you have a magnetic supported surface layer, that actually push the photosphere very far away from midplane. And that effectively make the disk you care about much thicker than what you think. And that's because if you think about if you have a X-ray, for example, try to irradiate the outer part, what you have first is interact with the photosphere, not actually near the midplane of the disk. So this is a kind of a characteristic structure we always find from the simulations now with a thin layer, where all the accretion happened, and then have a surface layer will grow very faster because of the magnetic field. Another thing I just want to mention that this is also very interesting that if you actually focus on the outer part, because of the magnetic domination is still inside the photosphere, you actually do not get the corona when you have a move to the disk like 100 RG from the black hole. So this is a very quick, in the last 1 minute, I just want to mention that there are a lot of actually interesting new thinking led by, like, for example, a few groups listed here, like the kind of variability we'll be looking at by compare the different wavelength band. This is actually not the only variability in principle could exist in the disk. So what they are doing is that they are using the time resolved spectrum and try to connect the particular wavelength band to a temperature in the disk. And then you can make a plot of the temperature fluctuation as a function of radius and the function of time. And then based on the SSDS spectrum, you actually see a lot of wave patterns propagate through the disk. So this is actually probing the emission region of the disk and see wave that can propagate out and wave can propagate in with a characteristic speed, actually the few percent of speed of light, which is nothing like the viscous speed you expect from a thin disk. And you can essentially do the same thing from the simulations because we have all the temperature information, and then you can just calculate the temperature fluctuation for a particular simulation we have and plot the time and the radius. And not surprising, the turbulence generate a lot of waves that can propagate in and propagate out. And the characteristic speed is essentially determined by the Alpha velocity at the particular location of the disk, which is also on the order of a few percent of the speed of light. So that's also very interesting that the simulation, if you look at in details, would have a lot of variability that we hope to probe with the data. Given the time I have, I think I will just jump to the final slides I have for the implications for LSST. I think the thing that we have learned, all the talks before, when people care about the continuum lags in different wavelength bands, but I will say that those lags are probably just probe the photosphere at different location of the disk, and that could have a different geometry if you consider the realistic structure of the disk. But more important, all the short lags coming from the inner to outer part really does not probe the internal structure of the disk. For all different waves and fluctuations we have in the simulations, we hope to actually using the data to connect, and Amy will tell you more about what we can learn by connecting the particular type of fluctuations so you can tie to the particular structure of the disk. And then all the variabilities we have from the opacity, from the empty turbulence, if somehow we can actually find them from the variability of the AGN light curves, that will be very powerful tool to determine the properties, for example, the magnetic field structures and the radial profile of the disk. And then another one important thing that the simulation also predict how those vulnerabilities will change a function of black hole mass and m dot. Even though we really only have a few simulations, but still we can actually see whether those theoretical predictions at the disk at the change is consistent with what we see in the data or not. That's it. That's all I have. Thank you.
Are there any questions? Yes.
I was just wondering, what are the shortest variability timescales that you're able to see in your simulation?
In the simulation, so the simulation time step for the simulation point of view is limited by the ratio between the resolution and the speed of light. And the resolution typically is like 1/10 or even a few percent of the scale height of the disk. So that time is very, very small, like minutes or even seconds, which is tiny compared to AGNs. And the issue is actually longer time scales. We really can resolve only a few summer time scales that limit what we can compare with actual data.
Any other?
Yeah, I was interested, of course, in your relation between the optical to X-ray flux ratio, and I guess you had it with Eddington ratio. Right?
Yes, yes.
Yeah, so
yeah.
The thing that's always been puzzling to me is when you look at that correlation, you know, the correlation is in fact strongest with luminosity. You know, the correlation, alpha X correlation with luminosity. And we have certainly attempted to look for correlations with Eddington ratio, and they are there to some extent, but they're actually seem to be weaker. And I've never really understood this. Do your simulations give any insights into why luminosity would be the driving thing, or is that not what you would expect?
Well, I will say that from theoretical point of view, everything scale with Eddington ratio. Like the black hole mass, if you change the luminosity, if the Eddington ratio change, you will have a different structure of the disk. Right. So I think from the theoretical side, that is definitely the quantity we want to look for. But when you look at the observational side, right, the luminosity definitely the only thing you see. So I think then when you change the black hole mass, the other complicated things that could show up. For example, when you go to smaller mass black holes, every time all the characteristic temperature will increase. So you may actually change the opacity more quicker compared with the simple estimate based on the Eddington ratio. So I think that could be the complication where several physics come together to change the optical emission and the X-ray emissions. The only downside is that again is the number of simulations we can have. So the thing I mentioned is only 2 simulations. This will show you the trend. If you really want to check, we want to do maybe another 10 to 6 solar mass black, for example, for 2 different mass accretion rate. Then we can actually see how the actual alpha OX relation would vary the more strongly on the luminosity or the black hole or the Eddington ratio.
Right. So if I understand you correctly, then you're basically saying what you ideally would want to look at is alpha OX Eddington ratio at fixed mass.
Yes, exactly.
Yeah, but this is obviously.
But observational, right?
It could be done, but it would just be, it's very observationally demanding to try to do that. But it probably could be done if you'd have to have a very big sample, all that's reverberation mapped.
So that's why I think the little bit tricky actually try to connect the simulation directly to the observers. But at least you can do that if you have a control sample in the way as we will think we're doing in the simulation.
Yeah, so I can certainly understand how alpha OX Eddington ratio would be screwed up because you're looking at objects with a range of masses. But then why would the correlation be so clear with luminosity? This is the puzzling thing to me. I mean, again, I would prefer, for the reason you just said, that it actually correlated better with Eddington ratio.
Well, that is the question maybe on the observational side, like how statistically, when the luminosity is particularly lower, whether there any observational bias or any when you actually convert, for example, the X-ray and the optical, I always have a question like how do you get the photometric factor correction? Like how do you go from the wavelengths in a particular to connect to the optical emission we think we are doing.
Well, so the correlation is not with the bolometric luminosity. The correlation is with the specific luminosity in the ultraviolet at 2,500 angstroms. So it's something you can measure quite directly. You don't have bolometric corrections running around. Yeah, anyway, this gets a bit technical.
Yes.
Yeah, go ahead.
Okay, yeah, thank you.
Here we go. Thank you. So the next speaker is Emi Secunda with simulating multi-band quasar light curves using radiation magnetohydrodynamic simulations.
If I want to use the pointer, it goes this way?
Yeah.
Yeah.
Try that.
Yes, there we go. Okay. All right. Hi, everyone. I'm Emi Secunda. I'm a fifth-year grad student, well, almost fifth-year grad student at Princeton, and I'm going to talk to you about some work I've done to try and simulate multi-frequency quasar light curves. And the goal here is to actually simulate discontinuum reverberation mapping. And so we had a couple talks that mentioned discontinuum reverberation mapping this morning. And the general idea is that you have high frequency X-ray light emitted from the inner regions of an AGN, so from the hot corona. And some of this light comes right towards us, and we see variability in these X-ray light curves. But some of this light moves outwards along the disk where it gets absorbed by the disk and then re-emitted based on the local disk temperature at different wavelengths. And so because it takes some amount of time based on the light crossing time scale for this light to move outwards in the disk, we actually see a lag between the variability in X-ray light curves and then the corresponding variability in UV or optical light curves. And we can use this to measure the radial extent of the disk because we know the speed of light and we can measure the lag, or we can learn about the radial temperature profiles of these disks because the temperature determines which wavelength these light curves are re-emitted in. Okay, great. And so I'll show you this example in some actual light curves, Swift and LCO light curves from Farrell 9 from Hernandez-Garcia et al. And right, so up top, I'm plotting the X-ray light curve, and you can see that it has a lot of variability in it. And then below, I'm plotting some UV and optical light curves in the B band and the Z band. And so you can see if you look at this peak over here, we have this nice peak that happens in the variability of the X-ray. And then you can see that there's a corresponding peak that happens in the B band and the Z band, but it happens a little bit later in time. You can see kind of this shift a little bit further. And so this is kind of the lag that we measure. And it's nice that you can see it by eye, but of course, there are various techniques that are used to measure these lags. But there's a couple other things you can notice about these light curves. So first, right, some of the more high frequency variability that we see in these X-ray light curves, as we move down into the UV and optical, the light curves are definitely smoother, right? So there's definitely some loss of variability. And then a second thing you can see, because it's plotted really nicely here, is you can see kind of these curves going through the different light curves that show maybe some long period variability kind of over the course of the whole observing period, so like 200 days. And you can see that in the optical and UV, it's kind of like a parabola, right? It's not a straight line, whereas in the X-ray, it's pretty much a straight line. And so this is kind of the opposite thing where we see that there is some long-term variability that's present in the UV and optical bands that doesn't exist in the X-ray. And so our traditional lamppost reverberation mapping models say that, oh, all the variability that happens in the X-ray, well, it just gets copy and pasted in different wave bands as the light moves outwards in the disk. But that isn't actually the full picture. There are some other things going on there. And so my goal is to simulate these light curves. And so I do that using a shearing box. So you can see the little shearing box over here. And So that's just essentially a very localized approximation for a region in this disk. And kind of like what Yanfei was saying in his talk just now, we are doing this local approximation because it's very computationally expensive because of the different dynamical timescales. If you do a global simulation like what he was showing you, the inner and outer radii have very different dynamical timescales, and it's hard to resolve both. So for the sake of time and efficiency, because we're going to be using 2 different frequencies of radiation, we do a shearing box simulation. But it is a 3D shearing box simulation. Our box goes from plus to minus 7 scale height. So it's a tall box because that's important. We want to be able to capture the photosphere so that we can capture radiation coming into and out of the box. We have good resolution of about 10 to the minus 2 scale heights. And then also, as Yanfei mentioned, we have a magnetic field in this box. And again, it's important to have a magnetic field because this can provide pressure support for the disk and also lead to turbulence, which might generate some of this variability that we're looking for. So, okay. We set up these boxes in radiation hydrostatic equilibrium, and again, with these realistic opacities. So, right, Yanfei was just showing you, but there's this bump in the Roslin mean opacity, and I can show you directly here. If you look, this is a plot of the density as a function of height in the disk that we use for our initial conditions. And you can see that there's a density inversion here, right? If you just use a constant opacity or you don't include this iron opacity bump, you don't get this density inversion. And that's interesting because it can lead to an entropy inversion, and then you drive convection. So it can both puff up your disk and again lead to an instability that will lead to variability. So it's important to use these realistic opacities. Okay, so then we do the exciting stuff. We add the radiation, and so we use an implicit radiation, and we're going to use 2 types. So the first type is this low frequency radiation that's based on the local temperature of the box, which is around 200,000 Kelvin to represent kind of the UV optical region of the box, at the midplane. And then the second thing we do is we add a second high frequency radiation coming into from the top and bottom of the box, so in from the photosphere. And here we use interpolated light curves from Ferrel 9. So we use the actual X-ray light curves, again, interpolated down so that they fit the time step of our simulations. And then what we hope to do is we can measure how much flux is leaving the box and just use that to create a light curve. So we can measure the flux that's leaving in this low frequency, so this UV, and then we'll get essentially the reprocessed X-ray UV light curve. So, okay, so we did do this. So first I'll just show you, right? So if we do this and we don't inject any X-rays in, we just have a single frequency simulation where the flux is just due to the local temperature radiation in the box, we actually can get a light curve. This shows the flux just over about six orbits. And you can see that there's already variability here. So essentially, if there was no X-ray being injected, you would still have a varying light curve. It's a pretty low frequency variability. In our simulations, an orbit is almost 15 days. So, you know, so it's not a daily, but it's a sub-daily timescale variability. And then, of course, what we do is we do add the injected X-ray, and then what we're going to get out of it is this reprocessed UV light curve. And so I'll actually put it together like this so we can compare them, right? And so the idea is injected plus intrinsic UV, what does it look like? And so if you look at the light curves, you can kind of see that a lot of the low frequency variability in the reprocessed UV light curve kind of comes from this intrinsic variability. But certainly the high frequency variability in this reprocessed light curve is coming from the injected X-ray. For example, right, if you look at these really sharp spikes over here, you can see them also appear in the reprocessed light curve. I mean, you can see that again and again and again. And so it does seem to be some combination of both light curves. And then we can look at this, we can look at the power spectral densities of the injected and reprocessed light curve, because we're curious to see, okay, so, right, we had seen some smoothing in those real Ferrel 9 light curves, but we had also seen some low frequency variability in this Ferrel 9 light curves. So for our simulated light curves, at what frequencies, at high frequencies, at low frequencies, do we see the reprocessed light curve be suppressed or actually be have more power than the injected X-rays? So far, again, we have about 8 orbits. And so we're working on going to 10, 20 orbits. These are time-consuming, expensive simulations. And so once we get there, we hope we'll have a little bit more of a range of frequency spaces. But right now, what we're seeing is kind of just an overall suppression of the power in this light curve when we go from the injected to the reprocessed. Again, we kind of expect that. We expect there to kind of be some smoothing. But again, we're really interested to see in the future if there's a region in frequency space where it isn't as suppressed, or, you know. And then the next thing we can also do is we can just look at how well correlated the injected and reprocessed light curve are. So we look at the cross correlation coefficient of these two light curves. So if they're well correlated, we would expect it to peak around 0, right? There shouldn't be some broad distribution because they're not well correlated, and there shouldn't be some distinct lag between the two. And that's kind of what we see. Again, right, we're not injecting these light curves and waiting for them to travel the length of the disk. So we're not expecting the 2-3 day lag we would expect from reverberation mapping. We're expecting 0, right? The light goes in, it should be reprocessed and come back out. On the other hand, this obviously doesn't happen instantaneously, right? I don't think a big question is how deep into the disk, does it have to go through the whole photosphere into the midplane of the disk, or can it just be reprocessed at the surface of the disk? How deep do you have to get to have this reprocessed light come back out? And the deeper it has to get, the longer that'll take, because these are optically thick disks, and so it'll take time for the light to travel down. And so we see like a little bit of evidence, I guess, if you look really closely around here, you can see that there's a little bit of a lag, but I don't think it's that distinctive yet. We're going to build up more statistics as we go to 10, 20 orbits. But yeah, so the idea is there might be a little bit of a lag that, again, is the time that it takes for the light to move and the light to reprocess. Another question that we're interested in is, in those opacity plots at high temperature, right, and these X-ray light curves are high temperature, right, you're very dominated by the electron scattering opacity. And so a question that we want to ask is, does the reprocessing, is it the gas absorbs this energy and then re-emits it because it's absorbed the energy? Or is it actually more of a momentum transfer? And this momentum transfer is what leads to this reprocessing. And that's because, again, the scattering opacity is really dominant over the absorption opacity. So there's very little actual absorption going on in our simulations. And again, we still see reprocessing even with almost no absorption going on. And so one thing we can look at too is, how does the X-ray being injected change the disk, right? Do we see a temperature enhancement? And so, so I'm plotting again, we only have UV, we have no injected X-rays versus UV with the injected X-rays. And so you can see in terms of density, so these are azimuthally averaged vertical density profiles. So on average, as a function of height, the density is pretty much the same whether we inject the X-rays or not, right? There's a lot of stochasticity in the density once you get above the midplane, but those, they look pretty similar, even if they're not exactly identical. And then for the gas temperature, we do see a little enhancement, right? If you look at the midplane right around 0, there is actually, the gas is hotter. So there is some heating going on even in the midplane. I should say this is a single time step from like the furthest point in our run. So about 6 orbits after we've started injecting these X-rays. And then you also see a little bit an enhancement of temperature away from the disk. It seems to actually be stronger on one side of the disk, which is a little odd, but not horrible, because again, remember, these disks are turbulent, so you don't have identical tops and bottoms. If the opacity happens to be slightly lower in the top portion of the disk, then you'll have a slightly different gas temperature. But yeah, so this suggests that there must be some actual energy transfer going on, but that we really might be dominated by this momentum transfer, which is kind of a different picture than we were expecting. Okay, so just to summarize, right? These multi-frequency radiation MHD simulations are actually able to simulate this reprocessing, which is useful because it can actually teach us about the physical processes that lead to this reprocessing. Looking at our light curves, it seems like the high frequency variability in reprocessed light curves does come from the X-ray, but the low frequency variability comes from the actual disk variability. And so looking at these two different variabilities in our light curves can teach us about the internal physics of the disk. And so ultimately what we want to do with these simulations is we want to be able to write down the transfer function of the reprocessing, so that instead of kind of what's in use today, which is mostly like a Gaussian or log normal distribution to describe these reprocessing, we can just write down a function that's physically motivated. And then finally, we want to do a parameter study. Reverberation mapping timescales depend on AGN parameters like accretion rate, like supermassive black hole mass, right? Also, we're looking at one very specific thin slice of the disk right now, but we want to look at different regions within the UV optical region of the disk. And so this might affect how the transfer function actually works. So that's a future step. And I guess the last thing I should mention is that Yanfei kind of teed me up to talk about some research I've been doing about what we've been calling a long negative lag. And I think I've talked to some of you about this, where actually it's looking at kind of this low frequency variability that happens with, that is caused by disk variability being accreted inwards on the inflow time scale, which we think may be as short as, tens to hundreds of days, so therefore detectable. And we've done a lot of work thinking about how we can use LSST to look at those two. But this work is kind of necessary to do that, because until we understand how, the simplest form of reverberation mapping works, and that, it's just the light crossing timescale, it's hard to understand how this accretion-based lag works. So anyway, thank you so much for listening.
Questions? Yes.
So my pipe dream for LSST is not just to select AGNs and do photo zeebs, but to use the variability to basically estimate the accretion, the Eddington ratio.
Right.
Right. And so what motivates that is we see significant differences in the variability in terms of, high frequency, low frequency, timescales, amplitude, whatever, as a function of Eddington ratio.
Right.
And so, I guess the question is essentially, what's the difference that you see or expect for a thin disk versus a slim disk? Are you going to have cases where you're only going to see basically the UV variability and not the X-ray injected because of some geometric effect, and then other cases where you are going to see both the underlying UV variability and the response to the X-ray as a way to sort of explain how things are changing as a function of Eddington ratio? Does that make any sense?
Yeah, no, it definitely does. Yeah, I think, right. if I had a guess, and again, like this is part of why we want to do more of a parameter study, but I had a guess, right? Like in terms of the intrinsic variability, you're limited of, it's probably easier to see if it's on a shorter time scale. You know, I don't think we have to worry about it getting on such a short time scale. We can't differentiate it from the high frequency X-ray variability. But so, you know, having, right. So I think how the disk changes the thermal time scale, I think could have an impact on whether we could see it or not, just because if the thermal time scale becomes, you know, 1,000 days, that's probably going to be hard to see even with LSST, but yeah, that's my first thought, but.
Maybe I'll send you a slide and sort of get your reaction to, you know, this is the slide I show. Am I lying when I show this slide? Or,
yeah, that would be great.
Any other questions?
Yep. So in your shearing box simulations,
yes.
You know, it certainly looks like there's quite a large amplitude of variability. But I guess my question is, how many boxes are there in a disk, and to what extent does the averaging out effect damp down the amplitudes?
Yeah. So that I mean, I'm trying to think physically how many boxes are in it. I mean, you know, thousands. Thousands. Okay. Yeah. I mean, the box is less than a scale height wide. So. And
will the boxes be correlated with each other, or is each box big enough to be statistically independent from the others?
So I guess right. So you're saying like if you observe a B band light curve, right, you're going to be observing many. You know, like does the variability differ too much from box to box so that you average it out? Is that what you're saying?
That's right. Yeah, how directly can this actually be interpreted in terms of anything you've ever actually observed from a full disk?
Yeah. Again, I think the helpful thing is right within the band, you're still pretty localized. And I think this variability isn't so local that it, you know, this part of the band's going to be doing this and this part of the band's going to be doing this. If you know what I mean? Like it's not going to average to zero, if that makes sense. So, right. It might look different than this, but I think it's still together, the time scales and the amplitude should be similar, I think, is what I'm trying to say.
So, okay, so you're saying the disk, the collective phenomenon of the disk, I mean, it spans, to do that, to have this be representative of the whole disk, you have to have this essentially be the way the entire disk behaves, right?
Well, no, again, I'm not saying the whole disk. I'm saying, you know,
how many independent regions are there, each one operating like that?
Right. Well, so I mean, none of them are independent.
Sure.
Right. But the scales of the fluctuations causing this are very small and stochastic, but they still overall combine to an effect that, you know, so for example, we're resolving the turbulent, the scale of the turbulence that's causing that, but it's much smaller than even the size of this box, if that makes sense.
Right.
So yeah, does that help?
Yeah. Okay. Yeah, I see what you're saying. It would be very helpful to have an estimate of that, you know, carefully sometime.
Yeah.
Okay.
So I actually have.
We have an online question first. Sorry.
Okay. I just quickly read it. The one question from online. The diagram you showing the correlation function. And what strategy did you use to create that? Or how do you measure the correlation function?
I just calculated a cross correlation function because these are evenly sampled light curves, so I can just use whatever favorite correlation function package or whatever.
Okay.
Yeah, it's so.
Okay, I guess you can go ahead.
Okay, so it's actually a related question. So for these tall shearing box simulations, they usually have this butterfly diagram that you have magnetic field coming up.
Yes.
So is this, so there are two questions. So one is, do you think this variability associated with those magnetic field rising up? And then the second question is, what is the scale of those magnetic field? Will those create your large scale correlation to lead to the overall variability?
Yeah, so I think we haven't quite looked at in a detailed way, right? We suspect that it is MRI turbulence that's leading to this, but there is, again, also some convective instabilities that we've seen, in another, right, in a space-time diagram. So we've seen both essentially, and so I don't know yet which is causing this variability, or does one cause a different sort of variability from the other. So that's something that we want to investigate.
Yeah, so I guess if you can demonstrate there's some large scale things.
Right. Yeah, right, exactly. Because this convection, again, we're not saying it's the whole disk, but it's a large region of the disk that would be correlated. So yeah.
Thank you. I guess we can go on.
Thank you, everyone.
So the next speaker is Chi-Huan Chan. Right. Okay. Variability crisis are GRMHD2 variable.
So by the way, I go by CK. So in case we haven't met, I hope that makes it easier for everyone. Yeah. So today I'm going to talk a little bit about this variability crisis that the Event Horizon Telescope are facing in our comparison of simulation and observations. So this talk, I guess, is a little bit different from the others because I will be talking about Sagittarius A star, which is log media AGN. But I guess I don't feel too bad because this is NRAO, and this is the place that we discover the radio source at the center of the Milky Way. And also, something I ask everyone to do is whenever you hear me saying Sagittarius A star, you can translate that to no luminosity AGN. Right, so all the things that we are talking about, all the physics that we are studying, potentially we can apply to things that people here are interested in. So, because this is different from other talks, so let me just be upfront about all the things I'm going to tell you. The important thing is in terms of air phase property, we are pretty good in simulating black hole. We can actually match a lot of observation properties. But once we want to compare variability, then we face a problem. It turns out GRMHD are two variable, so we call this the variability crisis. We have a very big library of GRMHD simulations, but then all the models in our library are two variable compared to the observation. So this naturally leads to two different questions. One is maybe GRMHD is just wrong, are they just two variable? But then another question is it possible that Sagittarius A star is too quiet, even compared to other no luminosity AGN? So I guess my selfish wish is by working with Rubin, I will be able to find some other sources that are very similar to Sagittarius, and then it will help me answer this type of questions. And then I also hope to just get input from this community of what we can do with simulation, what I can help. And maybe there's some synergy between the EHT and Rubin. Okay, so before I go into the technical detail, let me show you a movie. So this is Optical Night of the Milky Way. Let's see if it works. Okay, and now we turn this into radio. So again, it's well justified because we are at NRAO. So if we zoom in, this is the bright region at the center of the Milky Way, lower resolution because of zoom. And if I look at this, so this is what we call the mini spiral. So this is almost resolution, but there's a dot here. And if we keep zooming in and zooming in, eventually we will see a ring. So this is the photon ring around the supermassive black hole at the center of our Milky Way. My original slide actually have a group picture of the EHT, but when I translate it to PowerPoint, it didn't work. So apologize for my colleagues, but this is a result of a collaboration from more than 300 people, and we have more than 20 theorists who studied this source. So just a lot of credit for many other people. So I do want to talk a little bit about how we model the source. This is a little bit different from what Yan-Fei and Amy was saying because we are in different regime. And also because the science we care about it in the EHT. In the EHT, one of the major science goals is to test general relativity. So when we think about how to model the system, we need to put gravity here. We not only just have general relativity, we also put other metrics into our formulation to predict how the black hole shadow will look like from this other gravity. And then we do fluid dynamics. So these are MHD stuff that you already hear. And then we also do plasma physics because we are in a low luminosity regime. These are radiatively inefficient accretion flow. So with this physics, we come up with different methods or tools that we need. With GR, we mainly need geodesic integration to follow the null geodesic, follow how the photon go around in curved space-time. Combining GR and MHD, we have GR MHD that you already hear. And then if you have a lot of computation power, you can also do particle in cell simulation to find out how your electron will accelerate and emit at the end. And then by combining this, we can theoretically predict how the image and the spectral energy distribution look like from our models. Okay, so let me just go a little bit into the first part. So I want you to set up this thought experiment of having a black hole and then you shine a flashlight toward the black hole. This is a thought experiment proposed actually 40 years ago. So because of the curved space-time, some of the light will turn back to you. So when you look at it, you actually see this ring. So back at the time, the terminology photon ring didn't exist. People call it the black hole Dora. But nowadays, we just call it the photon ring. And on the right, this is a modern calculation. Again, the features are very similar, except you have more stuff around this. So these are the plasma in your accretion models. Okay, so using this, we can test general relativity. The idea is like that. So you have your photon ring, you follow the geodesics back to the space-time, and when you change your space-time properties, the geodesic change, and then the shape of your photon ring change. So in an ideal situation, when we can resolve the photon ring and its shape, we should be able to tell the space-time property around the black hole. And I also want to, okay, so there are a lot of work done on this. So this on the left, this is by Johansson and Sotters. They put a quadrupole in the curve metric, so you can see that modify the shape of the shadow. And on the right, this is done by Vera and company. And you can also see, by using different gravity theory, you can predict the shape of the black hole shadow. They are different. So by comparing the observed photon ring with this observation, you can test gravity. And I also want to do a little bit of advertisement that this is an undergrad student at the University of Arizona. He actually study what happened when you screen the black hole too fast beyond spin 1. So at that time, the event horizon actually disappeared and you see the naked singularity. So he got a paper already accepted. Right now he's at the CFA studying AGN and he's applying for grad school the coming fall. So, okay, so let's go to the MHD part. So I think this is probably the most interesting part for this audience, that nowadays we are very good in doing global GR-MHD simulation. There's no radiation, so this is a much easier problem compared to what Yan-Fei and Amy was saying. But there's some advantage here. They are computationally much cheaper. So we can do this type of simulation with many more different configurations, including magnetic fields, black hole springs. And I also want to point out on the right, so there are two major classes of magnetic configuration that we care about. On the left, we have the magnetically arresters. So these are configuration that you have very strong magnetic field got stuck around the black hole, and then they stop the material from falling in. So you can see this very chaotic feature. The plasma really need to squeeze between the field lines in order to fall into the black hole. So this creates a lot of variability. Now, for the things that people are more familiar with is on the right. So this is called standard and normal evolution. So these are standard turbulent accretion disk driven by the magnetorotational instability. Now, but for this scenario, we are talking about radioactively inefficient accretion disk. So these are thick disks, as you can see here. And by turning, by running this simulation, we can then do the next step of setting up a virtual screen in your computer. And for each pixel of your virtual screen, you trace back that to your GLMHD simulation, and then you can obtain movies like this. So this is a typical ray trace image from this your GLMHD simulation. The resolution is low because of zoom, but there is a photon ray, there is a jet, and then there is a body of the accretion disk. Okay, so by comparing this type of simulations with observation, then we can constrain gravity, learn about the plasma property around black hole, and all of those things. This is another movie. It's an old one, but I dig this out because it actually shows you the light curve of the simulation at different wavelengths. So blue is X-ray for this model is very smooth, but then for radio and EHT observation and infrared, they are much more variable. So again, these are things that we can compare with observations. All right. I didn't prepare too much about the plasma physics, but the idea is there are a lot of plasma instability that can accelerate electrons. And depending on your electron distribution function, they can affect the tail in your spectral energy distribution. So by assuming some electron distribution, we can again turn. Let me try again. Is it supposed to be movie?
Yeah, okay.
Can you click that? Yeah. You can turn the GLMHD simulation into these spectral movies. So again, now you can compare the variability at different wavelengths with observation. Okay. Right, so I only spend 10 minutes. So let me go through the EHT observation a little bit. So we don't just look at Sagittarius A star and M87. We actually observe many AGN, the brightest one, the larger one, the closer one. But it turns out among all of these AGNs and supermassive black hole, we can only resolve Sagittarius A star and M87. So that's the reason these are the main source that we study. So even though they are the biggest, they are still very tiny. So usually we just say it's equivalent to the size of putting a donut on the surface of the moon. But this is not super useful because I actually don't know how far away is the moon. So a better way to say this is imagine you are looking back at my office in Tucson, the tip of my pencil. This is the angular resolution we are talking about to resolve the black hole event horizon. All right, so this is very small. So in order to resolve this, we use this technology called very long baseline interferometry. Each radio telescope, I'm a little bit scared to describe this because I worry that some local people will point me out, I'm making mistakes. But anyway, so for the radio telescope, each radio telescope is only a single pixel antenna. So they are sensitive to a portion of sky. And now you imagine in the region that you are sensitive, there are different subfeatures. So each subfeature will send a radio wave to your telescope. In this picture, both telescopes receive the wavefront at the same time. But now if you have another subfeature from the same region of the sky, the wavefront arrives to the telescope in a slightly different time. So by capturing the wavefront and measuring this delay, you are able to have a very high resolution reconstruction of the image. So this is the core of the technology. Right, so this is our array. In 2017, we got 8 telescopes, and then we keep improving our instrument and add more telescopes to the array. And this is actually a observation done in 2022. This is 4 petabytes of data on the table, just from the Arizona telescopes. So because we are into interferometry, so we do not just take pictures directly of the black hole. Instead, when we have a pair of the telescope, they form a baseline, and that baseline tells us the Fourier, your frequency domain information of the image. And as the Earth spins, they actually trace out the visibility data in this Fourier domain. So if we have enough telescope, we can fill out this Fourier domain, then we can just do an inverse Fourier transform to reconstruct the image. But unfortunately, we only got 8 telescopes, so there are a lot of holes. So because of that, we rely on image reconstruction algorithm to get us the black hole image. So this is not super important, but then the important thing is because we have so many holes, our image reconstruction are not units. So this is also a movie. All the image you see here, each of them is a weighted reconstruction of the black hole. They all agree with the data. So one simple way is just average all the possible reconstruction and then conclude that we have a photon ring. Yeah, I guess if there's too much delay. But in the EHT, because we worry about this is not a photon ring. So what we did was to use a clustering algorithm to classify the black hole image into multiple categories. And then at the end, we conclude that most of our reconstruction, a ring-like structure. So by doing so, we can put some error bar in our final measurements. Okay, so this is the EHT observation. Now let's go to the interesting astrophysics. The bottom line is very simple. We are just comparing simulated image and spectrum with observation. So the way we do it is we build up a simulation library. We use GL-MHD simulation to obtain the dynamics, to obtain the things that are moving. And then we do a parameter survey on the thermodynamics because we don't really know how to accelerate electrons. So those become parameters that we can tune in our simulation library. And then we just look up constraints that are more or less independent from the observation. And then we compare the different constraints with the simulation library to rule out the models that doesn't work. Okay. So this is a list of our simulation library. So we use many different GL-MHD code, and then we have different configurations. For example, Phoenix is here is contribute to a wind fitting model. So this is not a standard accreting donut, but instead people model actually Sean Westlar's work. So they model if you have this S star orbiting around this galactic center, and you get wind from those stars hitting the central black hole. So this is in our models. Okay, so these are some of the visualization of our model. So we get the standard anomal evolution. So this is the turbulent disk, the thick turbulent disk, and then we have the magnetic arresters, the wind fittings that I just mentioned, and we also have tilted disk in our model. And using the GL ray tracing calculation, we get image like this, and then we can compare them to the observation. So this is again a movie. I hope that this works. This is one of the model. Magnetic dominate certain electron temperature, certain black hole spin, certain inclination angle. But just a single movie is not enough. So we change the inclination. All of these inclinations are possible. And then we also allow the black hole speed to change. So each row here corresponds to a different GL-MHD simulation. And then we also allow the electron temperature to change. So alpha is a parameter that controls electron temperature. And then we also have the magnetic dominant accretion disk and the turbulent accretion disk. So this is a subset of our simulation model. All right, and then we compare this very big library of simulation to different constraints. So we have constraints come from EHT. So for example, the size of the photon ring from our observation. We have the visibility, amplitude morphology. We have some fitting parameters. But then we are also using other observation. We have long frequency radio observation. We have fixed rate observation. So we compare this gradient with the models, and then we rule out the model that doesn't work. But then we also have variability constraint, which lead us to the variability crisis that I will talk later. So this is again our simulation library. If we start applying the different constraints, it will take a little bit of time for this to load. So first we apply the EHT size constraint. because we normalize the parameter based on EHT your value. So it's not too surprised that the size constraint is not too powerful. But once we put in the shape and the spectrum, you can see a lot of models got ruled out. So at the end, if we compare all the time FH constraint with our models, only 2 models survive. So these are our best bet models. This is another visualization of what the models survive. We call this our pizza pods. So the different radius here correspond to different electron temperature. These are different inclination, turbulent disk, magnetic dominant disk, and different spin. And you can see only 2 high spin model with very low electron temperature and phase on actually survive. Okay. So far so good. It seems we are pretty good in modeling the FH property of Sagittarius A star. But the problem comes when we okay. So this is actually a movie of the best bet model. So based on our best simulation, this is how Sagittarius A star look like. Okay. So far so good. But then the problem comes when we want to compare variability. So this is a low quality plot because I took it out from our early draft. We didn't include this in our publication, but I want to show you because for our GRMHD simulation, although we have less physics, we don't have radiation, but this allows us to run the simulation for much, much longer. So one of our simulation actually goes to 100,000 dynamical time scale. So for Sagittarius A star, this corresponds to, let me check, this is hour. So this corresponds to a few 100 hours of real time. And if you apply this to supermassive black holes like M87, this is 3-4 years. Okay, so with this simulation, we can really simulate time scale of Rubin time scale, right? And this is our modulation index. So this is just the standard deviation divided by the mean, and you can see when we use different integrate time, they have different values. But then the key point here is the dashed line. This is the observation. So if we fit a damn random walk to the observation, this is how the modulation index should look like. And all of our models are just 2 variables. Okay. So this is another visualization showing that all the models are 2 variables. The gray bars here come from the historical observation of Sagittarius star. For the fit that we care, for the actual observation of the EHT is on the very low end. So if we look at the turbulent disk, it's not too bad. It's slightly more variable, but not too bad. But remember when we compare the time average models with observation, all the turbulence disks actually got ruled out. So now if we look at the model that actually fit, so these are the magnetic dominant model, they are much, much more variable compared to the observation. So this is the variability crisis that we are talking about. And this is another visualization, again, the pizza plots, and you can see just a single variability constraint rule out all the math models. So we are in trouble. We actually don't know how to satisfy all these constraints, including variability. All right, so the conclusion here is by comparing our very large simulation library with observation, just looking at the time independent stuff, we can conclude Sagittarius is likely to be a 2-temperature plasma. The accretion flow is pole-gray and dominated by magnetic field, and it's a little, the edge-on model disfavor. Okay, so but then the problem is Sagittarius is less variable than our simulation. Okay, so all right. So the summary. So this is my second slide that I show you. So hopefully after this talk, you know what it means by we are pretty good in modeling the time average stuff, and I also hope you get a sense of the simulations are 2 variable. So we actually don't really know what to do. There are multiple groups trying to attack this problem. The Illinois group is trying to put resistivity in their model to smooth out the flow. A Germany group is trying to put resistivity. The Arizona group, we are trying to play around with the plasma model. But anyway, so far the models are still 2 variable. And with that, I will just leave this as a discussion, and I want to hear input from everyone. Thank you.
Thank you. Questions?
ask the radio astronomer question. So, can you learn anything from polarimetry? I mean, I know that Sagittarius stars high circular polarization and very variable there.
Yeah, so we are working on that, but I'm not allowed to tell you.
Oh, okay.
But the paper are coming out soon.
Okay.
Any other?
Just a small point, perhaps. You know, you mentioned this thing about this student working out, I don't know, imaging for ring singularity or whatever.
Yeah.
My recollection, of course, is that for a real astrophysical black hole, the inner horizon, the ring singularity are all highly unstable and are unlikely ever to actually form in reality. Yes?
Yeah, that is true.
So
And
what's the point of working out stuff with a ring singularity?
and then your even numerical relativity simulation showing no matter what you do, it's very difficult.
Even classically, classically, it's unstable. Yeah.
Yeah, exactly. But I think the motivation here is because we now actually have the image of the black hole, and in our MAT7 we actually said we rule out the Lake singularity because of a previous paper. But then we looked into that paper and the result was wrong. So that means our conclusion is not really valid. So the student look into it more to get the correct calculation. So if you look at, let me go back many slides. Yeah, so I agree with you. I guess when we work on it, we don't even think that Lake singularity exists. But in order to make the statement that EHT result rule out the Lake singularity, I think we did this study. So that is the main point. On the other hand, the thing I want to show you is when spin is larger than 1, the photon ring actually open up a gap. So this actually translates into a signal to noise requirement, a dynamical range requirement in your observation. So right now, our dynamical range is about 10. So it actually doesn't really rule out this just from the observation point of view.
Okay, I'm sure I can appreciate that. I guess my reaction would be, so I understand that that's reasonably motivated, but given that it's so unstable and likely to form, you might as well also rule out a line singularity or singularity made of a bunch of dots or many other varieties of singularity, because they're just as valid as that.
Well, I'm not sure. This is the Kerr solution. It's the same solution.
But it's, yeah, I understand. But even Kerr himself says the interior solution is invalid.
Well,
yeah, I've seen Kerr give talks on it.
So I agree with your point. We know it shouldn't exist, but in order to say the EHT rule out, this calculation is required.
Okay.
Other questions here?
So, if I understood correctly, right? So what we see of the EHT is an average of all of the models. But if I understood correctly, then once you consider other constraints, no model is consistent with the data.
That's right.
Should we be worried about that average?
That is a good point. So the way I see this is the variability is a higher order effect, right? Because the FH, it depends on the space-time geometry, how you do ray tracing. And the variability really comes from this fluctuation in your simulation. So I think, yes, we should worry, but on the other hand, our guess is there will be ways to fix the variability without changing the image too much.
Yeah, just another question related to this, like MAT7 is fine, right? I think because of the typical variability timescale for MAT7 is too long. So when the EHT published the result, right, there was no such message. So all the math model works. I'm just curious if you want to test the same thing for MAT7, how many years you need to wait to see whether the variability in MAT7 also is less or just carry sense?
I don't have that number for you, but I agree completely that MAT7 didn't have this problem because we didn't look at the variability. So if we have a long enough light curve for MAT7 and we compare that, it's possible that we will see the same thing.
Someone else?
May I ask one question?
Yeah.
If I'm allowed. I'm very curious. May I ask this question? Simulation seems very useful. I'm wondering whether how feasible or challenging to imposed external effect, not the disk itself. If the, for example, disks actually have a companion, like the binary, or the Christian disk itself is actually recoil, then to have an, the remnant motion after, to take that out. I mean, will that cause any changes in the structure of the distribution of the disk itself? And even though you're not predicting it, the observable EM, the signal, but can you actually predict the variations of the accretion rate or things like that? Is it feasible, or we are still in the regime where we can't really simulate this external effect?
I think it really depends on the parameter. You say a companion. So if the distance is very far, then I can imagine you put an external force in your GL-MHD simulation to just give you all the perturbation, and then you can simulate that. But if the companion and the black hole are too close, then maybe you really need to put in the companion stuff. So it depends on the regime. So I do think there's some regime that we can start using our existing code to adjust.
Yeah, I may have a follow-up question for you later. Yeah, okay. Thank you.
Thank you. Someone else? Okay, so thank you.
Wait, one more. So question from online. I'm going to read it. What are your thoughts on combining GL-MHD and PIC simulations to model variability? Could you also elaborate on the either ETH-ER database for NGEHD probable targets?
Okay, so these are all excellent points.
Yeah.
So there are actually people working on doing particle in cell simulation in a general relativity background. So, but the problem is that the scale separation is too big, right? So you have the gyro scale that is tiny, and then you have the gravitational, the black hole scale that is big. So you can still make progress by artificially adjusting your constant to bring down the scale separation, and you will still learn something from that. So yes, you can make progress in that way. But if you want to do the actual problem, just like normal PIC, you will face the dynamical range problem. In Arizona, we actually have a grad student trying to work out a different approach. So this is gyrokinetic in GL. So you integrate the gyro motion in order to speed up your calculation, and the student already derived all the formulation, and it seems to work. So I think that just the first question. And then the second question, I'm not sure if that's about simulation library or the observation candidate. But for the NGEHT project, we did look into the brightest AGN, no luminosity AGN that we can find, and then we are looking for candidate that we can observe.
Yeah, that's exactly the point that the person asked this question.
Yeah, so there's a paper on that. I can look that up and then.
Yeah, you can follow up on this slide.
Okay, thank you.
If there aren't any other questions, we can conclude here. Okay.
Thank you.
So we maybe logically would have a final discussion tomorrow, but I think the concern was that people would need to leave and not be available for that. So we have on the schedule a final discussion now. I don't know that we have.
Is it right now, or do we have a break? We don't have a break? We just go straight into discussion.
We could have a break.
Oh, that's fine. I'm good to go.
Yeah. So, I think I don't have anything planned right now, Niel.
I have one thing which we're going to talk about, and just gathering any necessary supporting data sets before we actually have Rubin data falling on top of us in 1.5 years.
Yep.
And I can say some words about the drilling field specifically, and I think equally important, and perhaps even more important, is the main survey. And I don't know if anyone wants to say any words about that, but that's something that we probably should discuss.
I mean, why don't you go, and then if anybody has questions about anything that we've talked about in the previous two discussions, you're certainly welcome to
We
ask.
don't want to dictate, though. If anyone else has anything they want to talk about in the discussion session, please raise it now, and we can hash through anything.
I mean, I have one question actually, based on the earlier talk in the simulation. Mentioned that the mixture of the intrinsic variability versus the disk, the instability, light from the UV light from the disk photosphere versus intrinsic, the variability in the midplane or the accretion disk. I mean, in theory, we can control, but look at the pulse spectral density, it's a Paul law that it's a scale free. So do you think we will be able to clearly tell, okay, which frequency we could set as intrinsic variability versus beyond which frequency we'll say like, this instability, something like that. Am my question is clear, or I mean?
Yeah, it's clear. I mean, I don't know. I don't know is the answer, but again, like if we think that the intrinsic variability is on a thermal time scale and the right, and then we can certainly see the frequency scale of the reprocessed variability by looking at the X-ray light curves, right? So, I mean, obviously not with LSST. So, yeah, I mean, yeah. So I guess if I'm thinking like we have Swift, then, you can look at the X-ray and then, but I guess if we have an intuition of what sort of power law we get from the X-ray versus in UV or optical.
Yeah, I mean, the theory can clearly draw the line. It would be very useful in terms of the observers to actually, interpret the data. But I'm curious whether it's really feasible or not. But I was wondering.
I definitely think it's feasible to gain an intuition. I mean, like I think a big thing, we would need a much wider parameter study, right? Because one simulation just won't apply broadly, right? I mean, likely. So, but I think it might be possible to see a cutoff. Yeah.
Thank you.
Again, it's hard because you need longer timescales too to be able to look at really high frequency, but or really low frequency. Yeah.
That's it for me.
Anyone else have anything they want to raise? This is a good opportunity for anything the science collaboration wants to talk about. If not, I can talk about some things and we can throw ideas back and forth.
So maybe following my own talk, I want to get input. So I just wonder, if we build very big simulation library, will that be useful? And if you will, then what kind of library that people want? So I guess for alpha, there's it's very expensive, so we can't really do that. But for non-luminosity AGN, I think we know how to do that.
I mean, I guess
happy to talk to you offline about
Okay.
I mean, I'll just say one initial reaction. I mean, and I think Yanfei, you mentioned this. People use the Shakur Sunyaev just because it's there, not because it's especially good, right? And you mentioned this possibility of somehow make. I guess here's the thing. I have, I'm sure, like many other people in this room, tried to make comparison with better disk models, and I go to the various scientific papers, and they have lots of nice diagrams like the ones we saw in the talk with arrows going everywhere and density grids and everything. And I do my best to make some estimates from those, but it's it's very hard to get much concrete. The papers, unfortunately, as an observer, never really give me what I need to make a comparison with observations. So I can think of a couple things there. I mean, one valuable paper would be, for the simulation people, and again, I don't work on SAG-A star, but it's probably equally true for SAG-A star, just to sit down with observers sometime and just write a paper where you spray out all the things observers actually want. We say, well, this is what we want you to compute, and this is what we want you to compute, and you write an entire paper, giving all the diagrams and the measurements people would actually want. That could be one approach. Another approach would be, if you could ever actually release a disk model, and then observers, in some sort of a fixed format where all the measurements are there, all the data are there, and then observers could go and simulate observing that disk, the way they want. And this would be like what we do with Shakura-Sunyaev disk, but you do it with a better disk model. So are those things practically possible, or are these ideas foolish for some reason on the theoretical side?
No, not at all. Actually, that's what we want to do after the simulations. So the thing that is missing, if you want to have a better equation disk model beyond the Shakura-Sunyaev disk, is the raw magnetic field.
Yep.
So the magnetic field is complicated because you do not know how much of the magnetic field, or basically magnetic pressure, will saturate compared to thermal pressure. Thermal pressure is easier. You can estimate from temperature density. So right now, we really just need a more simulation library to get an idea, for example, how the magnetic field change the function radius and the m dot, and people do for EHT. EHT have all the simulation libraries, so you can compare all the models. So that basically we try to do more simulation of the function of m dot and the black hole mass, and get idea on for example, the level, the magnetic pressure, the function of distance. And more important is we care a lot about the vertical dissipation. Like I mentioned, the X-ray and the UV is all controlled by where you put the dissipation. If you put the dissipation in the upper thin regions, you get X-rays because you heat up the gas. If you put all the dissipation in the upper thick regions, you get the thermal emissions. So right now we have a few simulations, but we want to have at least a double, so we can actually get a better idea. But there are people actually already trying to do that. For example, Mitch Bigman has some model where if you actually put the magnetic field in some like magnetic elevated disk, and then you get actually some structure, a function of distance, which is ultimately what you want, right? You want how the disk scale height or temperature, a function of distance, and m dot for different black hole mass. But all those models just missing is basically the dissipation. So we basically in the process try to get idea of the dissipation from the simulations. Then we can basically try to improve those models.
Right.
And then we can, not basically what you want, and see whether that actually fits any of the observational properties or not.
Right. So if I understand you, just to paraphrase that in like a sentence, are you saying that it's premature right now to try to do such a thing because you need to make more progress on the models before it's even useful to release such a thing to observers?
Yeah, it's just we given the few simulations, we are not trust. I can put something, but I do not trust that the evaluate for the particular simulation we have done, but I do not know how general it will be if you have different m dot black hole mass. So I do not know. I mean, I do not want to promise like how many years we can get there.
Well, I can tell you that, I mean, I've been requested. I mean, I used to go to conferences with Omer Blaze, 30 years ago, literally 30 years ago, back when I was a grad student, and these things were just around the corner, and they're still just around the corner. And so I don't know how to interpret that, but I'll take it in good faith that this is very difficult.
Now, right, we have already a few for 3D radiation MHD, so we have a few examples now, which doesn't exist like 30 years ago,
right,
when Oma was still young. Yeah. But yeah, I'm still working with Oma, so that's good. This is sign things continue.
So
another thing that, oh, sorry.
I was just going to say, I think this is a really appropriate place to have this conversation because I think radio jets are really perhaps useful for probing some of these questions, right? And so, Mark can, disagree with me here, but I mean, I would remind people that like less than 4%, maybe less than 1% of SDSS quasars have jets. And that's a great mystery to me. Like what in the world causes an object to have a jet or, not have a jet? And specifically when the difference in those objects outside of the radio is 0, right? There's absolutely no difference in the accretion disk for objects that have jets and no jets to first order, right?
Well, the X-rays are brighter in the jet.
Right, so, right, in the accretion disk, not the corona, right? But
No, the corona is actually brighter, but anyway.
I said in the accretion disk, I'm not talking about.
Oh, okay, fine.
So the, so the question I always wonder is, are the jets mad disks and the non-jets sane disks or something like that, and things are otherwise the same, but the question is, can we use this really, unique fact about radio jets as a probe of really accretion disk physics?
I guess my initial reaction to that question you raised, I would say M87 could be a mad disk. I don't believe 3C273 is. It's a bloody quasar.
Why does it have a jet?
Well, I don't know, but you can't try to tell me it's a mad disk because that accretion is not being stifled.
Well, without giving too much away from my torture map, I think there's going to be some interesting stuff in comparing radio variability and optical X-ray variability. We can get suddenly the optical variability we can get from LSST. Comparing those light curves might tell us something interesting. Although frustratingly, it's still fairly inconclusive from what I've done so far. But there may be patterns that emerge in a large enough data set.
Yeah, just wanted to mention that the data set, the stripe 82 the quasar, I just happened to do some exercise with the cross match with the VLAS, and we currently VLAS at that time has only 2 epochs available, but now it has 3 epochs. The initial investigation, radio is not strongly correlated, but there is an interesting trends like over the different epochs. The radio is the variable. It's a varies in terms of cores are brightened or cores are dimming versus a jet is brightening, jet is the dimming. So that is somehow correlated with the optical variability in terms of the amplitude and the time scale. But at that point, sample was not that many. But I'm just it's worthwhile efforts to actually look into that direction. If you have a multi-epoch radio, the survey data, comparing with the QSO, variability, see if the radioactivity is how is it correlated with the optical and the other wavelengths.
So I mean, the only thing I'll say it's really dangerous to assume that the radio is from a jet.
Yeah.
You need to know that it's from a jet, otherwise I assume it's not.
But not only the jet system, I mean the core, there's a single core itself. That core itself is a vary. I mean, of course, yeah, there could be potentially the smaller, smaller jet inside. We don't know yet, but.
Right, to some extent, right, might matter the black hole spin and the spin of the material, right, being accreted.
I think there's no evidence that spin matters at all. I mean, which is surprising, but I mean.
But you mean observational evidence, right? But it's
Yeah.
really hard to probe the spin.
Is, but there are ways, and I mean, which isn't to say that there aren't individual wacky objects that have high spin, but I think in the ensemble average, there's no evidence. Well,
yeah, my feeling is that spin is probably one of these necessary but not sufficient conditions.
Yeah.
that
Actually,
can be spinning but not produce jets.
Well, you need a tool.
I very like to go ahead.
I mean, theoretically, to get a jet in the tool, you need a spin, but also you need a net broader magnetic field.
Yeah.
All the math simulations actually put very strong broader magnetic field near the event horizon to begin with. But the big question is that can you actually advect a lot of broader magnetic field from the galactic scales all the way to the black hole, which will be very hard. And particularly the well-known theoretically for lower m dot case, the advection is more efficient, but for quasar radiative efficient disk, the advection is much less efficient. So it will be much harder to advect the magnetic field to the black hole, which is something also we see in actually binaries, right? During the state transition, you always see like in the radiative efficient thin disk soft state, you do not see a jet. But in the hot low accretion rate, when the disk is thicker pop up, then you see a jet come out. A common explanation is because you can get the magnetic field to the black hole much easier when the disk is thicker.
but you still then only see the jet like some tiny fraction of the time.
Well, that's why maybe in the galactic scales, it just in AGN, it's very hard to keep providing the magnetic field you need. So maybe the certain special conditions you produce the jet, which is a small fraction. I don't know, that's just one guess.
Well, isn't it also a question of time scale as well?
Well, that relates to the difference between the thin disk and the thick disk. Thin disk, the interaction time scale is much longer. So it's very hard.
Right. Yeah, right. But when we think about the difference between soft and hard states in X-ray binaries, we're talking about things that happen over time scales of days, and or perhaps weeks. And if you're talking about things that happen in AGNs, you have to scale up by factors of 10 to the 7, 10 to the 8th in mass, and similarly in time scale.
Sure, but I think statistically, if you translate the time scale to a statistical samples, right? I think the scale.
Yeah. And actually, this gets back to one point that I did want to bring this back to, is that with M87 and also with Sagittarius A star, you're kind of working on two very low Eddington ratio objects. And yes, they're very different objects. And yes, they have very different masses, but they're very low Eddington ratio objects. And so I guess the concern that has to be in the back of your mind, I guess, is that this is one end of the parameter space, and the parameter space has many dimensions. Am I right?
Yes.
Do you hear us? I lost.
We can hear you. I think it's his side.
Anyway, other stuff you want to carry on with?
Do you want to get on to LSST, Rubin stuff? Okay, I mean, I'll keep this pretty concise. I sent you a couple of slides, Ilsang.
Oh, okay.
You can put those out. And again, this is not anything I've prepared. It's just throw open discussion. So
can you tell me which one it is?
Well, it's in your email box. It just arrived 5 minutes ago, something like that. It's just some quick slides, so we have something to point at and talk about.
Yeah, I'll point at.
You have it there?
Yeah,
Okay,
it's
great.
This is right.
Yeah, that's it. Yeah. So again, this is just on the topic of making sure we actually have good data in hand, because when all these Rubin data are falling on top of us is not the time we're going to want to have to deal with that. And so I'm going to speak specifically about the deep drilling fields a little bit. And again, I certainly think we should have a similar discussion on the main wide, fast, deep survey, although I think someone else should probably lead that discussion. So I'll just remind you, of course, that there's a lot of solid angle in these deep drilling fields. Okay, each one of these little things is 10 square degrees, okay, except Euclid deep field south, which is 20 square degrees. So you got 60 square degrees there. We do not have those 60 square degrees under control. I think not as many people appreciate, and Mark appreciates that, but fewer people than perhaps should actually appreciate that. Let's go to the next slide. So these are the multi-wavelength data sets, and the large black circles show the Rubin field of view, okay? And here's Euclid deep field south, which is at a somewhat different scale than these other ones. And I think, Mark, you made these plots, I believe, right? I think these are marked.
The ones on the left, at least, yes.
You made some of them, yes, okay, right. So, yeah, and so basically, you know, the underlying grayscale shows Spitzer data. And of course, Spitzer was so good at pounding out solid angle, and Mark very aggressively used it to get full coverage for this one, and this one. And I believe Cosmos has some wider field Spitzer data. They never got the full.
Yeah, so those magenta circles, the HSC pointings, those are now.
They have Spitzer for those. Okay, so Spitzer's not too bad. Okay, and I don't know how much. Well, for Euclid Deep Field South. There'll be a lot of Euclids, so hopefully that, yeah, okay. Fine, so that's Spitzer in pretty good shape. Now, at the other wavelengths, we're not as in good shape. For example, you look at the really high quality ground-based near infrared imaging. That comes from the video survey, for example, which is this blue region there. That also is the SERVS region. That's also the region where we got the X-ray data. We all said, this is the best area. It's too expensive to get the whole thing. So let's get as much as we can, okay, of the best stuff. And the same thing was done in LISS-1. And the same thing was done in Deep Field South. But for example, this XMM SERVS survey, which was a huge effort, gave us 13 square degrees in these three fields, which is actually less than half of the solid angle in these three fields. And so maybe as AGN people, we don't really care. We're just going to do the best areas and just throw everything else away. Or maybe we need to actually do something to prepare out here, because it would be a shame, you know, to let half of the data just really not be very useful. Okay, so that's one point I wanted to raise. So I don't fully know the answer here. I have some ideas, which we could talk about, you know, involving just better analysis. I mean, I think it's probably too late to have a lot of additional data gathered by the time the Rubin data come. Okay, just knowing how, but I think we could do more effort actually analyzing the data out here for what we have. And so you could someone could put in real effort. You know, it's not going to be as enjoyable perhaps as down in here where we have super great data, but it will be extremely valuable, you know, to do good AGN selection out here and all around there and all around there. And may I ask, has anyone done that? Done a good job at AGN selection out in those regions? I'm not aware of anyone who has. And again, you're not going to be able to do as well as we did down in there, but you could do something. I mean, E-Rosita data will be coming soon, so you could use E-Rosita for the X-rays. You have very good Spitzer, okay, from Deep Drill. You have, I don't know, what's the best radio mark over these wide areas? Just go to VLASS, or like you can't even.
Yeah, so apart from the WCDFX, which we do have a deeper survey in, which I need to get out.
Over 10 square degrees?
Yes.
Oh, that's good.
Over 10 square degrees. But yeah,
Neil,
the other fields. Cosmos.
Can you define good?
Well, good. Well, I mean, the best that we have, the best that we have in hand, because that's what we're going to have to work with.
But I mean, it probably is useful to actually quantify that as number of AGN per square degree or something.
Yeah,
like
I understand.
That, right?
And that you'd have to, yeah, and I have not done the work to know those answers right now, Franz, but I just want to know what is in our hands that we could do something with.
So as a guess, having Roberto SF, for instance, has done some selection over wider fields. Paola has done selection over wider fields with variability with SCDs. Mm-hmm. You know, they're getting something on the order of 100, 200 objects per square degree, I think.
Yep. That's, well, again, we got in down in these regions, we have about 1,000 per square degree in the good areas.
Exactly.
So yeah, you might be able to get a half or a third of what we get down in the really good areas. But again, that's a lot of solid angle, and having something there is a heck of a lot better than having nothing. And right now, in my assessment, we have nothing. Do you agree with that, Mark?
Yeah, we don't have
it's just wilderness out here, as far as I'm aware.
There's a few DES pointings.
Yeah, there's data, but no one's actually found EGNs and made catalogs.
So as I just said, Roberto has a catalog that covers these wider areas.
This is your whole sky thing?
No. This is for foremost, right? We've been actually going through all of the DECAM data plus VHS plus the 9-year WISE.
Okay.
Data with actually the same software that Shadak was showing today to do SED selection.
Out in these areas?
Well, with the entire southern sky.
Yeah. Okay. The whole southern sky. Okay. Are you using, like, for example, in these areas that there is the very high quality Spitzer data, for example?
No, so that's not, but that's something that it's basically, it's not a major modification to do, right? So we're doing the Viking regions, which are significantly.
Yeah, so yeah, Franz, to answer your question, and I guess what I was hoping for is something that actually, I mean, the data that out in these regions are a heck of a lot better, you know, than your typical random patch of sky, even though they're not nearly as good as these central parts. And so I guess I would hope we would do something that would utilize the very high quality data that are there to at least do something. And yet
Yeah, I mean,
you have methodology, we have methodology to do it too. We can take what we did in here and do it out here, just not as well.
Yeah.
Yeah, the trick is mixing and matching photometry, and you know, you kind of have to draw the line somewhere, just to sort of make things homogeneous.
Yeah. So anyway, that's something I just wanted to talk about. Yeah, go ahead.
So just to understand your point, right? So your point is that we should know the AGN there, so we can jump immediately into doing science with LSST without having to develop the selection with LSST.
Part of it, yeah. Okay. And if you have them, you can maybe start getting some redshifts or photometric redshifts. I mean, once all the Rubin data is falling on top of us, are we really going to want to work out photoz's out here? I mean, and you know, you make all this photometry nice and pretty. I mean, I don't want to do it at that point. I want to run in and do Rubin in the good areas, but I'd like to be able to utilize these areas too, to some extent.
Right, but so that's okay. That assumes that the Rubin data is not important.
Well, the Rubin data are important, but I mean, I'd like to do something now, and then of course we'll do it all better with Rubin. But again, just from my experience, I mean, I thought this wouldn't be too bad. We'd knock it off in a year, and you know, I came to appreciate that while there was a lot of great data, even in these regions, people didn't have photoz's, didn't have tractor catalogs. I mean, it was just the data were there, but it was a mess. And so just to do XMM serves and characterize this, I mean, Fan spent a year just getting the data under control. And so it's a big job, but it's extremely valuable because we can generate pretty good AGNs out there. At least have something to work with.
Yeah.
That's the idea. Yeah, I agree. Rubin will make it all better. But you know what you do is you write a tractor code now that handles all the multi-wavelength data. And then when Rubin comes, you just plug it in. If you're not ready, you have to do it from scratch.
Right.
You're only going to get paid for that when there's Rubin data.
Was that?
You're only going to get paid for it when there's Rubin data.
Yeah, that is a challenge. Yeah.
So,
yeah. I mean, Chris, you had some ideas about that, right? About doing tractor photometry.
Yeah, it was about, I mean, it was very large scale LSST wise force photometry. But in practice, you could do it on smaller fields. Thing is that, and I think I haven't taken a look at the data preview in depth to see like what you need to use from it in order to generate. But I think you said you had already done it on one of the deep fields, right?
Which
you had used tractor.
Fan has tractored ISS-1, and Christina Nyland, working with Mark Lacey, tractored these two. That's where the tractoring comes from right now. Okay.
So Neil, the reason we don't have the data is because data was taken, but there's someone who actually working on the data, processed it and created a catalog and cross-matched to create a massive catalog for the wider area, or you simply...
Well, okay, so different groups did different things. Okay, I can speak to what I did. I mean, I only ever had XMM data in the good area, so that's what I did. Mark's the one who had data over the whole area, so he can explain why he did what he did. Well, why didn't you do everything, Mark?
I ran out of time and funding.
Yeah, ran out of time. Exactly. Ran out of time, ran out of money. That's the right, usual thing.
So if someone actually make a lot of efforts doing some homogeneous photometry using the Drexel or whatever available and create a massive catalog,
it'd be very valuable.
I see.
It'd be very valuable also. I mean, I don't think that somehow the Galaxy Science Collaboration has it either. I don't think anybody has it. So anyone who does it, I mean, we'll get the AGNs. There'll be enormous numbers of galaxies, which will characterize as well. I mean, many millions. And otherwise, all these areas are just, as far as I can tell, they're not really going to be all that usable. So that's one. And I've actually presented the best case. You want me to tell you the worst case now? Here's the worst case. How about this field? No one said anything about this field's a mess. Do you agree with that? I mean, there's very little systematic analysis of the data in this field.
Trying to remember whether there was ever any Spitzer data taken on that
I think
field.
there
That
was.
might
I
be-
think there was a
They
large
gathered- There's a
program
lot
for
of Spitzer data.
Okay.
But I believe the person who gathered the Spitzer data then went off and worked for Facebook.
Yeah.
So I
Sure
don't
what
think
state
those
that's in,
data,
yeah.
I don't think those data have ever been, do we have Spitzer catalogs in here? Are you aware?
I need to find, because they did do a whole, Spitzer wide reprocessing at some point towards the end. So it may be that is processed, but I will take that as an action item.
Yeah,
to
it's
check.
a good thing to check. I mean, do we have a good radio survey in here? Do we have, I can tell you, we have no X-ray.
Yeah,
There's
it's
no X-ray.
too far south of the VLA. So
Rosita.
That's cat
Yeah, you have E-Rosita when it becomes public, yep.
Yeah.
But there's this field's a total mess. And I mean, are we just gonna write off this field for AGN science? That's 20 square degrees, so we're just gonna throw away? I don't know. I mean,
The Euclid AGN people will do something.
in the next year and a half?
Well, when the Euclid data comes along.
Okay.
There's going to be people looking at the Euclid data.
I hope so. I mean, again, it's a long road. I mean, again, it took us years to get these under control. So I just don't know how you're going to pull that off on any reasonable timescale before the AGN data are coming. So doing AGN selection in this field, at least do something, would be very valuable, because as far as I'm aware, there's nothing. There are data there, but no one's actually done anything with the data.
Niel?
Yeah.
It might be useful to kind of motivate this scientifically. And so, right now you have, something of the order of 10,000 AGN in XServes. Is that right?
Yeah, 10,200, yeah.
Right, and that's including obscured AGN, unobscured AGN.
Correct. Yep.
And so, those will be pretty well characterized. In effect, you're saying, like, let's say a third of those are type 1, right? So you'll see some variability, et cetera. So we're talking about maybe 3,000 right now. And if you were to harness the other portions of the LSST deep drilling fields, you might get, again, of order 10,000 total. Maybe actually more.
Probably more, because Euclid Deep Field South would give you a ton just by itself.
Yeah,
you probably triple. So you could triple your numbers of type 1 AGNs. That's a pretty good thing. So anyway, that's one thing I just wanted to mention, that there's a huge amount of work that still needs to be done to get the deep drilling fields under control. Another point I'll make, and again, I'm sure Franz will have comments on this, is spectroscopy. Most of the AGNs that we know of right now in these fields do not have spectra. They have photometric redshifts. That's all they have. And so there are efforts being made to improve that. There is the Devil survey being done by the Australians that is getting large numbers of redshifts. It's not extremely deep, but it's something. It's a heck of a lot better than nothing. And the great advantage of that one is it's real right now. I mean, their data are taken, and soon, I believe, will be released, and we'll be able to use all those redshifts. So that'll be a big improvement. But then, of course, things will get much better once you have moons, once you have foremost, once you have blanking on the other one, the Japanese one, PFS. Once you have PFS and DESI, once you have those things will get a lot better. But right now, when we go to do AGN science for all the AGNs of the deep drilling fields, these sources are not going to even have spectroscopic redshift. They don't even have spectra at all. And so that's something that obviously needs a lot of improvement. We're trying. I've requested just recently, Franz knows, I've put in about, I've put in 12,000 moons targets, aiming to get spectra for all the AGN, so we can do a lot of this, but that's not going to be there when Rubin starts. And so
I guess the other caveat, Niel, is that most of the surveys you talked about are actually only covering the inner portion of the deep drilling fields.
Yep, that's right. And most of those are down in here in the prime areas. Out here, it's going to be much harder. But again, if you select AGNs out here, they're going to, you're going to have, you have shallower surveys, so they're going to be brighter, so they're going to be easier to get spectra for. And so you could knock it off without an enormous instrument to get the spectra. It's cheap and easy and could have a big payoff. So that's something I personally think would be very valuable. It's not the most glamorous work in the world. You're not going to get famous for doing it, but it's extremely valuable for allowing all the science that we hope to do. Anyway, that's kind of what I wanted to say. Does anyone have any thoughts? Yeah, go ahead.
I mean, this is deliberately provocative, but I mean, why should we spend time trying to double the return on the DDFs when there's, for good reasons, we focused on the best part of the DDFs to start with, instead of spending that time on doing the same stuff in YFSD?
Yeah, in my assessment, I don't know. I mean, that's why I said we should have, it's equally important to have a discussion. And I mean, my personal assessment is we're in even worse shape.
Exactly.
YFSD.
So, yeah.
You're in much worse shape, but at least, so I guess here's why I would say this at least can be solved. YFSD is unsolvable. I mean, you could fix this.
No, but I actually I not fully agree with that to some depth, right? To the full depth of LSST, I agree it's unsolvable in the WFD, but right, there's 4 AGN surveys with foremost that have analyzed all the data in the southern hemisphere. So between all of them, there's enough. We have, I think, enough identified AGN that at least to 22nd magnitude, right?
You said with which instrument?
For foremost.
Okay.
Preparing for foremost.
Preparing for foremost.
Right.
You don't actually have the spectrum.
No. But at least we know we have a good idea of
input
the
catalogs.
AGN candidates.
You have input catalog.
Right. We have So we have analyzed the input catalogs.
Right.
So
that's great. Yeah, it's good you have targets. I mean, I guess my point is this could be fixed before Rubin turns on. I don't think you're going to have your spectrum by the time Rubin turns on.
no, but you're not going to have a spectrum of those.
No, we're not.
Or-
Yeah, you can't fix
Either.
that, but you can get very good photoses.
Right.
You can get very good photoses because the data are high quality. So anyway,
So for the fields where somebody's actually wrangling the data or the data has been wrangled,
the prime areas, yeah.
right? But you said actually in the, or maybe I misunderstood. I thought you said some people were already doing the tractor photometry in the outer parts. No, okay.
No, not to my knowledge. That's one reason I wanted to kind of raise these things. Maybe someone out there is doing it and I don't know about it.
So I guess the question is this a dedicated postdoc, a dedicated grad student? Right, I'm trying to assess the level of resources we would need
Fan
to
did
dedicate to this.
LSS1. I mean, Fan is awesome, but it took him, how long did it take you to do LSS1? That was 3 months? Half a year to do LSS1. He knows how to do it though now. So it could be done. I don't know, throw money at Fan or something. Maybe he doesn't want to do it because he wants to do science now, but I mean, it's the type of thing. Anyway, that would be a very valuable thing. So, yeah, I mean, I think a very good dedicated grad student could do it and would do very well by having done it.
Right, and since for Euclid, it's more, you would really need a dedicated postdoc, just there's a higher level of difficulty there.
Yes.
I'm just curious, if when Ben did it, it's just half your time is mostly taken up by the running the tractor, or is it?
There is a learning curve. So probably for running takes a few weeks.
Okay, but the rest of the time actually they're checking the quality that the data is matching those things. Okay.
Yeah, and writing the code.
Yeah. We learned from Mark and Christina Nyland, and then he learned how to do it from them. So now he can do it. But I mean, let me ask this, how many people in this room know how to run tractor? Have ever actually run tractor? I thought you knew how to run tractor.
No, I haven't run it.
Okay, you know about it, okay. So the people in this room who know how to run tractor is 1. Is that correct?
I used to know, but I forgot.
Mark knows how- okay, Mark knows.
1.5.
Fine. Yeah, well, there's gonna be a learning curve then. So, yeah, so it could take a while, but it would be a very valuable thing.
So
And-
just another
Yes,
provocative
please.
comment.
Yes.
So let's not forget that we have super good quality likers from Vera Rubin in those regions.
Mhm.
And actually what we're seeing now with CTF, which is definitely not the same quality, in these IFETs fields where you have very good Rosita data, we are still finding targets that are not identified from the X-ray selection with variability. I will, this is a random number, but I estimate at least 30% of the candidates are not included in any, or are not associated to a given X-ray counterpart. So we can use complementary selection to fill these areas.
Absolutely. Yeah, that's a very good thing to do. So a couple things. First, of course, I would mention just, I'm an X-ray astronomer, so I have to defend. You know, EFEDS is very shallow.
Yeah.
Okay, XMM serves 10 times, it's several times deeper.
Yeah, but also we are doing this with CTF and not even the good quality data we're preparing now. So like in a few months, hopefully we will have much better photometry, and my hope is that this number will increase a lot.
Good, so you'll have AGN select, that's great. And so then if you have that, and if someone did all the tracking, you can have SEDs for all of them and photo-Zs. I mean, you're gonna have variability, you're not gonna have a redshift. But we, you know, if you did the tracking, you could have photo-Zs, you could actually do science with it. Whereas right now you're gonna have light curves. So I know it's a type 1 AGN, but I can't do anything with it because I don't know how luminous it is. I don't know where it is.
Yeah, just to mention that these are the same targets that Foremost will appear. So we will have in 5 years.
Foremost will do it, Moons will do it, PFS will do it. These fields will have spectra, but not on a time scale we need. Yeah, at least at the start. Yeah.
Ask Raphael, somewhere the UK's infrared cross-matching processing and contributions are.
So
within the context of the DGS in particular, I suppose.
Yeah, so I'll speak about this a little bit tomorrow, but the UK in-kind contribution with Manda Banerjee, we built a pipeline for joint processing of LSST and the VISTA survey, so video in the deep drilling fields. And that code is running, and we've tested it on the XMM LSS field where we have hypersea prime cam test data. We haven't done it on any of the fields covered by DARE.
You're doing veils, I presume.
We haven't done veils, but we are doing it, yes.
Okay, you're gonna do veils.
Yeah. I think the reason we haven't done it yet is because we've been exclusively testing on the hypersea prime cam fields. And we have to, in order to run on the dark energy camera fields, we have to also process that because the hypersea prime cam fields has already been processed with the LSST science pipelines. So we need to rerun the DECAM processing as well. And that's something that also Mara Salvato is very interested in. But again, that's the LSST and VISTA, or DECAM and HSC and VISTA. It's none of the other wavelengths. I think we were interested in moving on to Tractor and running Tractor, but we simply just didn't get to that stage. So I think VISTA, certainly we're hoping to contribute to that processing, but whether that's done before the start of LSST operations, because we were focusing on building a pipeline for processing LSST plus VISTA, and we were really just testing on hypersea prime cam. We weren't targeted towards generating usable catalogs before LSST came around. We're testing the pipeline. I think there are real barriers to reprocessing the DECAM imaging. But I think there's a new postdoc starting with Manda imminently. I think it would be definitely interesting to try and get that done in the next year.
Yeah, be a very valuable thing. I don't know who will take it on. I mean, I'm tempted to try it, but I know how painful it is. So that keeps me a little nervous from trying. Anyway, we spent a lot of time building up the middle part, so we want to get science out of those now. But fixing that would be extremely valuable, and let alone this. As far as I'm aware, we got nothing.
We do have Spitzer, actually. I just posted to the
Okay,
Slack
no,
channel.
there's data. I'm well
That's
aware
actually
that there's
reduced,
data. There's data. I'm not saying that. I'm saying you got to tractor it.
Yeah.
You got to do AGN selection. I mean, that's a lot of work. Yeah. Yes, all those things. I mean, we're not even close. And so, are we just gonna ditch this field and just say, well, here's 20 square degrees of great AGN science. We're just gonna walk away. Anyway, it's something that's worth thinking about.
Or we just wait for LSST and do it when LSST data are there when there's a higher motivation.
Sure, but again, Franz, I mean, having just gone through this ordeal for the past several years, as you know, I mean, I don't know if I'm going to want to spend 4 years in the middle of when the Rubin data are coming to do it.
Well, then that kind of answers your question. If there's not a scientific motivation to increase the numbers by a factor of 3 or 4.
Well, there is for the report you just said, but again, I mean, it's just picking among, do I pick up the silver or pick up the gold or pick up the platinum? Well, I'm going to pick up the gold and the platinum and let the silver go, but the silver is pretty darn good.
I mean, I think the problem is NSF doesn't care when things get done and who does it.
Yeah.
Right. So, I mean, the answer is going to be,
well,
yes, you're not going to do it in the next 3 or 4 years.
Well,
fine,
I will say
will,
NSF
right?
funded me to do these. That's how I'm doing it.
Yeah.
So it's something. I did what I could, and we're still trying, but we have to now get science out in the areas we did. Anyway, a couple more slides really quickly. Again, I don't want this to go on forever. Well, this makes the same point I just said. I mean, those are the squared. We can skip that one. We can skip that. I don't think maybe there isn't much else to say because we've talked a lot. Then we talk, these are the X-ray data. We can skip that. I'll say something about the X-ray in a minute. Next slide.
Just note that we actually only had a half hour scheduled, not that I wanted.
Oh, am I over? Okay, fine.
You're only over depending on how long people want to stay.
Well,
the temperature in the room is getting
okay, fine. You're great. Okay, so I think we can stop it. Here's the final thing I'll say. Go back to the first one. Yeah, those are just saying things. This one. No, the next one. How's that? Yeah, this one. Go back to this one. So we've talked about this one a lot. The other thing which I would like to do, I mean, in principle, but it's not clear to me I could win a proposal. It's not clear to me the proposal is winnable. I'd like to get X-ray coverage from XMM, for example, over the rest of these areas and over, I mean, all the cosmos 10 square degrees and all these areas. And how about this one? But I mean, you can work out the cost of that. It's like 10 million seconds of XMM time or more. So can anyone think of a really awesome science case that you could swing a 10 million or a multi-million second XMM proposal over to try to at least get something in those areas? I mean, the problem is, the way we got these with XMM is we said, look, all you have right now is Cosmos. We can improve Cosmos by a factor of 7. And we've done it. But once you do that, it's very hard to do it again because you're a victim of your own success. So can anyone see it? Yeah, go ahead, Franz.
What's the scope for StarX?
Well, it's not, what's the scope? What has to get accepted? We have a 50% chance of getting accepted. If StarX is accepted, we can pound the heck out of these fields. But the soonest that will happen, officially, according to what's written in the MidX book, is 2028. In reality, it's probably 2029. Okay. And first, we have to get accepted.
Yeah, because I mean, the most obvious thing is to do, X-ray variability. But that isn't something we're going to do with XMM. We would want to go over the same areas we already went over.
Right. Yes. Right. If you want to do variability, you do that. Anyway, I'm turning these ideas over in my head all the time. I would love to find some killer science goal that would say, oh, yes, we really need X-rays out here. And this is the great science we can do immediately that the X-ray astronomers will be into and would buy. And then also, of course, would lead to great science for all of us because all these fields would be better developed with AGNs. I'm just not quite sure how to get there. Because once you have 13 square degrees, it's hard to say, well, okay, I want to double it again. It's not that big of an improvement anymore. So anyway, that's another thing I'm wrestling with. But anyway, that's what I wanted to say. Is that hopefully that was somewhat useful. I mean, I hope that's kind of a wake-up call that the deep drilling fields are not in as good a shape as you think they are. And these are the best areas we have. And these are good compared to wide, fast, deep in general. And so that's all I wanted to say, I guess, about the deep drilling fields. And as was mentioned, in my opinion, wide, fast, deep is in worse shape in many respects, matching at least to the Rubin depth. And there, it's a much bigger problem. Here, you at least could imagine doing something to fix it. I can't even imagine fixing wide, fast, deep, but maybe people here have an idea to do that. So does anyone want to say anything about wide, fast, deep? I mean, I'll sit down now. And if anyone wants to say wide, fast, deep, I mean, it would be very valuable because I think wide, fast, deep is in a very similar situation. And it's perhaps not as widely appreciated as it should be. So.
I mean, I guess kind of just going back to what what was mentioned, but with the data we have, I think considering foremost, we've done the best we can, right? So you need to wait for the next step, which will be Euclid plus.
And wide, fast, deep. There's nothing else. There's nothing to do. You squeezed all the juice out of the infrared.
Right. So I mean, I think I'm just thinking of terms of AGN selection, right? Or actually, at least candidate selection, right? Right. So I think with the data we have, I don't know if we can really do much better until we have better data.
Right.
Right. And I think that's so
wide, fast, deep. Yeah. So you need better. So that's kind of what I said to answer Matthew's question, is, yeah. So you did what you could with wide, fast, deep. You're in bad shape, but there you are. And there's really nothing to be done.
I don't know if we're in bad shape, but we're in the shape we are.
To match Rubin depth data, you are.
Right, yeah.
To match Rubin depth data, you are.
Exactly, right? So we're 2 magnitudes shallower than
that's right. You're way shallow compared to what you're going to have with Rubin.
Can you not see this as a positive opportunity for a large discovery space for Rubin?
Absolutely, sure it is. It's great.
Absolutely.
Yeah, there still are things to do. Right. But at least here you could fix it, and you could fix it before Rubin started. Any volunteers? Yeah, right. That's the usual. So what the implication of that is even with the deep drilling fields, we'll get a third of the science out that we could get out. Something like that.
We get science from a third of the area.
Yeah.
I don't know if it's a third of the science.
But yes, fair enough. Yeah. You could triple all your source statistics with really high quality data.
Right.
And it's very tempting to go do it.
Yeah, you already published a series of papers based on that data set, right?
Was that?
Your group already published a series of
yes.
papers based on the
Yes,
existing.
and as has Mark Lacey's as well, Mark Lacey's group. So
at some point, if you could elaborate, okay, if we have a more data set, we could actually complement the current things we are finding now because we have a limited sample. So if we have more sample, we could improve or confirm the hypothesis. Is that something possible based on the current literature?
Well, I mean, I'm not fully. So
let's say you have a paper and made a conclusion and a finding. Then is there any points like, okay, if we have more sample, we can constrain this better?
You mean if you triple the sample size, what science goals would you achieve?
Based on you already published the results.
Yeah, sure. We know those things. Yes.
Okay.
Yeah, I mean, and you can do some pretty exciting things. We're doing some pretty exciting things in the areas we have right there. But the problem is, are they so exciting that you can win a 10 million second XMM proposal off of it? No, probably not. So, I mean, and that wouldn't come in time for Rubin anyway. I mean, that would take years to get done, 5 years before we'd even have all the data down. So this is what we're going to have. Pretty much, and it's very tempting to at least do what we can with what we have in our hands because there's a ton of great data there that is just lying there in the archives and no one's even picked it up. Anyway, that's that.
Yeah,
I do wonder.
Go ahead.
Yeah, I'm thinking aloud. But I do wonder if this is just something that, I mean, yes, the first couple of years, it's not solvable, especially since, take Chandra, for example, cycle 25 just came out yesterday. So those results are already set. And so that takes you right up until start of LSST.
Yep.
But a similar kind of thing for XMM is probably true, but this is one of the things where it does strike me that a large team proposal might have a chance
as a multi-year kind of thing. And maybe the way to do it would be to do it, I don't know, to negotiate something with the observatory staff, actually, to go that route, rather than to attempt to go through open competition, because I don't know.
Yeah, I see what you're saying.
This sounds I'm sorry, Neil, this sounds kind of scattered, but you have my brain going.
Yep. Yeah. I know what you mean. I mean, I dealt with the similar problems with the Deep Field South for many years.
Yeah.
So
fair enough.
I guess we have enough food for thought.
Yeah.
And we can continue this conversation tomorrow.
Yeah, great. Sure.
Right. Thank you, everyone.
Okay.
And